Hello. Hi, everyone. Welcome to SBC Day 2. I guess a lot of people are partying, so people will start walking in soon. I'm Alin Tomescu. I'll be your session chair today. And I want to introduce our next speaker, whose name I'm literally blanking out as I speak. Mahimna Kelkar from Cornell University and Cornell Tech. He's going to be speaking about complete knowledge of secrets. Really exciting talk. Looking forward to it.
Thank you. Okay, I'm really excited to be here. Today I'm going to be talking about our recent paper on complete knowledge, preventing encumbrance of cryptographic secrets. Oh, there's my clicker. So cryptography models a very simple form of knowledge. So what does this mean? If Alice knows some secret key SK, she can sort of explicitly furnish it as private input to a protocol and vice versa. So if you think about crypto functionalities, for the most part, you can think about them as being, say, a keyed functionality with some key SK that takes an input and produces an output. So this sort of talk will think about what happens with this secret key, instead of being held by Alice, is actually held inside of a trusted hardware box. So for the purposes of this talk, you can think about trusted hardware as sort of a black box that can run some predefined program and provides confidentiality and integrity of the output and running of the program. So in this case, if the secret key is held inside a trusted hardware, such that Alice doesn't know it, the TE can still sort of take part in the same crypto functionality. And this, as it turns out, is a problem, and I'll mention this in my talk. So basically, this is the problem of what we call key encumbrance. So in a nutshell, the idea here is to expose not the secret key itself, but a partial computational functionality of the secret key. So what does this mean? If you think about some sort of crypto functionality that uses the key, instead of it being held by Alice, let's say it's held by the trusted hardware here, let's say Intel SGX. So you can think about sort of the interaction with this keyed trusted hardware as providing an input to the program and getting an output that's based on the key and the input. But what if the SGX, trusted hardware, only responds to approved inputs? So there's a program that's running inside of the trusted hardware that only responds to approved inputs. This is what we'll call key encumbrance. And it turns out that it's not easy to identify key encumbrance. So for example, if Alice has her own key, she can sign all messages in existence. But let's say there's a program running inside a trusted hardware which actually controls the key. The hardware can block signing of a message for just one message, say hello. And it's not really easy to identify which one of these two scenarios we're in. And in fact, proofs of knowledge don't actually work because the same proof of knowledge protocol can be executed inside the trusted hardware itself. So for example, a simple proof of knowledge would be signing a random message with the secret key, but you can think about the same program, same protocol being run with the secret key inside trusted hardware as well. And in some sense, the motivation of this talk is that encumbrance allows you to prove knowledge without actually owning or knowing the secret key. And our paper introduces what we call proofs of complete knowledge, which will show unencumbered, complete access to ownership of the key. And in general, this encumbrance will also be for something like multi-party computation, not just trusted hardware, but I'll focus on trusted hardware in this talk. So before I get into complete knowledge protocols, I'll first describe why it's important to prevent against these key encumbrance by showing some attacks based on this. So the first one I'll show is trusted bribery, and this is the main one I'll focus on. So let's say we had a trusted hardware box that owned a key, and this key allowed a user to vote. But it had a program installed in it that said, for this election, I only will sign messages that allow me to vote for blue and not any other color. But it will allow all sorts of other transactions, including potentially transferring out cryptocurrencies, tokens, whatever else sort of the user wants to do with the key. Now, this sort of encumbered key program creates a problem, because here you can think about the key is Alice's key, but she doesn't own the key. But she can still do everything she wants with the key. She doesn't care about this particular election and is willing to be bribed for it. But she can still do everything else that she wants with the key. But at the same time, the briber is guaranteed that Alice cannot vote for anything else other than blue. So this sort of encumbrance creates a trustless bribery between a briber and the user who wants to be bribed, so that they don't have to trust each other, but can still benefit from the transaction. And in fact, the highlight of this paper is that there's been a long line of work on so-called coercion-resistant protocols, and they all break because of this key encumbrance attack. And I'll refer you to the paper for more details. So in general, you can think about this sort of trustless bribery as being expanded in the sense that briber can buy votes from a lot of different users using the same sort of encumbrance mechanisms. But what's even worse is we define something called a dark DAO, which is sort of like a vote-buying marketplace, if you will, where users who want to sell their voting power or even some minimal access to their keys can interact in a marketplace with buyers, or vote buyers here, who want to bribe these users to buy their votes. And sort of this marketplace allows selling votes to the highest bidder. And in fact, this is a dark marketplace in the sense that the voters and the vote buyers don't actually even need to know each other. And this was actually first noticed a few years ago, and the term dark DAOs was coined in this sort of seminal blog post by Phil Diane and others. But sort of the practical relevance of these kind of dark DAOs was brought up when we actually built a prototype and a follow-up work to the paper I'm talking about, actually, which we built sort of a dark DAO explorer and a way to do these sort of bribery marketplace in Oasis. The other thing I'd like to highlight is that it's actually not just sort of Web3 style bribery and Web3 style voting attacks. You can actually think about these encumbrance as being a problem on even something like end-to-end messaging systems, which offer deniability. You can also think about encumbrance being a problem for any sort of Web2 credentials, where these credentials can be sort of bought and sold or rented out. For example, selling the ability to tweet from a specific account, or password sharing, things like that. And I'll refer you to the paper for more details. So sort of the central question of this work is, how can we detect this sort of encumbrance and establish individual ownership, which standard proofs of knowledge don't actually give us? And so this is just a meme I'll leave you there, is like what we want is complete knowledge. So kind of let's try to take a step back and understand, why don't these standard proofs of knowledge work? So first, some background on proofs of knowledge. You can think about proofs of knowledge as an interactive protocol between a prover and a verifier, where the prover here wants to convince the verifier that she knows some secret. For example, the secret key corresponding to a public key that's known by both parties. So more generally, you can think about this as some statement X that's public, and you want to prove that Alice, here the prover, knows some secret witness W, such that f of x comma w equals 1. So most commonly, this is sort of an NP relation. But for all intents and purposes, you can also think about this as just secret key corresponding to public key to build intuition. So typically, proofs of knowledge have a couple properties that they need to satisfy. One of them is completeness, which you can intuitively think about as an honest prover who knows this witness W can always convince the verifier. The second one is soundness, where a cheating prover who does not know this witness should not be able to convince the verifier. And for proofs of knowledge in particular, you can think about a property called knowledge soundness, which subsumes the earlier soundness version, in the sense that if the verifier was convinced, then there is an efficient extractor device that can sort of extract the witness from the prover. So this sort of is the way typically knowledge is modeled in cryptography, through this extractor machine that can run on the prover and extract out the witness. And just as a sidebar, proofs of knowledge don't need to be zero knowledge, although they can be. So sort of trying to understand where these definitions fail, the kind of stark revelation here is that the extractor is often a theoretical proof construct. So what does this mean? So for instance, in most cases, it gets sort of code access or oracle access to the entire prover machine. And this actually may not be practically instantiable. So for example, if the key is held inside a trusted hardware box, if it's tamper-proof by assumption, the extractor should not be able to extract out the key from the trusted hardware. So essentially, this extractor that makes the theoretical proof go through cannot be instantiated in practice and won't be able to extract from this trusted hardware box. So in some sense, for our proofs of knowledge, we want our extractors to be concretely instantiable. They want to be practically runnable. So intuitively, we want some physical entity that should be able to recover, reconstruct the entire witness. So for the very least, we want sort of these straight line extractors, which means they should not be able to rewind the prover. And we also want sort of non-programming extractors, so they should not be able to program the random oracle, which is, again, sort of a theoretical construct that may not be practically instantiable. So this brings us to our definitions of proofs of complete knowledge. And the idea there is we need to make sort of these hardware-based assumptions. So we formulate this resource-based formalism with these hardware-based assumptions. And the reason we need to do that is you can think about everything that you can do outside of trusted hardware as being able to do inside of trusted hardware. So without hardware assumptions, it may not be possible to distinguish where the key is held at. Another way you can think about this is anything that you can do by a single computer, you can also do in multi-party computation or MPC. So again, you may not be able to distinguish just in the plain model, which is why our modeling will rely on these sort of hardware assumptions. So the key idea in this model is to physically instantiate the resource from basically the part of the protocol that enables the knowledge proof to go through. So we have a resource functionality R here that's connected to the prover, who is interacting with the verifier in this proof of complete knowledge protocol. And the extractor, instead of being a theoretical construct, is now actually thought of as an eavesdropper, man-in-the-middle entity that's modeled on the channel between the prover and the resource. So the idea here is that if the extractor learns the secret, then the prover or any machine that has access to this communication channel will have complete knowledge of the secret. So again, here the key observation or the key modeling insight is instead of having the extractor be a theoretical proof construct, we have it be modeled as a man-in-the-middle channel between the prover and the resource, as a concrete entity in essence. So I'll now define some proof of complete knowledge properties that we want to satisfy. The first one is, again, completeness. And the way we define completeness is that the honest prover can convince the honest verifier using an approved resource, R belonging to some approved resource set. And essentially, this sort of models the fact that these approved or honest resources will allow this channel E to extract out the secret. The second property is the more tricky one, which we'll call CK soundness, or forced revelation. And the idea here is that no adversarial prover should be able to convince an honest verifier using any practical resource. So not just the approved ones, but any unapproved ones as well, as long as they're sort of practically instantiable, without this extractor machine being able to recover the witness. So this sort of instantiable or practical resource set essentially will formalize our hardware assumptions for the protocol. And you can kind of observe here that the forced revelation also implicitly says that some honest resource will be necessary to provide complete knowledge. And so any proof that will go through will have the extractor being able to extract out the witness in practice. So I'll sort of describe two protocols for complete knowledge. The first one will be based on trusted hardware itself, so sort of a fight fire with fire kind of situation. And the second one I'll describe will be a proof of work based solution. So I'll get into the first one, which is the trusted hardware based solution. And here you can think about the honest resource as the SGXTE as a physical instantiation of a trusted party itself. So kind of this is the diagram here. You have a prover, again, you have a verifier, and the prover is connected to this SGX resource. And the SGX runs a very simple program for the complete knowledge proof. It just asks the prover to input the witness in plain text, checks the correctness of it, and just signs a message using its master secret key that it's seen the correct witness. And now the prover can take this proof and send it to the verifier, who can verify it, as I'll describe. But the main observation here is that the plain text channel between the prover and the resource will allow the eavesdropper on this channel to extract out the secret witness. So essentially, this relies on the fact that the input into the SGX will be given in plain text rather than in any encrypted channel. The verification is very simple. You can use this remote attestation functionality of trusted hardware in order to verify that the program running inside of the trusted hardware is the CK program. And then you can verify the signature of the trusted hardware using the master public key. And sort of the hardware assumption that's necessary for this plain text channel intuition is that the SGX cannot be sort of simulated inside of another SGX. Because if you could do that, you could imagine the outer SGX sort of encrypting inputs outside of it and then decrypting inside of it and then sending it to the inner SGX. So which would violate this plain text channel assumption that could be eavesdroppable. So this is where our hardware assumption for our protocol will come in, but as long as you cannot have a SGX simulated inside another SGX, this protocol will be sound. The second protocol I'll describe is an ASIC-based one. So the core idea here is that we'll take a well-known common proof of knowledge protocol, which is a Sigma protocol, and we'll sort of embed its transcript into a proof of work mining puzzle. And I'll describe what that means. So here, the honest resource you can think about as a proof of work mining ASIC, which again will take inputs in plain text. And sort of any form of encumbrance using trusted hardware or MPC will be slower than ASICs. And this is sort of the hardware assumption we'll use for this protocol. So hash computations on an ASIC will be orders of magnitude faster than any sort of trusted hardware-based or MPC-based CPU or GPU computation. So let me describe a little bit about this protocol. So first, for background, I'll describe Sigma protocols, which is a common three-round proof of work, common three-round proof of knowledge of some witness W for a statement X belonging to some language. So this three-round protocol has the first round as a message from Alice, the prover, to the verifier, which has a commitment A. Then there's a challenge phase, which is a response from, there's a challenge from the verifier to the prover. And finally, there's a response from the prover back. So it's sort of the general structure of a three-round Sigma protocol. And the Sigma protocol transcript here, which will be important for our protocol as well, is sort of just a tuple A, C, S. And the property that we'll use from these Sigma protocols is a special soundness, which essentially means that you can extract out the witness from two of these transcripts that have the same commitment. So the same A here, but different C and S's, you can still extract out the witness from these two transcripts. So this is a property of special soundness that's satisfied by a lot of these Sigma protocols. So just for intuition purposes, you can also think about one common Sigma protocol is just a proof of knowledge of the discrete log. So essentially, the witness here corresponds to the discrete log of some group element. and the Sigma protocol will prove knowledge of this witness, which is the discrete log. So how does our ASIC-based protocol work? So as I mentioned, there's a prover, there's a verifier, and the prover will be connected to this ASIC resource. And now the intuition is you will take the Sigma protocol transcript ACS and sort of do a proof of work mining on it so that the hash value of this ACS with some nonce is smaller than a target value. And again, the intuition here is that this channel between the prover and the resource ASIC is in plain text, so that can be eavesdropped by our physical instantiation of the extractor. There is a little bit of a pickle here. So if you remember, there's the special soundness requires 2 transcripts for extraction. So you sort of need 2 transcripts to be on the channel between the prover and the resource. But the proof should only contain one of these transcripts sent to the verifier. Otherwise, the verifier would also be able to recover the witness, which we don't want to happen. So the way we get around this is we use the verifier randomness. Remember, from the 3-step Sigma protocol, it's the second step, which is the challenge step, that generates the randomness. So we, instead of just using that directly in our proof of work, we will sort of generate many of these Sigma protocol transcripts using the same randomness. So let me kind of describe the protocol in a little more detail. The first step you can think about as the same as the Sigma protocol. You just have a commitment A. For the second step, the verifier generates some randomness R and sends that over to the prover. But instead of using that R directly, the prover gets the ability to choose a nonce mu to get challenge C by just computing the hash with the randomness. And then based on this, it will compute the third response, which is S in the Sigma protocol. And it will use this transcript now to mine again the ASIC proof of work puzzle such that the hash is smaller than some difficulty level. And the way this C is chosen is such that with high probability, at least 2 C's will be required to find the proof of work solution. So let's say the prover chooses 1 nonce, gets a challenge and a corresponding response. With high probability, if it tries to brute force through all possible nonces for the proof of work solution, it won't be able to find a valid one. It will have to sample a second, sort of this bigger nonce to get another C, S, and then try again with the proof of work mining. So this is sort of the thing that will allow for the extraction within the channel between the prover and the resource by our extractor E. And finally, when such a solution is found, you can just take that one solution and send it over to the verifier. So the solution here consists of not just the Sigma protocol transcript, but also these 2 nonces, U and V. And now what the verifier does for verification purposes is it can verify the validity of the Sigma protocol transcript and also the proof of work mining puzzle, and also verify that the proof was submitted in some parameterized time tau. And remember, this is where the hardware assumption comes in of the ASIC being able to compute the same hashes significantly faster than sort of any encumbered trusted hardware or MPC. So we will have this be sort of a timed protocol in order to have the honest prover with the ASIC being able to satisfy the proofs, but an adversarial prover without the ASIC not being able to do so. And you can run the same protocol for multiple rounds in order to decrease the soundness error. So you can look at the paper for more details on the proof, but essentially there's sort of 2 errors that we need to bound. One is the completeness error, which is the probability of the honest prover with an ASIC not finding a solution in that given time. And the soundness error, or the forced revelation error, which can fail in one of 2 ways. One is the adversary uses the ASIC, but somehow only requires 1 challenge C to succeed. And the other one is if the adversary uses a network of many CPU machines and successfully computes the proof of work. So we can sort of bound the errors of this protocol by running the protocol for some theta of the security parameter rounds, we can bound the error as being negligible in the security parameter. And the paper also contains sort of concrete parameterizations that can be useful for practical deployments of this protocol. So we have a couple prototype implementations. So the first one, for the ASIC, we implemented a verifier as a smart contract on Ethereum, and we parameterized it to work with the 12-second block times on Ethereum, and also with old ASIC hardware, which still turns out to be significantly faster than even thousands of machines running a CPU. We also sort of implemented a lightweight version of our TE-based solution on Android devices. So instead of using SGX, which may not be commonly available to all users, this uses sort of the Android phone TEs for the same purpose. I'll also briefly mention some new applications that are made possible only because of these proofs of complete knowledge that would not have been possible beforehand. So the first one I'll say is key coupling, which is this is the idea of proving that two keys or two addresses belong to the same entity. And this can be useful for all sorts of things, like proving I own two accounts, so that if I transfer between these two accounts, it's not taxed as a transfer. Right? Or things like KYC diligence, where I can prove that these are all the accounts that I own. And you can kind of see here that you can't do these proofs without our notion of complete knowledge, because you could have the situation where two different parties own these two different keys and use multi-party computation to complete the proof. So you can't have a key coupling proof without our notion of proofs of complete knowledge. The second thing you can think about as a new application is what I'll call atomic assets, which are non-fractionalizable or single owner assets. And you can think about use cases for these as blockchain representations of real world assets, like houses or concert tickets. You want them to be owned by a single person rather than being owned by multiple people. And you can sort of use our proofs of complete knowledge, again, to prove things like these. So I'll leave you with a couple takeaways from the talk. To summarize, our paper shows that encumbrance can create problems for a lot of these cryptographic protocols by violating assumptions about what it means to own a key. And our notion of complete knowledge provides a solution by enabling proofs of individual ownership. And the takeaway, one sentence here, is that if your protocol doesn't use CK, it actually could be vulnerable to a slew of these encumbrance-based attacks. And I'll leave it at that. I'm happy to take any questions.
Thank you, Mahinma. I think we have time for one or two questions.
Hi, Mahinma. So the key thing here is that the communication between the prover and the trusted hardware reveals the witness, right? And so one of the reasons why why the prover might use a trusted hardware is to not leak the secret key. But this seems like it might make the secret key more vulnerable to being leaked. So the prover might not want to use it. Any comments on that?
Yeah, that's actually a very good question. So sometimes for security practices, you might want to, in a sense, encumber your own key in like a hardware device so that only the hardware device knows it. And some companies actually have this security policy. And what I'll say to that matter is that in cases where these encumbrance attacks are not so much of a problem, that may be fine. But you have to think carefully about the trade-offs there. What extra defense in depth are you guaranteeing by hardware encumbering the key as like a security practice? And what are sort of the attacks that you also leave possible by the fact that the key was encumbered in a hardware wallet, and it will be indistinguishable from the key being encumbered inside a trusted hardware which runs like a general program that can encumber it further, like the functionality. So I'll just say like you have to think about the trade-offs there.
Cool, thank you.
Go ahead.
Good. Thanks, Mahim. A very, very clear, simple, powerful idea. I really, really love this. I have maybe a naive question. It seems like there is maybe something corresponding to designated verifier in some of these applications. So for example, the taxing authority, in order to be convinced of non-bribery, et cetera, may have to have an ASIC. In what sense are the provers essentially designated provers? Can they convince other people that everything was behaved and done properly? Or is that not too naive of a question?
So we have this notion of CK addresses as well, which basically say that once you've done a CK proof on some secret key, then it's a sense that always there will be the possibility that someone owns the key. So you sort of only need to do this proof once if you want to be convinced that somebody knows the key and it's not vulnerable to bribery attacks. So you could actually post these on-chain, and this is what we'll call, like we have our notion of CK addresses, like you can verify the secret key of an address being done in proofs of complete knowledge, and that's it, you can use that address anywhere else. With sort of the designated verifier part of your question, I'll say that actually designated verifier proofs can be broken by trusted hardware encumbrance. So you can think about a verifier whose key is inside of an SGX that accepts a designated verifier proof, and then the TE just constructs a publicly verifiable proof from just inside of, like the key inside of it, that can be accepted by any verifier. So you can actually break designated verifier proofs by this TE encumbrance. And the only way you can fix that is by having a proof of complete knowledge that the verifier's key given to the prover in this like designated verifier proof protocol.
Cool, thanks.
All right, let's thank the speaker one last time. So our next talk is on uncovering the impact of mental models towards adoption of multi-device threshold crypto wallets. The speaker is Aniket Kathe. I'm really happy to introduce him. Take it away.
Thank you. Hello, everybody. So, good morning, and thanks a lot for showing up early in the morning, such a rainy day, and especially after all the get-togethers and parties yesterday evening. I'm very happy to see you all there. So today, I'm going to talk about a usability study. So where we did a usability studies about the rise of the multi-device wallets. It was a quite interesting and unusual event for me, coming more like an applied cryptographer. We realized that there are interesting things happening with the multi-device wallets. And as an MPC fan and MPC user and developer, it's a first-time opportunity to see how these settings can be taken by the normal users. And that motivated us to start to do this study, and we found something usual, like as we expected, and some quite surprising things we come across as we did this study. And my aim here to use this talk is to actually present you those findings that we got so that we can learn as a developer towards building better distributed cryptographic or multi-party computation settings in the future. This is a joint work with Ishwar Bangipudi, Mohsen Manai, Udit Desai, and Moinak Mandal. Ishwar and myself are both here, and we'll be more than happy to take your questions even afterwards today and tomorrow. Okay. So the key thing to consider here is some basic information to begin with. We can indeed see the cryptocurrency user base is growing. These are the numbers from 2023, where the number of users are already in hundreds of millions and maybe touching several, even more than in this year. The estimated market size is going to significantly grow as we make further and further progress. And we estimate that it can be $1 billion and maybe eventually $1 trillion market for sure. And all these users, when they get connected to such an environment, these users need cryptocurrency wallets for storing and trading their cryptocurrencies. And in such an environment, what we wanted to study is that what kind of expectation that users have and what can we do about that. So as we all know in this auditorium, that when we talk cryptocurrency wallet, unlike with the traditional username and password mechanism in Web2 world, here we deal with a mechanism where we have a secret key or public key, or public key can also be called as wallet key, that are employed. And this secret key is something which is employed towards signing the transactions. And this introduces interesting aspects related to that, as we'll explore when users were informed and how they reacted to them. So if you look at cryptocurrency wallet, for this talk, my focus will be on comparison between the single device wallets, where the key, the secret key, is stored on a single device. That can be a phone, a laptop, some Exchange server, things like that. Or a multi-device wallet, where the key is stored on multiple devices. Either it can be replicated or distributed, but that's what is happening in scenario. And those devices can be user devices themselves, or external servers, or a combination of those. And when we now dive a little bit more into the detail for the multi-device wallet, there are two particular categories to consider in that space. I'll start with the threshold wallets, where the idea is that there is a single key which is actually distributed across multiple servers using a concept called secret sharing, and such that each of those devices have a share of the key. And a subset of them, typically we use words N and T to represent that. So N is the total number of servers, and T is a subset of among those that are necessary and sufficient so that such a secret key can be reconstructed. However, in the threshold wallet, the key doesn't get reconstructed. In fact, we generate the signature itself using those shares, using the threshold signature algorithms in general. On the other hand, there is a maybe a bit more popular mechanism, which we call as multi-sig wallet, where there is no single key which is present. Each of those devices have their own key, as I'm showing here, from key K1 to key 5. And there is, on the other hand, there is an access structure which is well defined. That access structure in this example is any 3 out of 5. And when any 3 out of 5 of these keys are employed, that can be used as a valid signature done by this particular group. Okay, so in general, both of them I'm represented as a threshold setting, but they can be also thought as a more general access structure setting, as we'll be looking into further down my talk. The key difference between them can be looked at what is known as typically considered accountability versus privacy, which means that eventually when we generate a signature using threshold setting, we typically do not immediately know which of the 3 parties have signed it. On the other hand, when we look at the multi-signature, it's clear because those 3 signatures show up there. And in that setting, we know, when we look at multi-signature, we know who all sign it. We also know what's the exact access structure that is employed. While in threshold setting, all this information typically can remain hidden, so that we even do not know what is N, what is T. We just see the final signature that appears on the chain. There is also one subtle difference in the sense that in terms of on-chain verification, threshold signatures can be cheaper because you just need to verify one signature, while in the multi-signature there can be more signature need to be verified and possibly stored. But there are obviously several wiggle room in this environment, but generally this statement still remain true. So now moving on from there, what's the reason for the single device wallet and what kind of vulnerabilities that can be present over there? Apologies for the typo, probably something happened working on the slides. So when we have a single device, only one device need to be compromised and the key can be lost. And there are 2 scenarios here I want to mention. Either the key get compromised and now your funds can be stolen by somebody, or key can be lost forever in some sense, and then nobody can even touch those funds for in general. In multi-device wallet, typically multiple devices has to be simultaneously compromised, and that's the reason typically, at least from more technical perspective, multi-device wallets provide better availability as well as security. But one of the key questions that come to our mind is that how can we even justify that in the paper where that multi-device wallets are better? But thankfully, a very interesting paper by Ita et al. Demonstrated that for majority of setting, when we have multiple heterogeneous keys, that mechanism is proven to be secure, and we employed that analysis towards establishing as a fact that multi-device wallets are better than single-device wallets. Moving on, why this is important is that attacks on wallets are extremely common. Easily around 20% of Bitcoins are already lost and stolen in general. And if you look at even just the numbers, in several billions of dollars are stolen already in cryptocurrency exchanges. Several existing works have already demonstrated the vulnerabilities of the single device wallets when they did different kind of analysis, usability analysis, as well as analysis of what's happening on the internet. However, one interesting thing we observe as we start to look into more detail is that single device wallets seems to be still very popular. And one of the questions that we wanted to also study in this space is why, as one of the interesting things that we wanted to see. So the question is that what stops users from adopting multi-device wallet at a large scale, as we see, and that was one of the key questions that with which we started to do our study. So then, based on this, our knowledge so far, we formed 3 key high-level questions that we want to do a study in this usability study. What are the current user groups and their preferences for the cryptocurrency wallet? This question is raised by so that we can compare the longitudinal study, means like what people found maybe 2 years ago and now what we are finding now, and so that we can use that knowledge. Then, provided with the essential information, are users willing to shift to multi-device wallet? Typically assuming that many of them are still working with single device wallet. And the final thing, which was in fact my favorite thing that I was really curious to study, is that what kind of default architecture setting, access control settings that users typically prefer and they may like as we build these solutions. So I'll go through each of these questions one by one. But before I do that, I want to talk about the study design. So we started with some general questions of the cryptocurrency wallets and usage and preference related to the first design. And then actually we built educational video, 2-minute educational video, 2 of them, to educate user about different single device wallet first, like hardware wallet, like what happens on the phone and stuff like that, so that they get some idea if they have not. And later a second video, which again 2-minute video, to explain them what are the multi-device wallets, what are different kinds, and what kind of guarantee they perform over there. We did talk about this trade-off between accountability and privacy of the multi-device wallet there, but we, to make sure to keep the discussion simple there, we did not talk about the performance aspects in our video when we created those. And then once we give this information, we first ask them some deciding question like, do you like multi-device wallet? If yes, why yes? If not, why not? And later, for those users or people who took our test, we also then go into more detail to understand what kind of settings they can like when we look at these different threshold settings and other environment in that case. So for such a usability study, we did recruitment following the Prolific, which is a common mechanism. We started our study first having pilot, where we took prominent, knowledgeable people and run our study with them. And special thanks to Omer Shlomitz and Patrick McCurry to spending time with us, doing the pilot with us, and spending 2 hours to just ask us questions as well as answer our question, which helped us a lot towards building this study when we work at it. We were initially worried that can we find really users who are knowledgeable in cryptocurrency space on such environment like Prolific, and we're surprised. In fact, we could find them very easily. I mean, we could have easily did study with thousands of users if you have time and money and bandwidth. So indeed, for everybody, if you want to do usability study, all these AMTs and Prolific, Amazon Mechanical Turks and Prolific, you will find a lot of users who can provide you good usability studies. In total, we collected around 524 responses, unique, but we discarded among them around 175, when we look at their answers and when we realize that actually there are inconsistencies and in their responses, so we discarded those responses, and basically then we collected this data from the data that I'm going to show is coming from 375 users from US, UK, and Canada in general. Mean time for this study was around 22 minutes with them, and they were appropriately paid following the standards. Okay, so what we observe now, start going to the different parts. So the first question was what kind of users are there and what their knowledge is that. So we actually found there are two self-reported groups based on how they do, based on their usage and how long they have been involved and several other factors. We found that there are newbies, that means these are the users who started very recently, mostly in the fear of missing out in sense, and there are non-newbies who actually have been already doing trading in such an environment as well as has been involved with the interest in technology. The reason why we have this trading and interest in technology is because one of the earliest study demonstrated that they find there are three categories like cyberpunk holders and newbies, but we realized that over the period actually we are not able to differentiate between the cyberpunks and holder, and we could only find the newbies and non-newbies as the two particular categories over there. When we started asking different users, so first question that we asked that how much is the rating is important information for different wallets as we pick, and we found that maybe not so surprisingly that people do find that to be useful, but not everybody says that that's not the only thing. They give importance to what was their own user experience was, as well as something when they work on such an environment in general. And all these charts will have two parts. One will be newbie will be in red and the non-newbie will be in the gray as you see throughout the study in general. So it's certainly the improving rating and having better user, it certainly helps for the wallets in general. We then start asking them questions in terms of how long have you been active in such an environment. And there are, as probably many of you will expect, we are seeing more and more users joining in such environment, which we see here as well, that many of them were actually involved in 1 to 3 years, and then things get reduced slightly here. Less than 1 year, obviously, because it's a short time period, it shows up as a small thing over here. Then we ask what kind of wallet they have employed and used, and we also give a field there so that they can give their own names there. And this is the information that we found here, where at least when we did the things, most of the users were employing Coinbase, MetaMask, and Binance. But I'll say that this is indeed study from 2023. So if you do not see your favorite wallet here or favorite mechanism, these things keep changing. So one more aspect to take from user study is that our questions can be, I'll highly encourage to look at the paper because you might find our study useful to redo again every now and then to understand how these things are evolving in general. So now we started going to the more concrete question. The first thing that we were interested in that, okay, are you aware of the multi-device wallets? And significant number of them were actually not aware of the multi-device wallet. And we kind of expected that it could be the case, and that's the reason we already created video so that we can bring everybody to the same knowledge level as they go into the further questions in general. So many users were not aware of the multi-device wallet. I think this is changed over the period, at least that's the hunch I got in last year or two, but still we can expect that most users are typically a single device wallet. And then first question that we ask to this user is that, what kind of concerns that you have, what are the biggest concerns that you have when we look at the wallet? And the two key concerns that emerge in such an environment is the compromise of the server, where the server get compromised and my funds or my key will get lost, was one of the concerns that we get up, as well as the loss of the key by the user, where I somehow lose my key, and that also come out of mechanism. Very interestingly, you can see the lack of recovery mechanism also showed up as one of the interesting thing, motivating again more research. And I know that there is some interesting research happened towards having good recovery mechanisms, including that's certainly something that I'm interested in, and certainly that showed up as one of the concerns. So indeed, some nice problem to work on for all of us here. Then moving on, then we asked them that, oh, are you willing to shift to the multi-device wallet? We did that after showing them the video. And then still we see that very interestingly, majority of them say that sure, we will like to move, but not everybody. Still 40% of were still mostly with majority of them in newbies, still were not willing to shift to the multi-device wallet. And that was a bit surprising to us, but as always with a usability study, we ask them to also give reason so that we can study such things further. And there are interesting things we found that I like to share. So basically these are different user number there, still anonymized for this purpose. So I like to keep things simple and easy to and without much complexity was one of the things that we heard. I'm happy to be in control of the key as I believe the risk is low. I prefer to be responsible for my own key. If I lose them, my fault. So we got such interesting results. I prefer a single storage location. One location is easier to secure than more multiple locations. So very interesting thought process we come across as we did this. What we did is that we coded these responses, means that we make sure that we created different categories and two different researcher from our side completely separately make sure to read those responses and based on that put them in different categories. And after this coding, we found that interestingly, what are the reasons that people are not willing? So it seems like for some users, even after looking at the video, they feel that the single device wallets are more secure. But interesting for us, and this will be a kind of a recurring theme for the rest of my talk, will be that many people say that I don't want to lose control of key. Okay, and that come up as an interesting reason, and we'll see again it coming up in a slightly different context. Moving on, then we take the further step to understand the difference. Okay, multi-device wallet, you heard about that, you look at it. Now, among the threshold wallets and multi-sig wallet, do you have any preference? And indeed, majority, but not a significant majority of them prefer threshold wallets. They said the privacy feature is a nice feature that we don't know what is my access structure and only a signature gets generated. But some users insisted that they want accountability such that when things go wrong, we can pinpoint who have done something wrong. So that did show up as well as an interesting thing. And again, these were followed by the reason like, why are you picking this way? And these are quite interesting, some of the interesting responses, more you can find in the paper. So the thing is, the first thing is that the fact that the NNT values can't be found from the aggregate signature seems like an added layer of security, that some say. On the other side, when somebody say for multi-signature, they say that this way I can know which people and device were used to provide signature. Although we do not talk about performance or computation cost on our side, we did get an interesting comment where somebody say that threshold wallets are more efficient because on-chain verification becomes cheaper, and they indeed presented that as the reason from their own knowledge base in general. Now, coming to the third question in terms of, all right, so for all these settings, what kind of access structure or what kind of how to organize your access structure for multi-device wallet. So in that setting, we ask this question where we say that, let's say I give you a setting. The first setting to consider is, let's say, 150. So we'll say there'll be a lot of servers available. You will be, 100 servers will be randomly selected from a lot of servers that are available online, and your threshold will be 50. The second one was 100 are selected again, but threshold is 5. And the third one, we say that we are going to pick 10 reputed servers which are well known, and among them we are going to select 5. So we give these are the example setting to understand what kind of user find. And it was interesting, maybe the accurate term, that we found that majority of them, 60% of them prefer fewer reputed server over just picking nodes or users from all over the internet and using them in the setting. So which was quite interesting. They say that trusting them is better than just somebody be available online. And reputation over the number of servers was kind of a thing which majority of users like. And one more thing question that we ask is that let's say we have 7 servers available and 2 of them are sufficient for threshold. Are you willing to increase this threshold? And again, the response there was demonstrating that, yeah, they say majority say that, sure, we can increase the server, which also is a very interesting phenomena when I compare multi-party computation in general and wallet, that in wallet setting, kind of it demonstrates that people are more willing to go for higher threshold values, and they're less worried about lack of availability in case some nodes don't show up because they say that, oh, we can go after them and find them out. So that was also the thing. We found that they prefer to go for higher threshold values in general. Moving on, then we asked some further questions, especially for single device wallets, that, oh, what are your expectation? Does your responses change when we provide different scenarios? Let's say where your devices can get compromised, and in that case, where will you prefer your key to be? Still, people found typically that even when the client's devices get compromised, still they'll prefer something like a paper wallet more than just storing the data on the external server as a mechanism that they liked. We did that with the server compromise, and the answers were still very similar. So typically, users do want to have control over the key, was certainly something that was observable even from this example. Then we ask for somewhat related question, which is related for both single device as well as multi-device, is that how can different government influence can work? We ask the user to choose between locations of the server and the government influence. So the question is that, can we say that the governments can block access to the key, or can they access the key or read the key from the servers if we store? And what we found is that a very interesting mechanism is that they're fine if the government can see their keys, but they certainly want to make sure that their access doesn't get locked, or that they stop getting access to the environment. So they are not worried about somebody watching their key, especially when it's come to more like a authority, but they want to make sure that they still have control or access to their keys and they can perform transactions that they wanted to perform. And these are the numbers in that respect. Yeah, so what did we learn from such a study? So the one thing that we learn is that when we do educate and nudge the users appropriately, they can indeed be pushed towards employing more secure solutions such as multi-device wallet. And it's important to make them aware of the risk of single device wallets, and then correspondingly suggest that we need to convey the difference. We need to convey them the difference sitting in a multi-device wallet, and so that they can pick the services and setting that they like the most. But more importantly, because they want the control by themselves, they want to keep the control there, we required uneven weight distribution kind of a setting when we look at define such distributed wallets. And I'll go into a bit more detail on the next slide. As expected, we did come across a trade-off between the threshold and multi-sig, where we look at the privacy and accountability trade-off. And indeed, the accountable threshold signature kind of ideas are very interesting in that space, if we can make them work for the schemes that can be typically employed by all different blockchains and environment like that. And basically, we want to make sure to have distributed cryptographic schemes so that if they provide more control to the user so that they find them to be more approachable, rather than just using some MPC server who is generating keys on your behalf. So when I say more user control, I want to give one particular setting which we ask user and they find to be useful, is that for threshold wallets, we ask the question that either you divide the keys among the servers versus dividing the key in two parts, where share 1 is always available to the user and share 2 is distributed among the server. And we found that user really like this second setting, where we have a distributed setup where the server themselves cannot sign on your behalf, and you are inherently the user is always have ultimate control in such an environment. So this is very interesting, because for some schemes like ECDSA, EDDSA, building such scheme could be non-trivial, such an MPC solution. So it's a very interesting thing that I found as a nice cryptographic challenge. Most user participants wanted to remain in the control of the key, as we saw, and they like to also increase the threshold, as I already see. So these were the interesting things I found. So finally, what are the takeaways that I found? The thing I found is the data-driven investigation is indeed a nice thing to do, and I hope that our study, which is the first study of this kind, motivate further studies when we build wallets with multiple devices and using threshold cryptography, as well as MPC in general. And user need the control of the key was something that we find to be a very important thing. And I hope that this study motivate you to think of interesting questions to ask and build on further studies from there onwards. Thank you.
Thank you, Aniket. I think we have time for one quick question. So I can actually ask something. So you mentioned this trade-off that users prefer between privacy and accountability, privacy of the threshold versus accountability of who signed if something went wrong. So there's some new work by Dan and Chelsea Comlow called Threshold Accountable Private Signatures, I believe, TAPS.
Yeah.
Did you include that in your study?
Yeah, so because we have included that in our analysis, implication that we presented, but we have not included that in the study. The thing could be, we want to make sure that the signature that we employ in such an environment remain directly applicable to blockchains. And because there were no such practical product available by that time, that's the reason we did not include by study. Yeah. But by the time we were doing study, the more work was happening. So it can be indeed interesting to see how users react to that.
So, yeah, it sounds like it's something that some blockchains might want to implement.
Indeed.
Yeah. Great. Thank you, Aniket. Let's thank the speaker one last time. So our next talk is an invited talk on MPC custody at Coinbase by Yehuda Lindell. It's my pleasure to introduce him. Take it away.
Thank you very much. Thank you for inviting me. And I'm going to talk about the system that we've built now at Coinbase for custody and more exchange. In fact, this is the system that's going to be protecting the vast majority of all the assets at Coinbase. It's joint work with the cryptography team at Coinbase, including Arash Afshar, Yisho Chen, and Samuel Renalucci. Samuel and Arash are here as well, so you can speak to them afterwards. The description I'm going to provide is not a full exact specification of what we're doing, and it won't include all details, and a legal caveat that this is a living, breathing system, and it will change over time. But this is the design and architecture of what we are using, and it will give a very clear and transparent understanding of how we're protecting assets at Coinbase. So I want to start with very briefly talking about a couple of the general challenges of asset protection with current systems. We can divide them possibly into offline, online, and some types of hybrid. But an offline system is an air-gapped system. The keys are on a machine which is not connected to the internet in any way. And this can be built with very high security. But it's important to understand that offline systems are not necessarily secure. Just to say the obvious, if you take a laptop that you buy at, at Best Buy, and you put it in the cupboard in your office with a lock that can be broken in 2 seconds, and you connect with a USB drive to upload the transactions and sign, and then download the signatures, this is going to be extremely poor security. So questions like, how indeed does this offline system actually communicate with the world? How do you upload what you want to sign on and download the transactions? How do you physically protect that offline environment? Who has access to the machine? Can a single person go in? Is there physical security around it? All of these questions are very, very critical when it comes to building offline systems. And offline systems generally result in challenges regarding time to sign. And there's also a very clear trade-off between the more controls we have around it, then this, of course, will increase time to sign. And that can be a problem with SLA because what's crucial is to protect the keys, but also to enable people to do business. If people can't transact quickly, then this is going to be a very big problem. In an online system, at least a naive online system, keys are held in some server, and there are obviously very, very clear security challenges. These are highly lucrative targets, things like supply chain attacks, insider access, 0 days. All of these are huge threats. And therefore, such a naive online system will typically not be suitable for large amounts. But the way that a lot of these systems are set up is that you'll have some amount in an online system which will give you day-to-day liquidity. You'll have a large amount of reserves in an offline system, and you'll transfer back and forth as needed. Okay, and obviously in an online system like this, you get immediate response time. One thing that we always keep in mind is this idea of a single point of failure or a single point of attack. And no matter how much you protect a system, when it's so lucrative, and I'm talking about billions and tens of billions and even hundreds of billions of dollars worth of value, then these are very, very attractive targets, and we have to think about how much we can protect them. So again, offline systems can be made secure, but they also to some extent become a single point of failure, because at the end you have a key sitting on a single machine in a single room with maybe not a single person, but with some people, some small number of people in that room with them. And although there are very, very good mitigations, these mitigations are costly also in terms of time, and the threat is always still going to be there. I do want to stress that there's a very big difference, however, between an offline system that you use for ongoing signing on a regular basis and an offline system that you'll use for more infrequent operations, for example, like key generation ceremonies. The reason is that people can be more careful, and more care can be taken when something is infrequent rather than when something is very, very frequent. Okay, so when you do something only every now and then, you're generally more nervous about it, you're more careful about it. This is the reason why social engineering works well on things that people do all the time. Okay, let's talk now about a system that we've built. It's called Core KMS Vault. It's already being used, and it will be used for more and more products in Coinbase for custody, for exchange, and so on and so forth. A couple of design principles that we had are, one, flexibility. We need to be able to support multiple products from the system. We don't want to have many, many systems. And therefore, this system, Core KMS Vault, has to be able to provide different security trade-offs and response speed, usability, and so on and so forth, so that it can meet the needs of each different product. In terms of security, we want no single environment with key access. We want strong separation. We want different types of entities with strong separation between them. And we want defense in depth throughout. So we use MPC or threshold signing to obtain this strong separation and flexibility. We can have different numbers of entities of different types, and we can tailor that to the product. The asset keys are shared amongst the entities, and they're never brought together throughout the entire life cycle. And backup is also an extremely important part of the system, because I always like to say that there's only one thing worse than having your money lost. It's money stolen. It's when you lose your money yourself. So backup needs to be done very, very carefully, both in terms of disaster recovery, in terms of being highly protected, and we use public verifiability to make sure that we're able to, in an offline way, in an ongoing in an ongoing manner, to verify that the backups are safe. Okay, so we have three entity types in Core KMS Vault. We have an offline environment, we have human approvers, and we have MPC servers. I'm going to go through each of the different entity types, and then I'm going to talk about how we actually carry out the operations. So the offline environment is what you would expect, some type of offline machine and a separate store of key shares. Exactly how that is built and what is done, these are things that we are not going to talk about. But I will say that it's a physically secure location with strict access limitations. So a lot of control around this environment. Importantly, unlike classical offline environments, in Core KMS Vault, the offline environment only holds one share of the key. So it's not a single point of failure. Having said that, and this comes back to the defense in depth that I talked about, the security of this offline environment is designed in a way that even if it would be the same even if we had the full key there. So we're not taking any discounts on how much to secure that environment. The second are human approvers. These are people with devices. So these are human operators, and they may have a mobile, they may have a laptop, and they hold shares of a threshold decryption key. Okay, they're the secret shares that they hold. So think, for example, TDH2 by Shoup and Gennaro. And this threshold key is generated via MPC out vault generation amongst the human approvers. And how does this connect to the asset keys? There is one share of the asset key which is held by the human approvers, and this share is encrypted under that threshold encryption key. Okay, so we have one share being held by the offline environment, one share being held by the human approvers, but that share is encrypted under a threshold encryption key, so you need a quorum of approvers in order to be able to access that share. And the human approvers can be arranged in any access structure that you would like. We can define a quorum, and our system supports quite advanced access structures, so you can think of actually defining a tree, and within that tree you can have AND nodes, OR nodes, and threshold nodes, and you can do anything you want. So you can say 3 out of 5 and 2 out of 4, and of course you can do much, much more complex access structures as well. And an important property of this human improver environment is that they are humans, meaning that they're sometimes available and sometimes they're not. And they're also, if they're using their laptop, they may at some point just close the laptop because they're finished working for the day, or they finish their shift, or whatever it is. And therefore, we do not require the human approvers to be online at the same time. We do not require them to be carrying out ongoing operations with each other. And therefore, the type of operations they can do must be of that type only. Importantly, I'll just note that the threshold decryption indeed requires each party just to generate a single partial decryption. They do not need to interact with each other in order to finish this process. And the third entity type is the simplest type, I guess. These are just simply MPC servers, or online MPC servers. Each server holds their own database of key shares. They're always online, and they can interact with each other. So how many shares do we have? We have one share for the offline environment, one share for the human approvers, and one share for each MPC server. So if there are 4 MPC servers, you would have 6 shares overall. Okay, the infrastructure for each of these environments is very, very different in terms of the type of machines they're running on, their location, who has access, and by definition, that gives us very strong separation. And strong separation is crucial for any MPC or threshold signing system, because if you, for example, split a key between 3 machines, and all those 3 machines have the same administrator sitting in the same room running the same operating system, yeah, maybe it's better than a single machine, but it's not a lot better than a single machine. It's actually quite close. Whereas if I have them in very separated and different environments, that protects me against 0 days against the systems. It protects me against corruption of a certain subset of the infrastructure of the organization, and so on and so forth. The offline environment, without their participation, there simply is not enough key material online, and therefore nothing can be signed. The human approvers are somewhere in between an offline and an online type entity, because those devices can be disconnected by the humans, and at which point, once again, if there isn't a quorum of humans who have approved, there will not be enough online key material to sign online. And the MPC servers are also very highly protected. They can be locked down in the server infrastructure, and depending on how one wants to deploy such a system, they can be also administered by different sets of administrators. They could even be in completely different environments, like different clouds and so on and so forth. Core KMS Vault can be instantiated in multiple ways with different types of entities. You don't necessarily have to have all 3 types of entities in every instantiation. And furthermore, you can have a different number of each entity within your instantiation. You may have different numbers of MPC servers or different numbers of human approvers, depending on the type of product that you're building and what you're trying to protect. And you can also have these entities in different places. For example, for a non-custodial product, you could have human approvers at the customer and MPC servers at Coinbase. For a custodial product, you would have MPC servers and human approvers all inside Coinbase. So this is the way it could look. You have an offline machine. Here, for example, you have 4 MPC servers, and maybe you have 5 out of 20 human approvers, and therefore you would need all of these entities in order to carry out any operation. Okay, we're now ready to talk about how operations are carried out. We'll start with key generation and backup. If it's a system with an offline environment, then the property that we want is that the key is never online until it is used, and therefore there is a key generation ceremony in a special offline environment. And I say a special offline environment because this comes back to what I talked about initially, that security in an offline environment can be much higher when you're doing infrequent operations like a key generation ceremony. And in this ceremony, generate a bunch of keys. The keys are then shared and encrypted under each recipient's key. So the offline environment has one key share. The human approver share will be encrypted under their threshold encryption key. And each MPC server has its own public key, and each of their shares will be encrypted under their own public key. And then that will be exported from that offline environment. If there is no offline environment in the system, because that's the type of a vault we're using, then it will be an MPC key generation operation. And at key generation, as I mentioned beforehand, all key shares are backed up using publicly verifiable backup with a quorum of backup entities, and that quorum, again, is a different set of parties that is defined. Their backup shares are protected using hardware and software. So, for example, you could have UBHSMs or things like that to protect those shares. The fact that it's publicly verifiable backup means that given the asset public key, given the public keys of the quorum backup entities, you're able to efficiently verify that the ciphertext indeed holds the correct asset key and nothing was corrupted. You don't need to expose any key material in order to carry out that verification. That's a very, very important property. Okay, now we'll get to the complicated process, which is how do you sign with this system? So the first step is at the offline environment. The offline environment receives a transaction request, loads the key share in however that offline environment operates, and that key share is then sub-shared into shares, one sub-share for the human approvers and an additional sub-share for each MPC server. So in the diagram we had with 4 MPC servers, you would be sub-sharing this into 5 sub-shares, 5 additive shares. This just means random values under the constraint that they sum to the offline environment's share. And these are then encrypted under each recipient's key, again, the public key for each MPC online server, and the threshold encryption key for the human approvers. And this sub-sharing is fresh and different in each transaction. That means that as long as one of the entities later is honest and they erase their sub-share, the other sub-shares will be just complete garbage and meaningless, and we don't care if they remain in the system because they don't, information theoretically, even hold enough information to be able to do anything. So this is the way it looks. You can see that step number 1, you have a transaction request over here. Then the offline machine will sub-share and generate the sub-shares to each of the parties, encrypt them and output them to the system. And of course, you have this some operator in the offline system which is going to load the appropriate share for the asset key. Step number 2, these shares, encrypted sub-shares, have been output from the offline environment, and the human approvers are next in line. Each human approver up to the last in a quorum. So if we have 5 out of 20, then the first 4 human approvers to connect will work in this way. The last one worked differently, so I'm separating it into 2 steps. So each human approver will receive the transaction request and will verify transaction attestations. This is extremely important because it's security of a signing service is, of course, only as secure as the keys themselves from being stolen, but it's also only as secure as the machine who can issue a request to sign. I don't need to steal your key if I can ask to transfer all of the money protected by that key to my address. And therefore, attestations are important. These are signed attestations from different systems inside Coinbase. For example, there's a system which does fraud mitigation, looks at the parameters of the transaction, and if it's a suspect transaction, will not issue an attestation. You would have an attestation also from the service that receives the request externally. You would be verifying at the very least both of those attestations, and the system can support multiple different attestations, again coming back to preventing any single point of failure. So it's not just who holds the key, it's also who can tell me to actually sign on this transaction. And these attestations are verified by every single entity in the machine, in the system, with the exception of possibly the offline system, because we want that offline environment to be very, very simple. But again, that's a choice of whether we want or not, but all the others always will verify before doing anything. Now, each human approver, after verifying the attestation and saying, yes, these are fine, will generate a partial decryption of the shares that are needed. There is the approver share, and there's also the sub-share generated by the offline environment. So there are two shares here that partial decryptions need to be generated for, and this is what that human approver will do. And then those partial decryptions will be re-encrypted under the public keys of the approvers. The reason why this is done is because once you have enough partial decryptions, it then becomes a public operation to decrypt. So to prevent anybody else from decrypting, these partial decryptions are re-encrypted under the regular public keys of all of the human approvers. That's everyone up to the last approver. The last approver who joins or who accepts the transaction will do the same thing initially. We'll verify the attestation, we'll obtain the partial decryptions of the other parties, we'll decrypt them, and then we'll just be able to combine the partial decryption, if its own partial decryption with the others, in order to get the shares themselves, the approver share and the offline sub-share, and we'll add them together. Okay, so that's what you can see here. We now have each human approver over here. Each human approver, they provided their partial decryption, and the last approver now has its own sub-share, its own share, the approver share, and also the sub-share from the offline environment. We're now ready to start signing, so each MPC server also receives the sub-share from the offline environment and also loads its own share from its database, its protected database, again, after verifying all attestations. All the MPC servers do this as well. And once we do this, the MPC servers and the last approver all agree on who is playing. Because there are a number of approvers, and maybe there'll be more than one approver who claims to be the last approver, we want to make sure that everybody agrees, that we have consensus on who is participating, because this is what MPC protocols or threshold signing protocols assume. And we also make sure that the secret material they have correctly adds up to the private key. We do that, again, in a secure process in order to make sure that nothing bad happens, for example, if the offline environment is corrupted and actually send bad sub-shares. Okay? We have a zero, we're always assuming that anything in the system can be corrupted, so everything is validated from the beginning to the end. Once that is done, the MPC servers and the last approver can sign. Here, the last approver needs to remain online, but remember we talked about the asynchronicity. That's between different human approvers. The fact that the last approver will remain online, that is fine. They're interacting with online servers, which are always online. So they run, sign on the message. They then they refresh the sharing of the asset key. So the asset key changes every time, except for the offline environment. No one talks to them, so the refreshing is done of the shares of the MPC servers and the human approver, but not of the offline environment. Then all state information is erased, and we finish the signing process. So it's a rather complex process with multiple steps, but once it gets started, once the offline environment has output its shares, it will complete very, very quickly. The speed with which the offline environment will respond will depend on how it is actually constructed, and that's beyond the scope of this presentation. Okay, so that's what I think I need to go through the diagrams, but you can see the processes that I talked about. The last operation I want to talk about is approver administration. We need to be able to add approvers, remove approvers, potentially change the quorum structure for whatever reason. We want to refresh the approver threshold decryption key so that it's not always the same. You can't slowly go and steal a share one at a time from each party. And all of these are also run via MPC. Of course, also generating the share, which I talked about, generating the threshold decryption key is also done in MPC. So we have MPC protocols for doing all of these different operations, and that's crucial because we need to manage those keys and the users. And important things you might be thinking: why are we using a threshold decryption key? Why not just have each approver have their own public key? The reason is, if an approver leaves and we have a new one coming, we need to issue them a new private key, a new public key, then now the encryption of all the asset keys is no longer valid. And we're not going to start re-encrypting 1 million, for example, asset keys every time someone leaves or joins, both because it would be computationally expensive, but also because it would itself be a security risk, because you bring online keys that are not in use, and that's something that we don't want to do. Also, all of these operations require assigned admin quorum approval. So how do you add an approver? You need to have, there is a set of administrators who need to approve that. You get a signature, and only then are you willing to go ahead and carry out the operation. A couple of properties. In terms of security, a key cannot be brought to signing without the approval from the offline environment, a full quorum of approvers, and all MPC servers. This is crucial because of the attestations. The attestations are verified by each and every entity, and that ensures that key misuse is very much mitigated. When you're using an offline environment, before a key is used, it is never connected in any way, shape, or form. And there is no single point of failure or attack in the system. Everything has multiple points that you would need to attack simultaneously, both in terms of holding the key, providing the attestations, and so on and so forth. And there is strong separation also between the types of systems. The types of machines that the human approvers hold are very, very different from the types of machines that the servers hold. And there's a very different type of machine also for the offline environment, which is an extremely secure machine that it cannot be used for anything at all. How do we achieve flexibility and speed in this? We can deploy the system in multiple configurations. And this is also important for MiCA compliance, because we can put some of these entities in different countries and therefore ensure that without that country's approval, you won't be able to carry out an operation. So here are some configurations. You can have all of the entities, which is what I showed until now. You have an offline environment, human approvers, and MPC servers. But the number of human approvers and the number of MPC servers, the access structure, the location of those human approvers can all be very different depending on what you need. Do I need a custodial solution where everyone is in the US? Do I want someone in the UK from MiCA? Do I want human approvers at the customer for a non-custodial? All of those can be carried out within the same system. A second type of system is one without an offline environment, so you have MPC servers and human approvers only. It's the same flow exactly as beforehand, but you don't start with the offline environment sub-sharing. So the system works in the same way, but you suddenly now get very different properties. It's faster than above, but it still has the human approvers who can disconnect their machines to prevent the material being online. And you can have a system which is fully online or MPC servers only with very fast response time. This will still be much, much more secure than classic online systems because there's no single key sitting on any machine. Attestations are verified by all of the machines, and you can have strong separation between the MPC servers as well, but you'll get essentially the same response time in practice as a single server. Defense in depth, I mentioned. All devices and servers are heavily locked down. The approver shares are encrypted both with the secure enclave of the user device and also external UBHSMs. There's a zero trust approach to all devices in the system. We don't trust any machine. Everything is verified. Nothing is assumed to be okay, and that's a crucial design decision. There are many controls around the offline environment, who the approver operators are, how they can work, what machines they use, and much, much more. All of that is crucial to the security of the system, and I like to say that I think we have quite a good cryptography team at Coinbase, but we have an incredible security team at Coinbase with huge operational security experience, and of course their contribution to the system is very, very crucial as well. Thank you very much.
Thank you, Yehuda. Time for questions.
Very interesting talk. So I want to understand the human approver part better. Maybe I missed. Is it defined what's the last approver? If not, then how the MPC server know which is the last approver in a consistent manner?
So you can define who you want the last approver to be, and particularly if there are not numerous approver sets in the access structure, you can define that you want the last approver to come from a specific set. But even if that set has more than one approver in it, that's why we have the step of consensus amongst the MPC servers and the last approver to agree on who that's going to be. So if two approvers come and say, I'm the last approver, work with me, you only get one consensus because the MPC servers need to agree with each other and with that last approver.
Go for it.
Thanks for the talk, and apologies if I missed this. I was wondering which threshold signing protocol you're using and what the challenges were in terms of gathering things from the literature versus inventing new ideas in-house and things like that.
Yeah. So it really depends on different protocols of course, for different settings, if it's two-party or multi-party, but here it's almost all multi-party. So for Schnorr or EDDSA, it's my protocol. For ECDSA multi-party, we're currently using a protocol by myself, Ariel Noff, Iftach Heitner, and Samir Anlucci. But we're looking at moving to the latest protocol by Abi Shalat et al., which is 3 rounds. The challenge is, in general, for all deployment, we're very, very strict about verification. So we will verify ourselves. We will have an independent review within our team, another independent review within the security team at Coinbase, who works with the internally and external consultants, and external review as well beyond that. So everything that we take is very heavily reviewed. The fact that something has been published is not something that we say, okay, then it's secure.
Just a quick follow-up, is the first one with Noff, Ranolucci, and Heitner, is that public or
Yeah,
not
it is
yet?
public, of course, yes. Everything's published.
Thank you for the talk, very interesting. Quick question from my end is about the complexity of all of this. So that scares me, just how many moving parts there are and how many different sub-protocols and so on and so forth. And then implementing all of that correctly. What measures have you taken to ensure that it's implemented correctly and to, in general, reduce the risk stemming from that complexity?
Okay, so we have, in terms of the engineering team, we have a team that has been implementing and working with MPC and threshold cryptography for about a decade. Significant number of members of the team have been working on encryption and cryptography products for 20 to 30 years. So a lot of experience in that sense. The way that we work is that there's a theoretical protocol, theoretical paper. We write, our team, the cryptography research team writes a clear specification, and from that specification an implementation is carried out. We verify that independently verifying in our team that the specification matches the theoretical protocol and that the code matches the specification. BlockSec, which is part of the security team inside Coinbase, also verifies that the specification matches the theoretical. First, they verify the theoretical paper is correct. They verify that the specification matches the theoretical protocol, and also an independent team in Coinbase as well verifies that the code matches the specification. And then we go to an additional external audit beyond that to do that whole process again. So we're very, very rigorous. We're very, very careful. Is any code perfect? No, that's why there's defense in depth. I'm extremely happy to have security at my back to make sure that we're not relying on anything whatsoever, but we have, I think, the most rigorous process that I've seen in industry for implementing all of this.
Thank you. And are you able to share like rough TCP sizes or things like that? Like, what's the lines of code on this kind of thing?
I don't know. Do you know?
Okay.
I don't know. That I don't know. Sorry.
Thanks.
All right. The next session will be at 11 a.m., the DeFi session. Giulia Fanti will be chairing. Join me in thanking our speaker, and go network.
All right. Hello, everyone. Before we get started in the next topical session, I have a public service announcement to make about the lightning talk session that will take place after the upcoming session. The lightning talk session is a great opportunity for you to, if you're working on a company, you're working on a project, maybe you have a recent research result, or just work in progress that you would like to talk about. This is your opportunity. You get a 3-minute slot. Have your slides ready. Come up here and present, basically whatever you want, as long as it doesn't conflict with, general decency. And the way we're going to do this is we're going to run this in first come, first serve. So, during the next session, towards the end of the session, everybody who is interested, please line up here on the left-hand side, form a queue on the left-hand side of the room, have your slides ready on your laptop, and then we'll start the session. We'll go one by one. You'll come up here, plug in your laptop, and give your presentation. And if you do not respect the 3-minute time limit, I have a very noisy bell with which I will try to chase you off the stage at some point. So yeah, I think this will be fun. Even if you don't give a talk, come here and listen to the talks of other people. And yeah, I look forward to it.
All right, thank you, Joachim. And thank you all for joining. Our next session is on DeFi. So our first speaker in today's session is going to be Aviv Yesh, who's going to talk about suboptimality in DeFi. So Aviv, please join us.
I'm going to present a joint work with Maya Datan, Kai Wachin, Aviv Zohar, and Arthur Gervais. I'm Aviv Yesh. In this work, we explore the optimal and suboptimal use of 3 core decentralized finance primitives. The first is collateralized lending, so platforms such as Compound and AAV let people deposit funds and accrue interest, or borrow funds and pay interest. The second primitive is flash swaps. So I assume that people here know what swaps are and what flash loans are. Flash swaps are essentially the love child of these 2 primitives. They let people take out one asset, use it for the duration of a transaction, given that they would repay it plus maybe some fees by the end of the transaction. And the last primitive is flash swap-based liquidations. So some lending platforms allow people to liquidate unhealthy debt positions, and some liquidation tools, some liquidators use flash swaps for that purpose, so that people that do not have the upfront capital to liquidate a position could still perform liquidations. So for each one of these primitives, we cast its optimal one-shot execution as an optimization problem, which we then use to evaluate the suboptimality of users who use these primitives in practice. With respect to lenders, people who interact with lending pools, we show that in some cases they could have improved their profits by over 100%. With respect to arbitrageurs that use flash swaps to close arbitrage opportunities due to price discrepancies between exchanges, we show that a lower bound on their lost profits is $4 million, which is not a lot, but we use our data to uncover other surprising facts. For example, we present circumstantial evidence showing that some private transaction relays use the private order flow that's sent through them. So these are not the relays you know from PBS. These are services that let people send transactions in private to block builders, proposers, etc., without going through the public mempool. Some of these services don't ask for any compensation in return for their services. Also, some of them promise users that they would not use the information that they are exposed to in any form. Okay? This has caused some people in the community to ask themselves, well, these services are costly to operate. Why are these people operating these services, right? Like Ty Cobb fan here asked. So I know that Phil Diane is here somewhere. I don't know why I put your tweet, okay? No idea. Our evidence are for a different relay, okay? I'll explain everything in depth soon. So let's start with the first primitive, lending pools. To set their interest rates for both lenders and borrowers, lending pools such as Compound and Aave use a metric they call the utilization. It's a fraction which is defined as the amount of funds borrowed out over the amount of funds deposited in a pool. Okay? Interest rates are monotonically increasing in the utilization. And this gives us some nice properties. For example, when the utilization is close to 1, when most of our funds are borrowed out, these rate mechanisms would increase the interest rates. And intuitively, this incentivizes borrowers to repay their loans and also incentivizes new users to provide funds to the liquidity pool because the interest rates are high. And when the utilization is close to 0, it means that our money is just lying around and not making profits for us. We want people to take out loans and pay us interest. So it's good for us to set the interest rates to be low to incentivize people to take out loans. When taking the perspective of a liquidity provider, of a person that has some funds lying around and who may want to deposit them in a liquidity pool, we cast the decision of whether to deposit funds and if so, how much, as an optimization problem. And we show that counterintuitively, in some cases, users would not find it optimal to deposit all of their funds in a single pool. That is because by doing so, they actually lower their absolute profits. Okay? When taking the perspective of a user that already has some funds in the pool, this means that sometimes it's optimal to withdraw some of the funds because this causes the user to earn more profits on this lower amount of money. Okay? This is very important for everyone here to understand. You can earn more on smaller deposits. That's surprising, at least to me. So when we wrote this paper, we took a recent example. We saw that Aave's curve pool had 80% of its funds provided by a single user. That user could have withdrawn 28% of its funds to increase its profits by a factor of 7. Okay? Short-term profits, at least. This does not consider the impact of the withdrawal on other users. Okay? So it's reasonable to think that if a user withdraws a large amount of money, this increases the interest rates, probably causing other people to want to deposit their own funds into the pool, right? But when considering thinly traded assets, this logic does not hold because other people don't have enough funds to repay what was withdrawn. And about 1 month after we put this paper online, the very same user from Aave's curve pool have provided an example of why this works in the long run for thinly traded assets. So that user started employing a strategy similar to our own and succeeded in jacking up the interest rates and its absolute profits for over 1 week. Okay? Although our optimization problem is for a one-shot setting, it succeeded in increasing profits for a longer time. Great, so in the paper we have more results for lending pools. Let's continue with the second primitive, flash swaps. So exchanges like Uniswap and all of its derivatives let people swap one asset for another. Under the hood, they implement all swaps as flash swaps. Okay, so first users receive some asset, they can use it for the duration of a transaction, given that they repay the asset plus maybe some fees at the end. This is commonly used by arbitrageurs, people who seek profit opportunities that can be made by exploiting exchange rate discrepancies between exchanges. Specifically, it's commonly used because it allows users to not have the upfront capital which is needed to close these arbitrage opportunities. So when writing this paper, I actually just randomly sampled blocks and transactions, and I noticed a peculiar pattern of sequences of consecutive transactions which exploit roughly the same arbitrage. So for example, maybe they close arbitrage opportunity between Uniswap version 2 and version 3 between USDC and ETH, and the transaction immediately after it does the same, but between Uniswap version 3 and SushiSwap, and etc. for other transactions in the sequence. This shows that the first transaction in the sequence is actually suboptimal, because if all transactions use flash swaps, it means that no one needed any upfront capital to succeed. Meaning that the first transaction could have done whatever all the latter transactions did and earned their profits. So when applying this heuristic on the data for the 2 years before we wrote this paper, we estimate the amount of money left on the floor by arbitrageurs by at least $4 million. Okay. So this suboptimality is very reasonable, right? Arbitrageurs have a huge state space to traverse in a very short amount of time, in 12 seconds, right now in Ethereum. Obviously, they cannot fully traverse it. So that's one reason we give for suboptimality. Another is that arbitrageurs actually have an incentive not to fully exploit arbitrage opportunities, because if they would fully exploit them, they would increase the risk of their transactions not working when in an actual block. Okay, so they have an incentive to make their transactions slightly suboptimal, or maybe even very suboptimal, to increase their chances of succeeding on-chain. So given the data that we collected, we also uncover another surprising result. As I said at the beginning of the talk, some services let users submit transactions in private without going through the public mempool. They're called private transaction relays, and specifically Ethermine, the largest miner in Ethereum before the merge, operated one such relay. And they promised to never leak nor act on the information they receive via the relay. So we asked, is that so? In our data, we found that one specific arbitrageur only has transactions in blocks created by Ethermine. That arbitrageur started operating roughly the same time when Ethermine opened their relay, also closed at roughly the same time, and also had transactions that appear in suboptimal transaction sequences, specifically after transactions that do not seem to have appeared in the public mempool, okay, so private transactions. This is circumstantial evidence that Ethermine either operated this arbitrageur or maybe shared some of its private information with the arbitrageur. Great. So our last primitive is flash swap based liquidations. So as I said, some lending pools let users liquidate unhealthy debt positions, okay? This means that users repay some of the borrowed funds to receive some of the collateral, the corresponding collateral at a discount. For the same reason as I mentioned earlier for arbitrageurs, flash swaps come in handy here for liquidators that don't have the necessary upfront capital. We again cast the execution of this primitive as an optimization problem, and we also solve it giving a closed form solution. And using this solution, we show that in certain cases, liquidators would not find it optimal to fully liquidate unhealthy debt positions up to the allowed amount by the protocol. Okay? Instead, it's optimal to liquidate a smaller fraction than that. And the intuition behind this is that when using a flash swap for a large debt position, the size of the swap can impact the exchange rate between the collateral asset and the borrowed asset. And this impact can be so large that it causes the liquidation to be less profitable than if the liquidator would have liquidated a smaller amount of the debt. So just in case people are not fully familiar with the technicalities of liquidations, let's say that the exchange rate between ETH and USDC is 2,000 USDC for 1 ETH, and that we have a borrower that wants to take out a loan of 1 ETH. Lending pools commonly require borrowers to over-collateralize their loan. So let's say that the collateral required for this position is 2,400 USDC. Okay, this is a 20% over-collateralization. And let's say that now the exchange rate between these two assets has changed a little. Now, to buy 1 ETH, we need 22,000 USDC. Okay? This means that our borrower is not over-collateralized by 20% anymore, right? So what if some of the people who provided this 1 ETH want to cash out? We need to have enough money to allow them to cash out. To do that, lending pools let liquidators repay the debt, right, the 1 ETH, in exchange for the collateral. So for paying 1 ETH, our liquidator here would get 2,400 USDC, which represents a discount compared to the current exchange rate, right? So this is a bargain, supposedly. But if the liquidator does not have the necessary upfront capital, the 1 ETH, that liquidator would need to use either a flash loan or flash swap. So in that case, if the flash swap is performed against an exchange that uses a constant product automated market maker, for a large amount of USDC or whatever that liquidator requires, the exchange rate between USDC and ETH may be impacted along the lines I said earlier, right? Meaning that for very large positions, the impact may cause the profitability of the liquidator to go down. So it's better to perform a smaller swap to make sure this doesn't happen. So these are our main results. We have many other results in the paper. To conclude, we examine 3 core primitives. We show that some users use them suboptimally. To do so, we cast each as an optimization problem. And besides these results, we also raise a lot of interesting follow-up questions. Specifically, if users were to act optimally, they may harm the stability and health of the corresponding protocol. For example, if we look at liquidations, right, the optimal behavior may be to liquidate a small fraction of the unhealthy debt. Obviously, we would want users to fully liquidate unhealthy debt, at least up until the limit imposed by the protocol. So this means that the optimal behavior may harm the stability of the mechanism. So an immediate question is, can we design good protocols that actually incentivize the type of behavior we want to see? And actually, this is much harder than it seems, because sometimes when examining a protocol in isolation, it may seem good. But here, the difficulty arises when looking at the bigger picture, when examining not the specific protocol in isolation, but when thinking of how users actually use it, and the fact that they use it together with other protocols. This is what causes the bad outcome that maybe we can avoid with different mechanisms. So That's it. Do you have any questions?
Thank you so much, Aviv. Do we have any questions? Maybe I can start one while you're thinking. So you mentioned earlier that that arbitrageurs might be incentivized to not fully exploit arbitrage opportunities and instead only partially exploit them. Could you explain that a little bit more? Why is that the case? And do we have a sense for how strongly that effect holds?
So it really depends. You can think of a hard-coded arbitrage transaction that is optimal, right? Its success depends on its location in the block, right? Consider that perhaps a transaction would be put in an earlier position in the block such that the exchange rates between the assets that are exploited, whatever, changes, right? This would probably cause the arbitrage transaction to fail. So you have an incentive to kind of tone it down, not be fully optimal.
Okay, thank you. Please go ahead.
Hi, so when designing better mechanisms, I think like the main obstacle, in addition to the platform being isolated, this is also like an inherent blockchain problem of partial information, because the only information you have is up to the end of the previous block, right? So even if you have platforms that somehow collaborate and you have some global design, then it still wouldn't suffice because the state wouldn't be updated otherwise until the block ends, right?
So I didn't completely understand the question.
Like, okay, so you only, like, the state is updated when the previous block ends, and now you're updating the new state. And the platform now, even if it has access to non-local information from other platforms, still has only partial information with regards to transactions that occurred in this block that is being created right now, right? So even if you design some global, more global system cross-platform, that still wouldn't solve the inherent problem of relying only on partial information.
Yeah, definitely, that's true.
I don't have much experience with arbitrage, so I apologize if it's a stupid question. But you had an example in part 3 that mentions like someone used 120% of collateral to do that. So like, what's the rationale behind that? Like why would I put 120% of the worth of the collateral to do that? What was the rationale behind that?
So that was not an example of arbitrage. That was an example of a user that wanted to borrow some funds. Okay, this over-collateralization is required by the platform to protect against exchange rate shocks. Right? We want to have an equivalent amount of the borrowed funds stored with us to pay whatever, to pay our lenders. And the rationale for people to take such, like to borrow from collateralized lending pools is, for example, it's an equivalent of doing a short, right? You take one asset, you pay with another. If the collateral asset drops in value, then you made money,
Okay.
right?
I see. Thanks.
If there are no other questions, let's please thank Aviv. Right, so our next speaker is Theo Diamandis from MIT. Is he in the audience? Oh no, that's not Theo. Okay, All right. Do we have a speaker for the next talk? All right. Time to start telling jokes. Why don't we do this? Oh, wait. Joachim, should we start the lightning talk session, or do you want to just pause for 30 minutes until the lightning talk session? Where's Joachim? Okay, everyone's gone. Okay, I think we should probably wait to start the lightning talk session at the scheduled time so that people who are planning to come in at that time don't get tripped up by the time change. So apologies for this disruption. I'm gonna try to contact the authors real quick. And in the meantime, we'll just take a break for now until the lightning talks. So thank you. Okay, welcome Theo. Please take it away.
I was in the room. Where's the All right, well, I guess we spent too much time in the backstage room. So anyway, hi everyone, my name's Theo. I am a PhD student, well, I guess for the next few weeks at MIT and a research partner at Bain Capital's Crypto Fund. This is work on multidimensional fees. So how do you do essentially congestion pricing for non-fungible resources that are contested in some way, and joint work with Guillermo, Alex, Tarun, and CMAC. So one thing that I hope to convince you of is that fee markets with fixed relative prices are inefficient. And this talk is a framework to optimally set multidimensional fees for congestion control. So let's give kind of a very brief example of why are transactions so expensive. Let's consider like a very simple example where we have a mempool and say we have a bunch of transactions and we have kind of two types of resources. So maybe compute and bandwidth. You could also think of maybe the first set of transactions, the blue ones, looks at like one account, so it accesses one particular smart contract, say in like kind of a Solana type VM, and the other accesses another. And these two things are orthogonal. And let's say, the blue transactions are more valuable to the users, so they have a utility of 4, whereas the bandwidth transactions, the orange transactions, are less valuable. Well, if we have a 1D gas market and say the gas cost is 3, what would we do? We would fill up the CPU transactions, but we would actually not really use the bandwidth that we could of the validators. However, if we have a 2D gas market and say we were able to price CPU still at 3, but we were able to price bandwidth less at like 1, we would end up filling up this block. And when I say filling up the block, this isn't necessarily in the block space context. This is more of like filling up the ability for the validators to actually execute these transactions. And this very simple stylized example illustrates why orthogonal resources should be priced separately. So what do I actually mean when I say a resource? Well, a resource is really anything that could be metered. So this could be something like blobs. It could be compute, memory, and storage. We could even go down to the level of individual opcodes. In fact, we could even say sequences of opcodes. So for instance, if you hit a storage slot and then you hit that storage slot again, maybe that's less expensive than hitting the storage slot and then hitting a different storage slot. We could also say compute on a specific core. We could say things like each account and an account-based model is an individual resource, and so on. So this is a very general framework that as long as I can say how much of something I used, I can call that a resource. So we're going to formalize this. A transaction J is going to consume a vector of resources, AJ, and we're going to say there's M different resources. So that means the ith entry of this vector is going to say how much of resource I is consumed by transaction J. Then a vector X is going to record which of n possible transactions are included in the block. So just simply xj is 1 if transaction J is included, and it's 0 otherwise. We can then write the quantity of resources consumed by a block. And when I say block, I mean just some unit of kind of time as this vector y, which is just going to be the sum of each of the vectors of resource consumption times this 0, 1 variable that says whether it's included or not. And we can write this simply as this matrix A, where the columns correspond to the transactions, times the vector x. So then we know most systems constrain and charge for each resource that's used. So as an example, we might define a resource consumption target that we'll call B star. And so the deviation from that target is just AX, which is the quantity of resources used by the last block, minus B star, which is our target. So in kind of the 1D gas market on Ethereum, this is going to be 15 million gas as an example. So this is in like 1559. We also might have resource consumption limits. So this says like there's some maximum size for a particular block. And that means that no block can have resource consumption, AX, that is greater than B, where B is the limit. And so finally, for each of these things, we want to charge for the amount of resources that's used. So we'll define a price vector P, and P is going to be an M vector that just says what the price is for each particular resource. So that means for a particular transaction, we can write the cost of said transaction as just P transpose times AJ. So how do we determine these prices? Well, there's a few properties that are like pretty obvious that we want. Let's say if we're consuming, if the last block had resource consumption exactly equal to the target, that probably means we set the price well. So we don't want to actually change that price. On the other hand, if we're over target, so if we're consuming too much of that resource, the network probably wants to increase the price. It means it's undercharging in some sense. And vice versa. If the consumption is under that target, then we probably want to decrease that price. So one proposal that's been given for like a multi-dimensional fee market, kind of multi-dimensional version of 4844, is this exponential rule. And if you check, you can kind of go through this, and it does satisfy all these properties. But there are actually many other rules that satisfy all these properties as well. And that begs the question, is this a good update rule? And what does good even mean in this sense? So it satisfies these properties, but what other properties might we want? What type of dynamic behavior do we want? And in the rest of this talk, we're going to see that update rules are implicitly solving an optimization problem. And so a specific choice of an objective function by the network designer is going to give a specific update rule. So instead of actually focusing on what the update rule itself should be, we're going to instead focus on what optimization problem we want to solve, and then use that to back into a specific update rule. Okay, so let's look at the resource allocation problem, which is this optimization problem. The setting for now is we're going to have an omniscient network designer who's going to be able to pack the blocks themselves. Of course, this is stylized, but we'll see that if you set prices correctly, then in effect, we're doing this in a decentralized way. So the first ingredient we need is some type of loss function. So this says, given a particular resource usage of like the last block, how unhappy am I with it? And just as a few very simple examples, we might say if we're exactly on target, we're not unhappy at all, so we incur 0 loss. However, if we're deviate from target at all, we're infinitely unhappy. On the other hand, we might say we actually don't care if we're under target, but we only care if we're above target. So if we're under target, we incur 0 loss, but if we're above target, then we're quite unhappy. The next ingredient we need is to encode all transaction constraints in the set S. So the set S is just going to say these are the types of allowable transactions we have. And this will include everything like network constraints, but it also can include very complicated interactions among the transactions. So for example, if you have some like DEX arbitrage opportunity that's at the top of the block that only one person can actually realize, that would be included in the set S as well. The final thing is we need some notion of utility that's obtained from each included transaction. So here I'm going to clump essentially everybody that interacts with the blockchain into one group, and then the blockchain itself or the network into another group. So when I say transaction producers, I mean users, validators, block builders, kind of all of this. So payments between this group, I'm not going to worry about, and I'm only going to worry about the net utility from kind of getting a particular transaction on chain. And if transaction J is included, I'm just going to say then this group gets a joint utility QJ. And of course, we almost never know this in practice, but we'll see that we actually don't need to know this as the network. So the resource allocation problem with all these ingredients is then just to maximize the utility of included transactions minus the loss that's incurred by the network, subject to the resource usage of the network is given by that of the included transactions, and the set of included transactions is allowable. So it satisfies kind of all the constraints that we have. And of course, this set S might be very complicated, but we're going to see we're able to actually outsource that, outsource the kind of complexity of that to the block builders. So as I mentioned earlier, the network designer doesn't actually solve this in practice at all. The network designer doesn't decide which transactions are in the block. The network designer doesn't know the utilities. And because of this, we're going to then lean on duality theory to set prices so that this problem is solved optimally on average and prove that this is indeed the case. So just to give a very brief outline of what duality theory is, it's kind of this deep theory in convex optimization that says essentially if we relax the constraints to penalties and we set the penalties correctly, then we solve the original problem if we set those penalty prices correctly. And one key observation here is the network designer really only cares about the utilization, Y, so the resource utilization, based on the transactions. But they don't actually care about the transactions, or they only care about the transactions insofar as it affects the utilization. Similarly, people that are building blocks don't actually care about the resource utilization of the network, except insofar as it tells them which transactions are actually allowed to be put in. So we're going to decouple the utilization of the network and that of the transaction producers. And as I said, if we correctly set the penalty, which is going to be the prices, then the dual problem is going to be equal to the original problem, and the utilizations are going to be equal. So the dual problem is, instead of that maximization problem that we saw earlier, it's going to be a minimization problem of this particular thing called a dual function given by g of p. From before, the prices p are essentially the penalty for violating that constraint, which are exactly the prices that we're going to want to charge for each resource. So this is kind of looks very complicated at first, but this is the form of the dual function. The first term is actually something that's quite easy, and we know this in closed form for many loss functions. So I would just think of that first term as something that's easy to evaluate. This can be done on chain. This could be done as part of consensus. Typically, it's a closed form solution. This is just the general case where we don't necessarily know what the loss function L is. The second term is actually a little bit more complicated. So let's look at it for a second. Well, the second term is saying choose the transactions choose the transactions X that are in S that maximize the net utility. So the utility minus the prices that are paid for including that transaction, subject to those constraints given by S. And this is actually the exact problem solved by block producers in determining what kind of transactions are actually included on chain. So what does this mean? The network doesn't have to solve this problem. The network can actually observe the optimal solution to this problem by just looking at what was included in the previous block. So what do we get at optimality? So let's assume for a second that we set prices correctly. So we set prices correctly. We give these prices to block producers. They tell us what transactions to include. At optimality, the supply, which is essentially how much of each resource the network is willing to give at a particular price, is exactly equal to the demand. So if we set prices correctly, essentially the gradient of that dual function, which is y star, which is the solution to kind of that first subproblem, minus a times x star, which is the resource consumption of the included transactions, is equal to 0. And just taking this one step further, if we're kind of plug things in, what this means is that the optimal prices charge the transaction producers, so the people including transactions on the blockchain, exactly the marginal costs faced by the network. And these prices are those that incentivize transaction producers to include transactions that maximize the welfare generated, which is that utility term, so essentially the utility of the included transactions minus the loss incurred by the network. So that's great, but this assumes that we set the prices correctly. So the question is, well, how do we find those prices that minimize the dual function? And we can compute the gradient of this. So y star is that kind of easy term that we can compute on chain. A times x star here is just going to be the resource consumption of the transactions that were actually included in the previous block. And this means that we can essentially, determine y star, observe x star, and then apply our favorite first order optimization technique. So for example, we can apply gradient descent. And we can kind of do this as for each block. So the question is like, well, does this work? Does this give us what I want? Or does this give us what we want? Because now we've kind of switched from this offline problem. I was like, this is a single block problem. But in reality, these systems are dynamic. So the transactions that are submitted are going to differ for each block, and so on. So what types of guarantees can we get in this scenario? And just to outline kind of what we have is we have this game that's being played essentially between the network and those that are submitting transactions. So at a particular block, which we'll index by t, first the network is going to publish some prices. So it's going to say, okay, the prices for this block are going to be pt. After it publishes the prices, then the users are going to submit the transactions. So these transactions have some utility and have some resource consumption. This might be adversarial. We're not going to make any assumptions on what transactions are actually submitted. Then the network is going to receive a payoff. So after these transactions are submitted, the network receives essentially some loss, which is given by that dual function. And the question is this a good thing to do? Like, is this something that makes sense? And to do that, we're going to use this metric called regret, which comes from the online learning literature. And so what this essentially says is compare these two scenarios. In the first scenario, I'm running this gradient descent type algorithm. So essentially the algorithm that I gave you a few slides ago, that's dynamic. So you can think of this as like a 4844, 1559 like mechanism. In the second scenario, I actually have an oracle that tells me all the transactions that are submitted in the future. So in some sense, like I'm omniscient. But I have to actually, instead of being able to change the price, I have to choose the best fixed price, knowing all those transactions in the future. For anybody that's done machine learning, you can think of this as like an online learning setting where the data is streaming in, and I kind of adjust my weights as the data is streaming in and make predictions, versus this case that's like a supervised learning problem where I have all the data in advance and I have to choose one set of weights. And of course, we never know P star in practice, but this seems like a reasonable baseline. This online dynamic approach versus this offline static approach where we actually know the entire future. So the main result, and why we say that these types of fee mechanisms are optimal, is that assuming we use gradient descent with kind of a particular step size that's chosen well, we get this bound on regret. So we essentially get that regret is O of 1 over the square root of t, which means that this goes to 0 as t, which is, you can think of kind of as like an epoch, gets large. Very importantly, this result doesn't actually require any notion of like stochastic demand, any notion of playing to an equilibrium. There's no assumption on what the transactions that are going to be submitted are, except for the fact that they are valid, so they pass consensus. This means that these can be entirely adversarial, and I think in blockchain settings, like having these adversarial bounds are quite important. And these results essentially follow directly from online convex optimization, which I do think shines in this setting. As an interesting aside, this actually doesn't require that we ever converge to any prices. So it doesn't require that we converge to the optimal, and we still get this bound, which is quite cool. So again, when I say optimality, this scheme is optimal in the sense that it's 0 regret on average. And another point is there actually exists a stochastic adversary that does match this bound. So you can have an adversary that does cause you to hit this bound, so you can't hope to do better without additional assumptions. However, if you do have additional assumptions, like for instance, demand or transactions are drawn from some distribution, you will get all the nice things of like this converging to a clearing price and so on. Another thing is a lot of these online convex optimization results are stronger than the traditional game theoretic results in that they don't require things like playing to an equilibrium. They don't require a rational adversary. They only require an adversary to be bounded in a certain sense, and this could be either a bounded budget or typically in these systems we have some max block size. So just to go through simple examples and kind of go all the way from the loss function to what an update rule would look like, if we take this kind of silly loss function, this zero infinity loss function we saw earlier, we get this update rule that looks like pretty vanilla gradient descent. So we update the prices based on a term that looks like the residual. So B star, remember, is the target, and A times X star is the resource utilization of the last block. If we look instead at this loss function, but actually with mirror descent, so mirror descent adds an additional kind of regularization that tells us what we want the dynamics of gradient descent to look like. We actually recover exactly the 4844 update rule. And unfortunately, I don't have time to get into this, but I will refer you to the paper and happy to answer questions on this. And let's look at the other loss function that we looked at earlier. So this loss function says we actually don't care if we're underutilizing the network. We only care if we're overutilizing it. And here we get the same as we have up top, but with the differences, we don't allow negative prices. So up top, where we actually care if we're underutilizing the network, we might have negative prices, which you can think of like a subsidy. Whereas in the bottom, this loss function says we don't care if we're underutilizing things, so there's no reason that we would ever give a subsidy for someone to use a particular resource. And just to kind of wrap up, I hope I convinced you that really when designing these fee mechanisms, you should choose your objective function and the update rule, so kind of the algorithm that you're using, instead of trying to choose the price rule directly. And if you choose this objective function using this framework, you'll get kind of an optimal price update rule that has those strong adversarial guarantees. Of course, there's no difference between kind of correctly choosing these prices with an oracle that tells you what the future is, and then using these online gradient algorithms, and that's what we mean when we say they're optimal, that these things are zero regret as the time window gets large, and these results hold without kind of any assumptions on, distributions of demand or stochasticity or so on. So all these things are adversarial bounds. There's a lot of I think this area is really interesting. There are a lot of other fee mechanisms that might kind of benefit from this type of online optimization approach. Some big questions here are like, what should these resources actually be? I imagine this depends a lot on what type of blockchain system or rollup you have. So in an account-based model, you might want to price things per account. In other models, you might want to separate things like compute, memory, and storage, and so on. There's a few teams like Avalanche and Penumbra in particular that have been implementing these. And so, kind of these things going into real-world systems might give some insights as to how to think about this question. In addition, I gave you some update rules using gradient descent. I also gave you one using mirror descent, which gave us 4844. There's a question of what update rules are the most useful, and how do we trade off things like convergence behavior, complexity, and kind of the dynamics that we actually want for these, which might lead to different user experiences. And as I mentioned, this might be relevant for many similar fee type mechanisms. So while I'm talking about fee mechanisms on like an L1 or L2, you can imagine there's a lot of protocols where you have some resources and you want to do congestion control, and you can use fees to set or you can use this framework to set fees appropriately towards that objective. Anyway, for more info, check out this paper or feel free to reach out. Thank you.
Thank you, Theo. Thanks for the nice talk. Do we have any questions? Do you mind going to the microphone, please?
Hello. Awesome. Thank you for the talk, by the way. Just a quick question I had was, well, two-sided in that, is the loss function different for both, for like the dual problem for proposers, block builders and the kind of the omniscient network designer? And then with proposals to kind of decentralize the proposer process such that MEV or other adversarial forms of value extraction are decentralized, does the loss function become more optimal in the sense that the bounds are achieved in a much stronger, easier sense?
Yeah, great question. So for the first, I would say so the loss function that's in kind of the original problem, which is this problem that we want to solve, is what shows up in the dual. So it's not, you're getting kind of a different form in the dual, but the dual mechanically is derived from the original problem. So there's no, I guess, room for choices when deriving the dual problem. You're essentially applying this mechanical method that spits this out from the original problem. And then for the second question, we kind of play a sleight of hand here where we're actually not, so most of what goes on between, say, like the users, searchers, block builders, and validators, we group all of that together. So for example, if like I'm a searcher and I have an MEV opportunity, I might pay some block builder a large amount of money to include that, and then that ends up going to the validator. And for our utility, we essentially just net out those payments. So we're looking at everybody that interacts with the network and then the network itself. And so there's a ton of research questions as to like, how do you get people to, right, we have this block building problem, and in this block building problem, we're saying like, we're assuming that people kind of submit the highest net utility transactions, but what is that actual utility? I don't know. How does it net out between these players? I don't know. How do you do this so it's like, you know, make these incentive compatible between those players? There's a lot of people that have done a lot, you know, of interesting work on that. What I'm talking about here is like once you kind of have people, like the final person that's submitting the transaction to the network, how do you kind of do congestion control? So I'd think of this more as like an inclusion, talking about inclusion rather than ordering.
Awesome, okay. Thank you so much.
Yep.
Anyone else? Okay, I also had a question actually. That's kind of related. So in the resource costs, you modeled it as being linear, like A times X, right? Yes. Is it possible that the order of inclusion in a block would affect like how much resource gets used? And like, is there a possibility to extend this to nonlinear models? Oh yeah, definitely.
So actually, what you'd end up doing with that, let's go back, but the idea is essentially you duplicate the transaction. So let's say like you have a transaction and if it's the first in the block, it's the first thing to hit a particular slot. So that kind of, you know, storage read is more expensive, whereas if it's the second to nth thing in the block, it's less expensive to do that S read. And what you'd end up doing is you'd actually put two transactions in. So you'd have one transaction that has the resource that's like the first read, the other transaction that has a resource that's the second read. And in the set S of allowable transactions, you'd have a disjunctive constraint that says only the first one or the second one is in. And so that nonlinearity you'd basically do by duplicating it. And the reason this doesn't require like a blow up in complexity is the AX term is just, you only need to care about what was actually included. So in some sense, any transaction where X is 0, when you're computing like, you know, Y is equal to A times X, you just throw out and you totally ignore. Does that answer the question? It's a nice modeling trick.
Can you speak a bit more about the Avalanche and Penumbra implementations of this and what you found value there?
And sorry, what?
What you found is valuable or interesting in that implementation?
Yeah, I would encourage you to talk to the teams, which I think are both, there are folks from both teams around here. But I think it's like, one thing, like I said, kind of the selection of resources matters quite a bit. And so like one thing that's kind of interesting is Penumbra, for instance, does a lot of client-side proving. So they separate out kind of bandwidth cost into what's actually like people that are running the validators have to do and what the client-side proving has to do. Let me just... So I think it's like this kind of resource selection of like how, when I say like orthogonal resources should be priced separately, nothing is truly like 100% orthogonal for the most part. And so how do you actually choose these things? And I think that's kind of one of the things that for both like Avalanche went also towards, I don't remember, I think they used 5 resources, but it was kind of like bandwidth, compute, memory, and so on. So similar to kind of the example that I had. And then there's also a lot of kind of questions of, you know, implementation details that interact with this framework that I think are valuable to when rubber meets the road in some sense. So I think that resource selection, and then also like, for instance, do you have caps on how, or do you have things like different resources might be priced where, say, the gradient step could be faster or slower. So perhaps for some resources, you can have like huge bursty spikes, and so you actually are fine raising the price slowly, but for other resources, if you have a burst, that can't be sustained, so you actually want to push the price up quite a bit faster. And then the ability to actually like see this in practice and then on a test net, I think is super valuable for figuring out like what types of algorithms you should actually design. Then the other thing that I think is interesting on the implementation side is so Avalanche and Penumbra went more for kind of this like bucketing, I would say like bucketing the opcodes and saying like these opcodes correspond to these types of things. I'm butchering this, but for the sake of kind of stylized, like, you know, these types of actions consume compute, and these types of actions consume bandwidth, and so on. Another place where you could apply this framework as well is saying, okay, I want to price each account separately. So saying like a Solana model, where you might instead say like each actually account or each piece of state has its own controller. And so I want to make things like, say, if there's a big meme coin craze, and people are spamming the network with those types of transactions, I want to raise the price on accessing those dexes, but I don't actually want it to be influenced by, say, other things that are using like compute. I want, say, like certain transfers to still be super cheap or accessing other applications to be really cheap. So that's another thing that, as far as I know, isn't implemented by anybody yet, but it's been talked about. And I think that's also like a super interesting path to see kind of, that wasn't the original thought when we did this research, but kind of everything applies one-to-one.
Thank you so much, Theo. Let's please thank the speaker. So next we have the lightning talk session. So Joachim, if you want to come up and give people instructions.
All right, hello everyone. Let's get ready for the lightning talk session. So we do this first come, first serve. If you would like to speak, please line up here on the left-hand side so that we don't block any of the exits. The rules are fairly simple. You get the mic for 3 minutes. Bring your slides if you want. If you don't have any slides, that's also fine. There's a USB-C and HDMI here. That should work. I'll be sitting down and enjoying the talks with a timer. If the timer of 3 minutes expires, I'll give you like a sign like this. It's time to wrap up. If you don't wrap up, I'll have this very obnoxious device to enforce the timeline. And yeah, I think that's it. Let's get started with Siamak.
Thank you, Joachim. So I just want to take a couple of moments here. Is this working? To just make an announcement. It's great to have SBC here in New York City this year. I think that's kind of an acknowledgement that New York has really become a central locus for blockchain activity, both in academia and in practice. And so given that, I want to invite everyone here back to New York City and to Columbia in December, when we'll be hosting the 3rd annual Columbia Crypto Economics Workshop. Our goal in organizing this for the past 2 years has been to try to be the premier event, bringing together academics and practitioners to discuss issues related to economic incentives and blockchain. So here we're thinking of topics like transaction fee mechanisms, MEV, restaking, roll-up economics, and so forth. It's an event that's co-organized between members of the Robust Incentives Group at the Ethereum Foundation, myself at Columbia Business School, and my colleague Tim Ruffgarden in the School of Engineering. And given that we really try to have, like SBC, kind of both the top researchers in academia and in industry, and try to carefully curate that. And so, you know, we're going to have more information about the event coming in the upcoming months. But for now, just remember the dates, December 4th and December 5th. There's an URL there where you can see what we did last year and where we will also post new information. And we hope to see you in December. Thank you.
So speaking of events, okay, there. Okay. If you'll be, well, try again. Sure. What? Sure thing. Here we go. What? It's and there's it's not working. It's always a fun thing at conferences, a room of smartest people ever. The slideshow never works, nothing ever works. But we can do this. I trust in us. Anybody on the technical team? Mirror display. Let's try it here. Yes.
You don't have a dongle, right? You don't have a thing?
It's doing something?
It is doing something. Windows. You don't have your file, right?
What?
You have the file?
I can send you a link for this.
It's going to take forever.
A link?
Yeah. You want to send?
It's just, oh.
Put the next question. Put the next question.
Okay, yeah.
Hey everybody, my name is Vanashri. I have a couple of research questions, the solutions to which I think will be helpful for the ZK industry in general. One question is around trusted setups. Currently what is happening is that different projects with different proof systems need to do their own trusted setups, which is operationally expensive and time-consuming, in general resource-consuming. The question is, is it possible to do one single truly universal trusted setup that different projects across the industry using different proof systems can utilize? And here is a starting point to think through a solution. I think the reason why different trusted setups are needed is because the way we have on-chain verification is by having one hop away from the proof system by using Groth16. And the Groth16 prover proves computation of the verifier, which of course is variable because you're working with different proof systems. Instead, how about the following direction? If you put something like a flonk in between, so you start with your proof system, then prove its verification using flonk, and then you go to Groth16. Here, this is a starting point. This still does not work. Why this is a starting point is because you want to, the goal is, I think, a solution for this, the goal is to find an endpoint of proof system where the prover only does some generic computations, and the only variant has to be the size. And you can do that by, I think, a few hops. I think one hop. It's okay, I'll talk through it. one hop doesn't work because here, the verifier of flonk also, it seems that it is it's dependent on the computation that its prover does, so it still does not work. I think, and the idea could be that goes so succinct that the prover of the final proof system can do everything in just addition and multiplication, and then it's just the size. Okay, I think my time is up. There's one more nice problem, but if anyone is interested in collaborating, please come talk to me. And by the way, one last sentence, we are building FIRMA, a universal proof generation layer. Thank you. Come talk to me if you're in ZK space, please. Thanks.
All right, let's see if this works with my laptop. No mechanism of predicting these things in advance. Okay, well, that's a good sign. And it's gone. Yeah, I just would like it to not mirror if at all possible, but this seems too hard to figure out right now. Anyway, I'm Isaac. I work for Heliax on Anoma. I'm a scientist, and I want to talk about technologies for cross-chain atomic commits. So these will eventually make their way into the Typhon project, which is for building Anoma native chains within the Anoma software ecosystem. So I want to start with the train and hotel problem. So this is the problem where I want to book a train, presumably on one chain, and a hotel, presumably on another chain, and I don't want to book neither. So I want these to be booked atomically. A traditional way to do this would be with a multi-phase commit. So we start out by locking resources on each chain. Until they're both locked, there's some interchain communication, and then we do an unlock phase where we commit or abort. There are three problems with this. One of the problems is liveness. If we lock our resources on one chain and the other chain dies, then we're just screwed. We've somehow set the liveness of all the resources to the worst of all the chains involved. Another is that it takes multiple rounds. Anything that does this requires at least 2 commitments, at least 1 round of interchain communication. There's a certain inherent slowness. And finally, there's a kind of free option. Whichever chain communicates last has the ability to decide exactly when this transaction happens, which might be valuable, and that in turn might be a problem. We don't want to incentivize chains to delay stuff. So ideally, the thing that these chains are doing, I mean, they're already running consensus. They're already doing atomic groups of transactions called blocks. What we're trying to simulate fundamentally is putting one block on 2 chains, one group of transactions atomically committed to both. So let's try and make the easy case easy. This is based on a consensus algorithm I published in 2020 called heterogeneous Paxos. And the easy case is derived from looking at the actual quorums that do the consensus of these chains. I'm assuming we're doing something with finality. So let's say the quorums for red chain look like this. Obviously, they would have to intersect. The quorums for blue chain look like this. And the easy case is when all the quorums of one chain intersect all the quorums of the other. A decision made by red will have to be respected by a decision made by blue as long as each of those red-blue quorum intersections contains an honest validator. And this may sound like an unusual case, but it's actually not that uncommon. Proof-of-stake chains tend to have a fairly large amount of validator overlap, in part because they're just professional validators who make a business out of doing this, and they do it for a lot of chains. So it turns out that there actually are cases when it's possible to have, for example, a red-blue commitment and a blue-green commitment, but there isn't enough overlap to do a red-green commitment. So our proposed answer to this scenario are what we call chimera chains. It's a chain for each possible heterogeneous consensus, and they are sort of a separate place for doing these red-blue transactions. I don't have time to go into a lot of details about how the programming model for these works, but it does require explicit support from the base chains, and we hope to integrate that into future Anoma chains. Thank you.
Okay, attempt number 2, we have the slides. It must be easier. Okay, so we're going back a bit to event things. I'm Clara Schickelman. I'm with Chain Code Labs. We're a nonprofit here in Midtown Manhattan focused on Bitcoin research. And we have a bunch of cool things coming up in November. So the Bitcoin Research Day, it's going to be the 2nd edition of the previous event. It was really good. It's going to be even better this year. Some of the speakers are present. Go to the website, see it. We're going to get core developers, engineers, academics talking to each other, doing some very cool stuff. Some of the other cool things that are going to happen at the Bitcoin Research event is that we're going to hand out the Bitcoin Research Prize. We're still accepting nominations until the end of the month. The paper has to be in a peer-reviewed journal or conference and so on. It needs to be published recently, where this is the line, and it has to be somewhat relevant to Bitcoin and the Lightning Network. It doesn't need to be a Bitcoin paper, but it has to do something with the space, like no molecular biology or whatnot, but anything that is related. Please nominate your papers and send them off, and then it will be handed at the event. And another event that we're holding, it's called the Bitcoin Research Week. It's a small workshop. It's an invite only. If you think you should be there and we haven't contacted you, talk to us, drop us an email. So I hope to see you on November 22nd at the Bitcoin Research Day. I'm looking forward to seeing your papers nominated for the prize. We have an amazing committee that will go over it and choose the best one. Yeah, and talk to us. Thank you so much.
Hello, everyone. I'm Taro. I'm a PhD student from Carnegie Mellon University, and I'm excited to talk about our new research on a new type of denial of service attack that tries to exploit latency optimization in the Ethereum peer-to-peer network. So at this stage, we all know that latency matters in the blockchain peer-to-peer network. When the node receives transaction from the user, it will first validate the transaction and propagate it to the rest of the network. For the actors like MV bots and block builders who want to execute sandwich attacks or arbitrary transactions, they have the incentives to hear transactions faster than anyone else in the network to build a block or transaction bundles as quickly as possible. So oftentimes, they connect to the node from the centralized services that are known to be faster than the others. And in general, there are many ways to reduce latency. For example, you can deploy many nodes on a different location or maintain large connections to other nodes in the network. But the last thing you can exploit here is to skip the validation stage and by modifying the client and let the transaction go through without any checks. And indeed, we observe this behavior in the wild. So I'm not talking about like theoretical scenarios. However, because the node doesn't check the validity of the transaction, it will accept many invalid transactions to the network, which are supposed to be filtered out at the validation stage. So we as a researcher are interested in the security implication of this node modification, and we came up with a new type of denial of service attack where the attacker sends invalid transactions to this particular node, and it will incorrectly propagate to the rest of the network so that the original attack traffic gets amplified by 1,000 times. And on the one hand, we also try to quantify the economic benefits or economic values that you can generate from skipping the validation by reducing the latency so that we can ultimately answer the question on whether the risks associated with this attack actually outweigh the latency benefits. So we made this paper public a couple of days ago, so if you are interested in the answers to those questions, please scan this QR code and check this out. Thank you so much.
Awesome. Hi everyone, my name is Mo Walji. I'm the founder of Derek.io. We're building a SocialFi platform for professionals, primarily starting with a job board. The idea is that we want to combine fragmented areas of identity across different areas of different chains into one place and allow that to have hiring managers to make informed decisions about as people are applying for a role. At the beginning, it's starting off as a job board. Allows, if you go in from a employer perspective, you should be able to get candidate information such as scoring on DeFi, NFT, DEX, and multi-chain usage. It shows how active you are currently. Aggregates things in one place, even things like DGen score, alongside with all your educational and experience in one place. We want to be able to give hiring managers the option to kind of look further in depth if they are looking for more crypto native people. And then further down the line, we're actually going to be opening up a reputational system and attestations, which allow people to start vouching reputation and kind of staking that towards recommending people for further things. If you do want to get in touch, or if you're looking for a job in the meantime, please check us out. Please take a picture of the slide. If you want to get in touch, that's my Telegram at the bottom at Incatera, or just simply give us a follow on Twitter at WeAreDerek. Thank you very much.
Perfect. So hi all, I'm Burak. This is our paper with Danning from Flashbots and Thomas Thierry from Ethereum Foundation. This is titled Who Wins Ethereum Block Building Auctions and Why? And as the title indicates, we want to understand how the successful block builders, the dominant builders today, win the auction, and also how they make profits, because as you can see in this chart, which shows profitability and the sizes indicate this market share of the builders, the size does not necessarily grow with profits. There are some builders who are not, who doesn't have that much market share but extremely profitable. So we want to understand, okay, how do they make profits and how do they win the auction? And we want to then get insights so that we can design better auctions in the future, which potentially preserves Ethereum censorship resistance properties. And our results show that the order flow diversity of the builders are positively correlated with their market share. This potentially is because if you have order flow coming from different providers, then you can be competitive in more auctions, whereas as you are dependent on a single provider, then potentially you are only competitive in less often auctions. We also show that builders who have potentially integrated searchers or exclusive order flow deals with providers are more profitable in general. The intuition here is that if you get order flow which the other builders don't really have access to, and this is strictly don't have access to, then you can keep profits while winning the auction, whereas builders who don't have such order flow, who are maybe dependent on common order flow, they can still win, but they have to subsidize. And then finally, we find a bunch of different features which are correlated with both earning profits, but also earning market share. And we actually converge to this chicken and egg problem that was also highlighted in previous works. That is, builders cannot profit from their blocks if they don't have distinguished order flow providers. But to get such providers, they need to have high market shares. And you can find the archive link or the paper archive version on this QR code, and the paper will be featured in AFT. And you can also just type in Vitalik got surprised by this chart on Google, and I think you will find the paper again. And that's going to be all. Thank you.
Hi, everyone. My name is Xunqi. I'm a fourth-year PhD student at The Ohio State University. And I have a talk at 3 p.m. today. For now, I would like to introduce you Honeybee, decentralized peer sampling with verifiable random walks for blockchain data sharding. This paper was done by me and my PhD advisor, Professor Shalish Bojavan at Ohio State University. In a P2P network, nodes would like to sample other nodes randomly. And why would we care about this node sampling? There are a bunch of applications that need random node sampling. This include node discovery, data availability, and data sharding. You can consider data sharding part of data availability sampling. And also Byzantine tolerance and overlay construction. Basically, you cannot have a blockchain without these things. Therefore, it's safe to conclude that random node sampling is a very important part of network layer of blockchains. And now we introduce our work, Honeybee. Honeybee is the first effort to conduct P2P random node sampling with Byzantine-tolerant verification techniques for blockchains. And we use novel verifiable random walks and table consistency checks technology. And Honeybee is completely decentralized and robust against various attacks. From the evaluation perspective, Honeybee's node sampling quality is 4 to 63% better compared to state-of-the-art baseline algorithms. And most importantly, the Honeybee protocol is not only applicable to blockchains, it is also applicable to P2P node discovery and neighbor selection in general. As we already mentioned, in a P2P network, we want to sample nodes randomly from the entire network. How do we do that? We do that with random walks. And you probably want to ask, what if malicious node reroute your random walks? That's why we have verifiable random walk. In verifiable random walk, a node uses time-sensitive pseudo-random numbers to make sure that you are doing a genuine random walk. And you probably also want to ask, what if malicious node lie about their routing tables? And we already prevented malicious node from reroute your random walk. If we believe there are lies about their routing tables, you can actually do a de facto rerouting. That's why we have table consistency checks. In this Honeybee protocol, nodes cross-check others' routing tables randomly, and when we find a traitor, we slash them with fraud proofs. So here we have the evaluation result of Honeybee. As we can see here, Honeybee significantly outperforms the state-of-the-art baseline algorithms from the sampling quality. And thank you for your attention. Please check out our paper, Honeybee Decentralized Peer Sampling with Verifiable Random Walks for Blockchain Data Sharding.
Okay, so I'm Longfei Qiu, and I'm presenting our recent work on Lido, which is about formally verifying the safety and liveness of consensus protocols. So we know that consensus algorithms lie at the heart of blockchains, but they are also very difficult to implement completely correctly. And if we look at the bugs that occur in consensus algorithms in the wild, we can see that there are mainly two kinds of reasons that the implementation can be incorrect. First, that your algorithm might itself be incorrect. And second, even if your algorithm is correct, your implementation might deviate from your spec, so it becomes buggy. So it's not enough that we have paper proofs of consensus algorithms. We need formal guarantees that can connect your implementation all the way to an abstract spec, which in most cases is the SMR, state machine replication. Now, formal verification, we know that it has a bad reputation in the industry. People consider this kind of work inefficient, and they consider our implementations as toys, mostly because first, most implications need very ideal assumptions, and they are also very difficult to reuse because you must reprove all the invariants as soon as you modify your implementation. And this means you cannot incorporate the optimizations that are useful in the industry. Now, our belief is that all these difficulties can be overcome by using refinement, which is a proof technique where you first build the safety proof of a simple unoptimized system or abstract system, and then you prove that your optimized optimization simulates the behavior of a simple system. So based on this idea, we introduced a model called LIDO, which is an abstract framework for a leader and round-based consensus algorithms. And using our approach, you can structure the formal proof of your protocol as a sequence of refinements, as shown here, where on the top level you have SMR, and on the bottom layer you have your network implementation. And this can be at first be an unoptimized version, and later you show that an optimized version simulates your unoptimized implementation. So to summarize our achievements, we already achieved this formal safety and liveness proof for Jotian, which is a very recent consensus protocol. And we verified both unpipelined and pipelined versions of it. And we established both safety and liveness. It's the first formal liveness proof for a pipelined consensus algorithm. And the implementation can be extracted to a OCaml executable. And also, we are in the middle of extending this work to cover the more recent algorithms, such as DAG protocols and BFT protocols. That's all. Thank you.
Hi, everyone. I don't have a presentation, so I'm going to make it short. My name is Pak. I'm a co-founder at Moti, which is an identity protocol where we focus on creating utilization and monetization for self-sovereign identity. Each user generate about 150 gigabytes of data a day, making California $5 billion a day. But the users don't actually make anything. So our solution is that we have built a deepened network that is centered on identity, that allows people to basically bind all of their Web 2 and Web 3 accounts across the internet into their DID and enable them to run computation using their private credentials in a secure way. And so what we want to do now is to basically use this structure to build a social graph based on peer-to-peer credentials, verifiable credentials, that enables us to basically create a new age of digital connections. I would love to talk to any experts in identity, someone that is very passionate in it, outside, perhaps over a coffee. And that's it. Thank you very much, and have a good time.
Okay, I have a good news and also a bad news. My talk is going to be funny, and also the bad news is I need 1 extra minute. Okay, so I have I have a cryptography background. I want to mention that cryptocurrencies are not cryptography. Cryptography is a wider range of study that we consider multiple stuff, and cryptocurrency are some subset of this word. So many people, I talk outside during this conference, and they think that we are the security guard of the digital world, okay? I believe that we are not. We are just chefs and farmers in this world. Why? Because I believe that there is a close relation between human food chain and also cryptography chain. In the human food chain, we have the primary resources, light, water, and soil. They go to herbs and also algae and vegetables. And primary producers like fish, cows, and sheep are going to give us the protein. Essentially, they are going to be mixed to have delicious food for the consumers and the people that they are going to the restaurant. On the other side, we also have pure science, math, and physics. From them, we extract some hardness assumptions, D-log isogeny base, lattice base, and so on. And then essentially we go to cryptographical primitives, okay? By mixing some cryptographical primitives, we will have cryptographical protocols. Bitcoin, Ethereum, and some other cryptocurrencies are one protocol, which is a mix of multiple ingredients. And essentially, we are going to serve them. In the human food chain, we have multiple ingredients, potato and onion. It's also the same in cryptography. We have multiple types of digital signatures, okay? Digital signatures are potato in our world. BLS, RSA, Schnorr, and so on. What are the onions? The onions, in my opinion, are zero-knowledge proof systems. One hint, starts are good for frying. So TLS is a mix of potato and oil, a high-quality oil. We already said that potatoes are digital signatures in our world. What about the oils? The oils are key exchange protocols. Choose your perfect key exchange protocol, choose your perfect signature, and essentially you have such a recipe for TLS. However, we might actually go, and instead of having a French fries, we might actually have a Persian fries. Now you have to add saffron to French fries. In this case, you have to add BGV to the TLS, which is a FHE scheme, and it's super expensive. So I just want to wrap up here that many people are working on ZK-TLS. ZK-TLS is going to be a ring onion next to the fries. Dan told me that make it more healthy. Now it's a salad next to it. Thank you so much.
And it's almost working. Okay, so I'm Csaba Király from the Codex research team. We are working on a decentralized storage network, focusing on data durability. We also work with the research team with the Ethereum Foundation on scaling L1, and also with the client teams. So actually, all the people that you see here, Leo, Dimitri, me, are here. If you want to talk about these topics, come to us. Or, as an alternative, there is this material that I wanted to show you. Unfortunately, I don't have a write-up on this one, just the ECC talk. So in this talk, I was introducing data-based sampling. That's less interesting, I think, for those who know it. But there is also PIRDAS. PIRDAS is the next iteration that we'll be implementing in the next hard fork of Ethereum. So there's an introduction to that. And even more interestingly, I think, the techniques that we are introducing to go even beyond that, to target 32 megabyte blocks, or more formally, data related space related to blocks every 12 seconds. So, and finally, I was also giving a broader perspective related to data, decentralized storage networks and data with layers. So if you are interested in these topics, come talk to us, look at this one, or look at this one. This is an East Research write-up on FURDAS. So FURDAS is kind of the summary of techniques, and it's a bunch of techniques that we were developing to get to the 32 megabyte or beyond or near. So to scale layer 1, 6 techniques there, or 7. Lostidas is an interesting one, which is focusing on not having that many false negatives, which is a less known huge problem with data with sampling, availability amplification, topic routing, and then networking techniques, more traditional peer-to-peer networking techniques, which make it hopefully work for larger block sizes. So if you are interested in these topics, come talk to us. We are all here at SBC. Thank you.
Hi, everyone. My name is Eric Forst. I'm the co-founder and CEO of Blocksy. We're a Web3 data index for AI model building. We started our company 2 years ago as a Web3 CRM based on the idea that the wallet is the new cookie. That allowed us to build a data index that correlates off-chain data to a wallet address. As the NFT market went away, we found a new use case for our data index. And we're now powering a new BitTensor subnet, number 45, that just went live last week. And they're using our data index to build a wallet risk assessment model that's useful for payment apps, wallets, DeFi apps. We just finished the first cohort of the Crypto Oracle Collective AI Web3 Accelerator, where we received 200,000 in grants from the Manifest Network. I'd love to talk to anyone who has an L1, L2, or L3 that would like a data index optimized for AI. Come find me. Love to talk to you. Thank you.
Is it showing up? Any technical guys here? Okay.
Hello, I'm happy to have no technical difficulties because I did not prepare a presentation. Apologies for that. My name is Luke Parker, also known online as Kayaba. I am a researcher for the Monero project, and I have my own work, but that's not what I'm here to talk about today. The Monero project is currently working on replacing ring signatures, which have a linear prover and linear verification time, with a Merkle ZK proof of some output existing in a Merkle tree to offer full sender privacy instead of sender privacy within a subset of the outputs on chain. As part of that, we've moved forward a few pieces of cryptography because we're solely using a trustless set of cryptography. And when you need trustless set of proofs, you have poor performance compared to trusted setup options. So we've really had to optimize our verifiers and our circuits to be as small as possible. And with that, we look to Liam Egan's work in 2022 on using divisors and the function fields of elliptic curves in order to prove sums of points. And the end point of all of this is that we have funded the security proofs and are working on the implementation of deployment of proofs of discrete logarithms in a zero-knowledge circuit with just 7 multiplicative constraints over R1CS, which is a 72 times improvement from the industry standard of using double and add over 256 points. If anyone wants to talk about that, I'm available too. I just thought it was worth sharing, this being a cryptography conference and all. Thank you for your time.
Awesome. Hello, everyone. My name is Sumpan, a student from University of Illinois. I assume all the folks in the conference here has a smartphone, and maybe some of you are staring at this right now. If you misbehave with your phone by downloading some suspicious applications, you expose the phone under the risk of information leakage as well as intentional intervene. Probably most of you have crypto wallets, and guess what? The crypto assets are in danger. So I have thought of moving all the wallets operation into the mobile TE. The workflow is simple. You have a request sending to the app. You relate to the precompiled TE, and internally it verifies the request and performs private application operations like signing. All the necessary information on the chain will be obtained through observer nodes with attestation. Since TE has the highest priority inside the phone, no other apps can intervene in the operation or spy on that. The only approachable attack is to steal your phone and to break it. So the above problem is solved. So I'll show a brief draft timeline for the application. But is that the end story for the mobile TE? I don't think so. So back to the old time, so where the Apollo 11 can achieve its mission with only 4 kilobytes of RAM and only 70 kilobytes of its ROM. So definitely with mobile TE, we have more use cases. And I'm looking forward to collaborate with some of you guys in the conference. Some of the ideas I had includes decentralized ML, secure web browsing, maybe distributed VDF using the small devices crowdsourcing, and etc. I will leave my contact at the end. And finally, is that still the end? I don't think so. So right now we build our trust on top of hardware, on top of manufacturer, and also on top of the developers. So I would like to delegate this to the math, which by replacing the components with the current cryptographic protocols, definitely with efficiency. And thanks for listening, and this is my contact.
Hello, everybody. I'm Drew Austin. No slides, just wanted to quickly introduce myself. I'm the founder and managing partner at Redbeard Ventures and Denari Labs. So just to tell you a little bit about us, there's a lot of really incredible builders here. We're one of the more active investors in the blockchain space. We've invested in over 200 plus companies across a wide range of sectors and across a wide range of stacks. A little bit about our ecosystem. We have an AngelList syndicate, which has now about 4,500 accredited investors in. You guys are all welcome to check it out. We have amazing deals that we've distributed through that network. We kind of use that as both a marketing engine and fundraising engine for a lot of really interesting and creative companies in the space. We then raised our first managed capital fund, which is, again, a blockchain-focused venture capital fund, Redbeard Ventures Fund 1. We're now kicking off fundraising for Redbeard Ventures Fund 2. And then we also, about a year and a half ago, started Denari Labs. Denari Labs is a tokenomics consulting and accelerator firm. So, you know, we kind of came across two different gaps that were happening across the majority of our investments. One was that most of the companies specialize in one key area of their business and value proposition, but understanding how to launch a token, how to go to market with a token, understanding sinks, faucets, risk mitigation, exchanges, market makers, all of that was really a black box and a kind of a gray area for people. So we come in and built out an expert team to support the companies in that area. The other part is like developer adoption is key for most of the infrastructure investments that we are investing in. So we partner with a lot of these ecosystems and invest in companies building on their stack, evangelize the stack, and we built out a whole team to support that. So I'll be out in the hallway. Feel free to come by. I thought this would be a better way to just let everyone know that, you know, if you some great builders here and we're actively investing and want to support this ecosystem in whatever way possible. So thanks for having us. And you can find me on Twitter at Drew Austin, and on email, if you want to email, it's drew@redbeard.ventures.
Hello, everyone. My name is Tahir Mahmood. This is my LinkedIn profile. I'll just keep it up here for 2 seconds. You can contact me on that. That's probably the easiest place. I know we all use Telegram, but anyway, let me start. So I think a very lucky stage. We, as Kernel, I'm the co-founder and CTO, are literally about to come out of stealth, and the project is named Kernel. Basically, what we do is we're allowing a transaction, then normally that you have a transaction that goes to a node to be able to do much more than it's ever been able to do. And that's what Kernel is all about. We expect basically to be able to have a new paradigm where a blockchain node in itself is able to do much more than what it does today. So just imagine a transaction being transmitted into a node, and instead of going to the local pool, mempool, being propagated out, that it could actually execute so many other things. And that's what we call kernels. Those kernels, limitless functions, they can be on-chain, off-chain. So we utilize technologies like account abstraction, Web2, open API specifications with GPRS, all the other sort of stuff that you can imagine. It's quite strange how many technologies we use. What I'm going to get down to is the use cases that we have is that imagine you're able to transmit a transaction, do KYT compliance, KYC, the transaction goes on, proof of provenance, that all that execution took place, so you actually know that that transaction is valid and all the proofs are there. what I want to get down to is it's all based around osmotic computing, a lot of this technology that we built. I can go into the use cases, but this diagram probably gives the best example of what we do. Imagine having it that every smart contract function on every chain is accessible to you from the initiating chain. You know, it's a very simple concept, but imagine the whole economy being able to be accessible from one place. I'll just move into that, the architecture, as I'm the technical guy. It's very simple. We have modified a Geth node. That's where we're at the moment to be able to achieve and do all these great things. We'll be able to support all EVM and non-EVM chains in the future. There is a token economy that goes with it. It's a two-sided marketplace. It means people who have got all these smart contracts, which are, I call it, you know, on sort of a very chains which are not making much activity, to be able to bring all of that to other chains. So anyway, I'll leave you today with, we're looking for builders to build on our economy and build on what we're doing. We're literally at the stage of coming out of stealth in the next 2 weeks. Thank you very much.
Good morning. My name is Derek. I am from Martella Network. We're building what we call extensible blockchain. Let's just dive into the technical details. So pretty much what we're doing is called the EVM++. What it means is that we're using parallel EVM and elastic block space to boost the scalability. And on the other hand, which is where the things get interesting, we are actually throwing a extension layer in between the dApp layer and the base layer, and in which there lives what we call aspect, or actually the virtual operating environment that allows people to customize some conditions for the smart contracts to be met before they can be executed. That's what we call aspect programming. And immediately after that, if you want to check more about the technical details, you're more than welcome to log on to the official website and check out the white paper over here. And I should probably also mention that we're actually in the middle of the incentivized testnet. So obviously, we're looking for more people, more infra builders to build with us on these customizable structure, and also more dApp partners to cooperate with us on the incentivized testnet as well. I should probably mention that last week we just surpassed a 1 million user on the incentivized testnet, which is obviously a huge milestone. Very happy for it. If you want to get more of the user base, please, you can either send a message to our Twitter, and also you can find me anywhere in this venue. And happy to talk to you. Thank you.
Hello, everyone. I'm Sachin. I'm one of the co-founders at Bionomy. And Bionomy is a infrastructure company that's focusing on solving the user experience on blockchains, basically. So we are a B2B platform. How we are doing it? We are providing a full stack account abstraction solution for developers building an Ethereum ecosystem, all the EVM chains. And we provide like smart account functionality, paymaster and bundlers. So if you're familiar with ERC-4337, you would be knowing these terms. But the end result of these technical terms is the user experience, basically. As a user, you want to use blockchain applications that are easy to use, that have less friction during onboarding. You want to get onboarded to application as quickly as possible without downloading a wallet. So things like social logins, where you just use email ID to log into a decentralized application, get a blockchain account, and that account will be a smart account. And then after that, you want to interact with the application and doing on-chain transactions. So when you do transactions, you deal with gas fees. And when you do cross-chain transaction, there are like a lot of complexity over there. So we are trying to solve the user experience when you interact with blockchains also. So the functionality like paymasters helps application developers sponsor those gas fees on behalf of the users, so they can just go to the application and just do click of a button and the transaction happens behind the scenes. and the user don't have to pay for any gas. User don't even have to know, what the gas is. So these kind of UX we want to enable on the applications, and this technology actually allows us to do that. There is this new standard I want to talk about, like ERC-7579. That's a standard for building modular, smart account, and our smart account is based on that. And the cool part is that it's open and it's modular, where if you want to extend the functionality of your smart account, let's say you want to add like a multi-sig functionality or spending limits or any other feature on your account, you can do it via modules, and anyone can build these modules, if you're following this ERC. And just wanna, anyone who wanna know like what's going on in account abstraction space, like what kind of traction there is, you can visit this site bundlebear.com, and you can see like there are 12 million smart accounts that have been deployed across multiple EVM chains. Total 46 million user ops have been done. And this recent spike you are seeing here, that's because of the Coinbase smart account that is like gaining a lot of traction like lately. And one last thing I want to mention here, there is this EIP7702 that's like coming in next Ethereum upgrade, the Pectra. And it will actually allow EOA to have like a smart account like functionality. So I'm really looking forward to it. But yeah, anyone who want to talk about UX, I'd love to talk about that. And thank you.
All right. Can someone take a picture of me so that I can show my professor about this? Thank you. Is it working? It's showing up on the screen here, but not. Oh, there. There we go. Okay, hi everyone. I'm Suyan from University of Wisconsin-Madison. I work with professors Ramsey and Andrea Pichiduso. If you know them, they are experts in the storage system in the crash failure world, but we're relatively new to the blockchain world. So kind of like as a first step into a new field, we want to understand what's already out there in the wild. But that's a little bit tricky with blockchain systems because, well, the implementations out there are production code, and we only want to know how fast a plane can fly for when this is what we see in production. The second problem we really face is that we want to understand its performance at the scale in the wild, which can easily go over thousands of nodes, but we don't have that many machines around because we're just research groups. So what we're going to do? Well, for the first problem, we want to know how to, we really have to put those blockchain systems under the same framework. And hopefully this framework can be modularized so that we can easily identify the problems in the blockchain system. And also it should be generic enough so that we can accommodate most of the blockchain systems in the wild. And this is what we came up with. At a high level, I'm not going to go too detailed about this, but this is I'm showing here is this pipeline for maintaining the memory pool. And once you have the memory pool, this is kind of like a pipeline to manage transactions into blocks and get the blocks committed. Several things I want to point out about this model. This is a stage event-driven architecture, and seed architecture is well known for its ability to identify bottlenecks. And out of the decent number of blockchain systems we have been studying for, it fits pretty well with all of them. So that leaves us the second problem. How do we test its performance at large scale when we don't have that many machines? The answer to that, there's a 2019 paper in FAST conference that kind of sheds light to the solution to this problem. And it says that the key to computation is not really the intermediate results, but just the execution time and the eventual output. So what that says is that instead of running the actual computation, actual disk I/O that can be really expensive, we can just sleep. We can just put the program into sleep and returns the result we expect to have. That way, we are able to save a huge amount of computation and disk bandwidth, and that allows us to pack multiple validators onto a single physical machine. So now we end up with this. We have these validators talking to an underlying virtualized network layer, which we will refer to as mailbox. And I'm running out of time, so the last problem we have is network I/O, which is really not a problem because the validator nodes usually have like a much lower bandwidth than data center network. I also got some results, but for the sake of time, I'm just gonna skip it over. If you are interested or you have any feedback on our project, please do let me know. Thank you.
Hi. I just want to talk about this LLVM bug that appeared a few weeks ago. This is a convoluted function which essentially just computes 4 minus x, but which accidentally gets compiled to only return 4. And so this is a bit of a problem when you have a lot of ZKVMs using LLVM to compile code down to ZKVM instructions. And so this highlights a problem in the whole stack where we don't really know, we can't be sure that the code that we're compiling down to ZKVMs is actually like the code that we're intending to run and essentially prove. And so, well, I get that this is a very convoluted example and that in most cases you can trust the compiler to actually do the right thing and give you the correct result. It also highlights that there's essentially a gap in how you can trust that what you're proving is actually what you intend to prove right. And so nobody could go around and audit all of LLVM or like actually make sure that, look at the assembly and make sure that everything is running. And I know that there's also a lot of projects which are working on like verifiable compilation, et cetera, and like using formal verification methods. But this is something we need to be aware of, and also to be able to like have defense in depth methods such as TEs to make sure that that we can handle these kind of failure modes. I work for Argument, formerly known as Lark, and we believe that when you're building these systems, you have to know what you have to be honest with what you're trusting in your whole stack, down from the code you're writing to the compilation phase to the proving phase. And so we're trying to push the limits of like what we can do with ZKVMs by building a much simpler language which is based on functional reduction, and we're looking into building verifiable computation as a ground up, so that the whole system is simple, easy, and auditable. So thank you. Please check us out. Bye.
Cool. This concludes the lightning talk session. Thank you all for sticking around. And we ran a little over, but I think that was okay. There should still be food, hopefully, in the hallway. See you next year. Thank you.
Welcome, everyone, to session 8, the restaking and data management session. I'm delighted to say that we're kicking off this session with another invited talk from Sriram Kannan, who is the CEO of the very popular company EigenLayer, and also a former faculty member at University of Washington. So he is both a CEO and a serious scientist. Please welcome Sriram.
Good afternoon, everybody. Thank you so much, Ari, for the kind introduction. I'm going to talk today about cryptoeconomic security for arbitrary tasks. I'll start with motivating this talk with some of the work we are doing at EigenLayer. So if you think about the evolution of blockchain, our thesis on blockchain is it's a mechanism to create more permissionless innovation or open innovation. And if you look at the various layers of a blockchain, you see basically there is a security layer at the base, and then it could be staking or mining, on top of which there's a consensus layer. Nodes come together and arrive at consensus. On top of which there is an execution layer, like an execution environment, like Bitcoin script or EVM or whatever. Then applications then build on top. Bitcoin was an application-specific blockchain designed for storing, sending Bitcoins. So you had all these 4 layers, and they were all tightly coupled and integrated. And Ethereum was the first modular blockchain. Modular in the sense that anybody can build new applications on top of a common substrate of security, consensus, and execution. So this led to a whole growth of dApps. Anybody coming and building new kinds of smart contracts on top of a common trust platform. And then you go to the next framework. I think you look at rollups. Rollups, basically, anybody can come and build new execution environments on top of a common consensus layer. Each rollup runs its own off-chain execution and makes proofs that it did the execution correctly. And so now you can have innovation at the level of execution environments. You can build many execution environments on top of a common consensus and security layer. And what we did with EigenLayer, I used to run the University of Washington Blockchain Research Lab, where we worked a lot on consensus protocols. I also have a bunch of papers with Ari on FAR ordering and consensus protocols. Let's say you want to go build or deploy any one of them. You don't have root access to go change it on Ethereum. So this is really why we built EigenLayer. We built EigenLayer to modularize security. It just does security, on top of which anybody can build new consensus layers, on top of which other people can build execution layers, application, and so on. So it is the deepest level of open innovation. So now you can basically build anything. So just imagine an abstraction. It just covers decentralized trust or security. Now anybody can come and build new kinds of networks, protocols, which require you to reprogram how the network works. OK, so we call these consensus layers built on top of EigenLayer. So EigenLayer is the name of the protocol that we built. And it's a system for shared security, a common security layer for any decentralized network to be built on top. These networks, we call them AVS, actively validated services. Actively validated means somebody is actually running nodes to keep these things going. Services rather than chains, because we think of service as the right unit of operation. You may be sitting on Ethereum and you want to make a call to an AI engine, and you get a return, which is the executed output of this AI inference. That's a service. It's not necessarily a chain. OK, so that's the setup. Now you ask, how do you provide security? And in this talk, I'm not going to talk much about the sharing part, which is how do you extend security to multiple different systems. But I'm going to focus on what is the right framework for providing security. So the core idea in EigenLayer is cryptoeconomic security. What is cryptoeconomic security? You have a bunch of nodes which commit stake. They all commit some stake. Stake is just take a bunch of digital assets, ETH or something else, and then lock them up into a contract. And once you lock them up into a contract, now you promise to run various services, various AVSs. Okay, so that's what's happening. And the main question is, when you have permissionless validation, anybody can come and run validators, how can you make sure that these validators are doing the right thing? And the core idea of cryptoeconomic security is if nodes fail to perform the task in the way they promised to do it, then they'll lose their stake. So that's the check and balance for how cryptoeconomic security works. Okay, so once you look at this, you can ask the question, do we need cryptoeconomic security? Are there other ways of doing security? And should we use the best possible one? And so to do this, we came up with a taxonomy of what kind of properties you want from systems and how we can use different mechanisms to achieve these security properties. So a group of nodes come in and they're running some task. And what you want to do, I said in cryptoeconomic security, if they did the thing wrongly, so which means they committed a fault, they should be punished. So what kinds of faults are we talking about? The first category of faults is objective faults. Objective faults means you're violating some objective condition. Think of it like a mathematical or a cryptographic or like a deterministic code execution. So the first category, subtype of objective faults, is we call it proactively attributable. What does proactively attributable mean? I run a piece of code, and then I can attach a proof that I've actually run this piece of code correctly. So as soon as I give you an output, I can give you a certificate that I've done that output correctly. And when you're running an execution, so you can use something like zero-knowledge proofs, which is basically what we call in our space, but really verifiable computing, which is you can create short proofs of correct execution. You can use either zero-knowledge proofs, or you can use cryptoeconomic security. CE stands for cryptoeconomic security for this. But ZK is probably better. And a lot of people think maybe ZK is all you need. You don't need anything else. All you need is cryptographic integrity to do all these tasks. I'm going to argue it's absolutely not the case. So the next category of faults is what we call retroactively attributable. They're still objective, but only retroactively attributable. What do I mean by that? Imagine I sign to, the protocol says you should, validators should sign off on only one block for block number 30. But a validator goes around and signs 2 certificates for block number 30. This is a violation of a core covenant of the protocol. But I cannot give you a certificate that I have never signed another block with block number 30. Because this is not an error of commission, this is an error of omission. I've given this other certificate to another counterparty and trying to fool everybody. So, but retroactively, after I did this, somebody can, get both the certificates and prove objectively by showing me 2 certificates that Sriram signed on block number 30 is H, but block number 30 is G. They're not the same, so he should get slashed. So it's objectively attributable, but only retroactively. You cannot do ZK for this. There is no cryptographic proof of integrity for this. Except in quantum computing, you can use the no-cloning theorem to do this, but we'll skip that for here. So this is, we call them reorgs or double signing or whatever. And these faults, you need cryptoeconomic security. I have a bunch of stake. I promise that I will not do this error of omission, like that I will not sign 2 blocks at the same block number. And if I do, you can catch me and slash my stake. Okay? So first argument for why ZK is not the end game. ZK is not the end game for building blockchains. We need much more interesting, more important fundamental primitives, or equally important fundamental primitives to actually make these systems work. Okay, what else do we have? We have a category of faults we call intersubjective faults. Okay, fancy name. What does it mean? Intersubjective. Subjective means like I have my own opinion. Intersubjective means we can all socially agree. Another way of thinking about it is these are faults for which there is off-chain agreement, but not necessarily on-chain agreement. Okay, so I'll give you an example of a fault. We say, who is the president of the United States? Who won the silver medal in swimming in the Olympics? Examples of questions for which we have off-chain, social, intersubjective agreement. But on-chain, I don't know. There's no locus to bring the right sense of truth on-chain. So these, we call them intersubjective faults. So when you think about intersubjective faults, we still categorize them into two types: retroactive, and an example of this is, an Oracle price feed, let's say. I come in and say, 1 BTC is equal to 1 USD. 1 Bitcoin is 1 US dollar. It's absolutely not true, we all know, but on-chain, somebody said it. Now what are you going to do? How do you know it's wrong? We don't know on-chain it's wrong, but we know off-chain from the outside frame of reference that it's wrong. So this is an example of intersubjective fault, and it's retroactively attributable. Depending on the scale of the error, it's retroactively attributable. I can come back in 3 weeks, and if I said 1 BTC is 1 USD today, you would still know that I said the wrong thing 3 weeks back. So intersubjective, retroactive. Okay, so the next category of faults we call intersubjective concurrent. Concurrently attributable. Concurrent basically means you had to be there at that time to know that it was a fault. One fault that we think about a lot is data publishing or data availability. I have a network of nodes which are storing the data, and they're promising that we will allow anybody to download the data if they ask for it. It's called data availability. Is AVS that we are building called EigenDA. Okay, so in EigenDA, these nodes promise that they're going to serve the data to anybody who asks for it. But how do you know that they all didn't collude and never serve any honest node ever? Even if they served one honest node, that node has the data, they can go and stand up a website and let anybody else distribute the data. But what if they never served even one honest node? This fault is not observable on-chain, but it's observable off-chain. Anybody who's querying the RPCs, anybody who's running a full node, anybody who's connecting to the peer-to-peer network, all have a locus to know whether data was published or not. This is an intersubjective fault, off-chain observable, but concurrent. I need to be there at that time to know. I can't come back 1 week later and know whether the data was published this week or not, because I may have withheld the data this week and publish it 2 weeks later after whatever fraud-proof window or other important time horizon lapses. So it's a concurrently attributable intersubjective fault. So this is the topography of the various kinds of faults. There are also non-attributable faults. They're neither on-chain attributable nor off-chain attributable with high social concordance. An example would be you take a data item and then spread it into secret shares, like Shamir's secret sharing, many of us would have read. So you take the data and then split it into secret shares and send it to a network. Now, if a majority of the nodes met together in a private boardroom and revealed the data to somebody, there's no way for us as a society, as outside observers, to get social concordance on whether that happened or not. So this is not even intersubjectively attributable. So these are the various topography of faults that we came up with. And the question became, how do we create cryptoeconomic penalties for intersubjective faults? To go into this, I want to specify a meta framework for coordination. Whenever you're thinking about who is enforcing these conditions of coordination. So think of this like the fact that you don't want certain kinds of faults, think of this as basically like a condition of coordination. I'm a validator, I've opted in, I've promised that I will not make these faults. Now, who's enforcing this type of coordination? You can think of like broadly at like a macro scale, 4 types of coordination. You can have an authority that enforces a condition of coordination. You can have a committee that enforces the condition of coordination. You can have a majority of some group of nodes that enforce a condition of coordination. And then, and each of them are more robust than the previous one. And then finally, I think you have the gold standard of coordination I call self-enforcing coordination mechanisms. A self-enforcing coordination mechanism executes itself irrespective of what anybody says. Neither an authority, nor a committee, nor a majority can come and corrupt the condition of coordination. So that's what we call self-enforcing coordination. So I'll illustrate this with an example in blockchains. You know, a lot of the theory that we do as academics in blockchains usually stop with majoritarian coordination. We assume a majority of nodes are honest, what properties can you brew aboard a consensus protocol, and so on. But the really powerful thing in blockchains is you can go even beyond that to self-enforcing coordination systems. Imagine like you're running a blockchain protocol, and a majority of validators are malicious, and they sign an invalid block. They sign a block, the state transition function is not computed correctly, they sign off on a block. Okay? So this is a majority malicious behavior. And in a protocol like Ethereum or Bitcoin, the condition is that if the block is invalid, it doesn't matter even if a majority signs off on it. You don't accept it. You don't accept a block which is invalid, which means you fork around it. So you fork around it means somebody else will include the certificate claiming that a majority were malicious, and then they can continue. Only the remaining nodes are now eligible to participate in consensus. They come to consensus, and then they can actually proceed forward based on this system. So this is a self-enforcing coordination for validation, for execution validity in a blockchain. You don't need to trust a majority. If a majority does the wrong thing, signs off on an invalid block, they'll get slashed, they'll get removed from consensus later. Very, very powerful system. So blockchains are not correct based on a majority of the nodes. They are self-enforcing. Okay, so this I'm specifically talking about for execution validity. So we have to take each fault that a blockchain can perform and make sure we can recover from that even when there is a majority fault. Okay, I'll skip ahead and start the question. Okay, so this is true for execution validity. Right? Go back here. If the execution was wrong, then yes, you will fork around it. But what if inside this Ethereum block, there was an Oracle price feed or an EigenDA feed or some other AVS brought in a wrong data? We can't fork Ethereum. Ethereum has we don't have any license to fork Ethereum for things that happen on the application layer or on the eigen layer or any AVS layer. Okay, so what do? This became the big open question for us in resolving how do we solve faults which are socially, intersubjectively, off-chain attributable, but we want to enforce this not based on an authority, not based on a committee, not based on a majority, because they all suffer from the tyranny of majority. A majority of the committee could lie, a majority of stakers could lie, so we don't want to trust any of them. We want to enforce it only to truth, not to power. Okay, how do you do this? So, the methods people have are majority voting, like you have a majority of stakers vote on something, you can have a committee vote on something, but you have to ask the question, what types of coordination mechanisms are we building? How do we make them very robust? And both of these are vulnerable to the tyranny of majority. So the only system that's really robust to the tyranny of majority that we know about is forking. Okay, but as I said, the problem is, so what's happening in forking is if there were two forks of Bitcoin or Ethereum, people figure out what is the right fork because they know what the execution conditions are. It is self-evident what the right fork is, and so people automatically gravitate towards the right fork. Okay, so you can think of forking as like a social consensus on an unsized and unbounded group. Like you don't know who these people are. Anybody who's coming behind you is going to decide what the right fork is. So this is the only system that is robust to the tyranny of majority. So we call these self-enforcing. So the question is, how do we extend crypto economics to any intersubjective fault without forking the chain? Because EigenLayer is built on Ethereum. We have no license to fork Ethereum. What are we going to do? Okay, so that's the main problem. So I'm going to illustrate a couple of key ideas and then put together the solution for you. The first idea is when we're talking about forking, a lot of people have this idea of social consensus as ad hoc, post facto, capricious. We meet on Twitter and then say, oh, that guy is bad, I'm going to fork him. That's not a good system. It's a kangaroo court. You want to have a system where it's preset. There is a setup phase which presets what the conditions of forking are, and then an execution phase where you just follow the pre-agreed conditions. You fork on pre-agreed events that are self-evident. 2 words, pre-agreed, self-evident. So you only fork on pre-agreed events that are self-evident. Okay. One thing that gives us a good match here is when we're talking about self-evident, intersubjective faults are self-evident because they're off-chain observable. So that's a good match of what framework we're talking about and this core idea. The second core idea is, as I said, we're building on Ethereum, we have no right to fork Ethereum. What are we going to do? We create a new idea we call token forking. Okay, so here is a meta point. I said the faults are intersubjective, which means socially, off-chain, it's observable whether it's a fault or not. There's another thing which is intersubjective, which is the value of a token is intersubjective. We all look at a system and say, suppose I take Bitcoin and fork it and create another chain. Are you going to say that that's worth $1 trillion? No, you'll say the original one is worth $1 trillion, this new one is BS. That's what you're going to say. Value is intersubjective. Truth, social truth is intersubjective. You merge these concepts. So that's the basic idea. Okay, how do we do this? The core idea is instead of forking the chain, which we have no license to do, fork the token. What do you mean by fork the token? So, you're chugging along, you've staked the eigen token on eigenlayer, and the system's chugging along, and then a majority of eigenstakers turn malicious and report that 1 BTC is equal to 1 USD. Okay, now they've created an error event. Now what do? We need to punish them. They need to lose their eigen. That's the right punishment for them. How do we do this? Anybody can create a new fork of eigen, the token. They create a new fork of the eigen token. And now, in this new fork, they say, oh, we're doing this because of that pre-agreed condition that eigenstakers shall not give a wrong oracle report. So now, those stakers who gave the wrong oracle report, 1 BTC is equal to 1 USD, their stake is removed from the second eigen token. This is a new eigen token is created. So now looking outside looking from inside Ethereum, Ethereum doesn't know whether eigen 1 is correct or eigen 2 is correct. Both look the same to Ethereum. It's just another ERC20 token. But looking from the outside, we know the pre-agreement on what is the eigen token is the one that says the truth. Okay? So people converge on eigen 2 as the token that is valuable. When people are trading it, they're going to trade eigen 2. When people are staking it, new services come in, they would want eigen 2 to be staked, not eigen 1. So this is the core idea. The fact of whether eigen 1 is right or eigen 2 is right is not transparent on-chain, but it's transparent off-chain. And we want to bring that intelligence on-chain to turn around the crypto economics. You want to enforce the correct punishment and rewards. Okay, on the eigen users, point to the right one. So this is the core idea. There is more to it. This doesn't overload Ethereum's social consensus because Ethereum doesn't need to know what is going on. Only anybody who's interested in the eigen token needs to do this. This is not the idea that tokens can be forked is not our original idea. Vitalik wrote about this back in 2014. There was a paper even earlier called TruthCoin, and a bunch of blog posts here. The main system that worked off this idea is called Augur, which used this idea of token forking. But it had a bunch of shortcomings. I'm not going to get into it, but I'll explain how we solve those shortcomings. So the first property that we have for eigen is it's universal. Universal. What do I mean by universal? It is not an application-specific forking token. Augur was an application-specific forking token built for prediction markets. Eigen is a universal forking token. So what that means is you can start building new tasks on top of the eigen token and create forking conditions for all of them. And if the eigenstakers opted into those conditions, they'll be bound by it. Okay, so universality is one major concept in the eigen token. The second one, which actually makes this insanely hard, is what we call a property called isolation. Isolation is If a token is forking willy-nilly, that same token is listed on exchanges, the same token is being lent and borrowed, there's financial applications on all these tokens, it induces a downstream cascade of events that you don't want. So the way we solve it, we create two kinds of eigentoken. One called a solid representation. A solid representation is one which is honored 1:1 on every eigenfork. If you hold a solid representation, it's honored 1:1 on every eigenfork. But if you hold a not solid representation, which is forking representation, then you are stuck with that fork, but you need a forking representation to stake. So what we do is we decouple the utility of the eigentoken on fork staking and financial utility with two different tokens. And then finally, or the third point is metering. Metering is forking induces a social cost. Somebody comes in and says, hey, there are two eigentokens, they can be forked. Now this is a problem, because now everybody needs to adjudicate whether eigen 1 is correct or eigen 2 is correct. Induces a massive social cost. You don't want that. What are we going to do about that? We meter the cost of social consensus. Let's say we know, this is going to induce X amount of pain on all the users. What you do is you say, when you fork the token, whoever is claiming to fork the token, they have to burn a bunch of the first token, the original token, and they will be minted the same amount or more in the second token. So they are actually measurably giving up opportunity cost. If the first token turned out to be right, they're burning their fingers. This is a kind of a bloodletting in making sure that they are actually do not create denial of service, but also, if they were wrong, the value of the other user's eigen token increases, compensating them for their attention. Okay, so that's metering. And then finally, we found a major problem in cryptoeconomic security, which is cryptoeconomic security models usually were adversary-centric, which means they think about whether an adversary, they think about what is the profit that an adversary can make from attacking the system, and what is the cost incurred on the adversary. It's called cost of corruption and profit from corruption for an adversary. But the problem with these things is there are always extrinsic incentives that you can't model. Somebody may have a short position, somebody may be bribed, somebody may have some other thing going on. You can't model all of this stuff. So we created a new framework we call strong cryptoeconomic security. Strong cryptoeconomic security is adversary neutral. You don't need to think about the adversary. You think about yourself as a user. And the way you do it is if you're transacting certain value on the system, you buy insurance directly from the system called compensation. And when the stakers are slashed for their misbehavior, you can take that stake and compensate back the people who hold the insurance. So if I'm using an Oracle in a DeFi protocol and I have risk worth 1 billion, if I hold insurance worth 1 billion from the protocol, then I'm cryptoeconomically secure, irrespective of what the adversaries do. So this is a brand new concept of cryptoeconomic security that we invented called strong cryptoeconomic security. The eigentoken satisfies all these properties, solving this fundamental problem of how to do strong cryptoeconomic security for arbitrary intersubjective faults. Thank you so much.
Okay, we have time for maybe one question.
Just trying to understand from the Ethereum Classic fork perspective, the only proposal here is you would have to burn a bunch of tokens before you can mint eigen 2 tokens? Or is there something else?
There is all the 4 differences that I laid out. The first one is Ethereum versus Ethereum Classic. The problem was the setup condition of Ethereum was code is law. Code is law. And then what we had to do was to negotiate that code is law except there are major bugs. So this was a massive social renegotiation, very hard. Second one is Ethereum does not fork for arbitrary events. And to fork for arbitrary events, you need a mechanism to solicit and monitor the cost of forking and the total amount at risk for all these different events. So that goes to the first point of universality. The second one on isolation, which is also a very important thing, which is how do you make sure that there is a single representation that is honored 1:1 on all these different forks. There's a whole bunch of details on this. I'll let you take a look at that. And then finally, slashing and redistribution is a new concept for how you honor people who are actually using the system without letting them make random assumptions on adversaries. So those are all the differences. Thank you so much.
Thanks, Sriram. Okay, our next talk is entitled Atomic and Fair Data Exchange via Blockchain, and will be given by Nusret Tas.
Okay, it's working. My voice coming all right? Yes, okay. Well, welcome to the afternoon session. My name is Nusret Tas, and I will be talking about our work, Atomic and Fair Data Exchange via Blockchain. This is joint work with my wonderful colleagues, Istvan, Yino, Mark, Mahimna, Joe, and Lara. So let me jump right into it. So I would like to start by explaining the fair data exchange problem. So this problem involves two parties, a server that holds some data, and there is perhaps a succinct commitment to this data up in the cloud that is publicly accessible by everyone, and there is a client that holds some payment, and the client would like to retrieve the data by paying for it. Now, our goal is to basically design a protocol where the client and the server communicate with each other. And as a result of this communication, the server obtains the payment and client obtains the data. And as you can see, there's some formatting error, which wasn't there 2 seconds ago, but let's stick with that. Yeah, so our goal is to achieve this, and we would like any protocol achieving this to satisfy three main properties. The first one is correctness. So the correctness states that if the client and the server are honest, then the client obtains the data and the server obtains the payment. However, we would like to guard the system against adversarial clients, and this is captured by server fairness, which states that an adversarial client should not learn anything about the data without paying the server the correct amount the server asked for. And similarly, we would like to guard it against adversarial server, captured by this property client fairness, which states that an adversarial server should not receive any payment if the client does not obtain the data it asked for, namely the data underlying the commitment. Okay? Now, unfortunately, there is an impossibility result. It's a well-known result from late 90s. It's impossible to achieve all these three properties without a trusted third party. But the name of this conference is Science of Blockchain, right? So we do have blockchains as our trusted third party, so this gives us some hope about achieving that. But before I explain how we can use blockchains for that, let me motivate this problem further. We, in fact, could use a fair data exchange scheme for proto-dunk sharding. And how does this work? So in proto-dunk sharding, there is this blob data that is eventually kicked out of the chain, but it can be stored off-chain by some volunteering servers, right? So here we can see the blob data. Now, a commitment to this blob data, a KZG commitment, continues to live on-chain, so it continues to live on Ethereum, but the servers are just volunteering to store and serve it to clients in the future. Now, we can use our FD scheme to motivate these servers to keep storing it by enabling clients to pay for this data in an atomic and trust-free manner. So this is one application of the fair data exchange, and other applications could perhaps include exchange of other archival blockchain data, motivating servers to keep storing other archival blockchain data, and facilitating data marketplaces over the chain, such as clients would like to, they could want to stream movies, and now they could perhaps purchase the movie over the blockchain. Okay, so now we are equipped with the blockchain as a trusted third party. Let me give a strawman solution. So our strawman solution starts with the client locking some payment in a contract on the blockchain. Now, the server, in order to unlock this payment and retrieve the coins, it sends the data, the full data, to the blockchain. You might have some question marks here, but hold on to that. Now, the blockchain checks if the data the server posted is indeed the correct data the client is asking for, namely the data underlying the commitment. And if that is the case, it lets the server withdraw the coins that the client locked. And finally, the client can read the data from the blockchain, and this way it will obtain the data, and the server will end up obtaining the payment. However, there is a major problem here. All data is posted to the blockchain, so we are using the trusted third party in a very heavy manner, and blockchains are notoriously limited in terms of computation and storage. Right? And to give an example, posting 1 megabyte of data to Ethereum, even after all of these updates, would still cost $2,500 US dollars. Now, in our protocol, we would like to offer a solution for that. And our solution works as follows. We will first have the server encrypt the data. Then it will transfer the encrypted data off-chain. So most of the data will be going to the client without touching the blockchain at all. But now the data is encrypted, so the client doesn't know what data it received, let alone whether it received the correct one. So the server will sell the decryption key on-chain. So whatever touches the on-chain will be a succinct decryption key. Okay, so this seems like a viable solution. However, now, how does the client know that the key that it will buy from the server on-chain is going to actually decrypt the ciphertext to the correct data, namely the data underlying the commitment, right? So here, the server must actually prove to the client that the key it's going to sell eventually is going to decrypt the ciphertext to the data under the commitment. Okay, so to achieve this, to help the server prove to the client this fact, we will need a new cryptographic primitive that we call verifiable encryption under committed key, or VEC for short. So this is a variation on the verifiable encryption. So it consists of 5 algorithms. So we first generate the public parameters, and you should think of all future algorithms taking these public parameters as input. There is an encrypt algorithm that is run by the server. It takes the commitment to a witness and the witness W as input. Right? Here, by witness, you should think of our data, and it outputs a verification key, a decryption key, a ciphertext, and a proof pi. So what are these objects for? So in particular, what is this proof pi proving? The proof pi is proving that the ciphertext CT is the encryption of the data, the correct encryption committed by the commitment C under the decryption key SK that is committed by the verification key VK. So VK commits to the SK, and C commits to the data, right? So our proof is proving that. Now, we have a key verification algorithm that is run by the blockchain contract, and it basically checks if you give me a verification key and a decryption key, whether the verification key commits to the decryption key. So it checks if this commitment is correct. And we have a ciphertext verification algorithm, which checks if I'm given a commitment, a verification key, a ciphertext, and a proof, whether the ciphertext is the correct encryption of the data committed by the C commitment, right, under the decryption key committed by the verification key VK. So it outputs 1 if this is true, and decryption simply decrypts the data. Okay, so these are our 5 algorithms, and the bottom 2 are run by the client. Now, we would like this VEC scheme to satisfy 3 perhaps basic properties. These are really important, but they sound familiar. So first one is correctness. Both verification steps for key and the ciphertext must succeed for honestly generated encryption. And this is going to imply the correctness of our fair data exchange scheme. The second one is soundness. So no efficient adversary should be able to generate these SK, VK, CT, and pi, such that the verifications succeed, both of them, but the decryption would not output the witness. So if no adversary is able to do that, then we can infer the client fairness of the fair data exchange. Because now the server will not be able to fool the client by giving it some values that for which the verifications succeed, but the client won't be able to obtain the data. And finally, we would like to enforce computational zero knowledge. The ciphertext and the proof should leak no additional information about our data. And this would imply the server fairness of the fair data exchange scheme. Now, because one of our main motivations is to use this for proto-dank sharding, in particular to incentivize the servers to keep storing the data in proto-dank sharding, we are going to assume that our commitment to the data is a KZG commitment, a polynomial KZG commitment, which means that our witness is a polynomial, and data is simply corresponds to the evaluations of these polynomial at these points, and the commitment is the KZG commitment. Okay, so now equipped with this object, let's see how we can achieve the fair data exchange protocol. So as the first step, the server will run the encryption algorithm on the data, and it will output a verification key, a decryption key, a ciphertext, and a proof pi. Then it will post the verification key to a contract on the blockchain. Then it will send the ciphertext and the proof to the client off-chain. Note that most of this data is transferred off-chain. Then the client is going to verify this proof with respect to the verification key on the blockchain contract, and the ciphertext is received off-chain. And if the output of this verification is 1, then what the client will do is it's going to lock the payment. Okay? Now, once the server observes the payment is being locked, it will send a decryption key to the blockchain contract, and the contract is going to check if the decryption key matches the verification key, the commitment to the decryption key. If this answer is 1, then the contract is going to allow the server to withdraw the coins that the client locked up. And now, finally, the client can indeed read the decryption key from the blockchain contract, and using the decryption key, it can decrypt the ciphertext and obtain the data. So this is the full protocol once we are equipped with this VEX scheme. Okay, but where did this VEX scheme come from, right? Like, where do we even get it? So now I would like to describe a very simple VEX scheme, assuming that we use El-Gamal as our encryption scheme to generate the ciphertext. So here are our public parameters, some group elements, and the encryption algorithm run by the server, our prover here, is going to be simply sampling a random field element. It will be our El-Gamal decryption key, and the corresponding commitment verification key to it will be this value shown here. And the prover is going to generate these El-Gamal ciphertexts. Now, for now, let's assume these data points, right? Remember that the data was the evaluation of the polynomial at these points. Let's assume they're small, so we can easily decrypt the El-Gamal ciphertext. And for the prover is just going to use a generic zero-knowledge snark. So with the instance being the commitment verification key, the ciphertext, the witness being the decryption key and the polynomial, the witness. Okay, then it sends over this verification key, ciphertext, and pi to the verifier, which is our client here, and it outputs, it verifies the ciphertext if the proof verifies. It's as simple as that. It's just checking the snark proof. And the decryption is the decryption for El-Gamal, and the blockchain contract, in order to verify if the decryption key matches the commitment, the verification key, simply checks this relation, the same relation as the generation. Okay, so far so good. Is this the end of the talk? Well, not really. So note that when we use a generic zero-knowledge snark here, we are including the encryption as part of the snark relation. And we realize that this might not always be the most efficient thing to do. So what we do in our work instead is we design an efficient VEC protocol that exploits this shared structure of the El-Gamal ciphertext and the KZG commitments. If you look at how these are constructed, they have a shared structure. And furthermore, I did assume the evaluations of the polynomial are small. Before that, I'd like to flash that meme. If you are really up to your current memes, you would maybe immediately get it. But what this means is that we don't need this heavy equipment of a zero-knowledge snark. We have our own scheme that's more open box. So, And furthermore, we can indeed support large data elements. We don't need to assume they are small by splitting the large messages into smaller pieces, perhaps by splitting them into like chunks of 8 or 16 chunks. And then, of course, we need to show each chunk is small with range proofs, and we can batch them as well. OK, enough of the meme. Unfortunately, there is a drawback here. Well, this step blows up the ciphertext size by k, which could be 8 or 16, right? Now, what do we do about that? In response to that, we designed another WEC scheme that is now not based on El-Gamal encryption, but it's based on poly-A encryption. And this avoids the ciphertext blow up by a factor of k, at least theoretically. And then we have shown that both of these schemes are secure. First, assuming decisional Diffie-Hellman assumption, we showed that the El-Gamal-based WEC protocol satisfy correctness, soundness, and computational zero knowledge. Recall that these imply the correctness, the client fairness, and server fairness of our FDE scheme in the random oracle and algebraic group models. And similarly, for the poly-A-based WEC protocol, assuming the DCR, decisional composite residuosity assumption, we can prove security in the random oracle and algebraic group models. Okay. I mean, okay, so far I have assumed there are only two parties, a single server, a single client. Well, there is also our trusted third party. I'm not even counting that, our blockchain contract. But in reality, multiple clients might want to purchase the same data. That is plausible. Like just going back to our data marketplace movie example, it's not true that each movie is watched by only one person in the world. So in this case, server can ask itself the question, can I save some work by amortizing my proof generation across these many different clients? Right? Well, here's a strawman idea. Why don't you just generate your proof once? Just generate a secret key once, a verification key, a ciphertext once, and reuse that for all of the clients. Well, there's an issue here because, first of all, to sell the secret key to the first client, you're already posting it to the contract, right? Now, all other clients can read this the decryption secret key, sorry, the decryption key from the contract, and they don't need to they don't need to buy the key anymore from the server. Now, you might say, OK, we can maybe fix this. I can maybe encrypt the decryption key to the public key of the client and do a more complicated proof and resolve this issue. But there is another drawback here, which perhaps is much harder to resolve, which is the fact that these clients might be talking to each other, right? So perhaps they won't talk to each other too much, because like if each client just serves the full data to its peers, then it will be acting as a server. So we also cannot do really anything. So we won't be assuming clients can tell the whole data, but it's plausible that each client will tell each other this decryption key that it obtained from the server. Okay. In particular, maybe each client can tell each of the other peers that data that is succinct in the size of the full data that they are asking from the server. This tells us that we must, or the server must, re-randomize the decryption key across the clients in order to amortize some work. And we indeed give a multi-client version of our WEC protocol in the paper called MC-WEC, where the prover saves some work by moving parts of proof generation to a pre-processing step. In particular, the ciphertext generation and the range proof generation for the El-Gamal-based WEC, they are both moved into the pre-processing step. So the step that is done per client only involves re-randomization of this decryption key and generating some elements associated with that. So we will now soon see how this helps us. So now I have been talking about how we designed this more efficient scheme, but well, what makes it more efficient, right? Now everyone wants to see some numbers. So let me briefly talk about the implementation. So we created a proof of concept implementation in Rust on a consumer laptop. I should warn that this is a very early proof of concept implementation. It can be improved in multiple ways, even with known optimizations. And here is our prover time for 4096 field elements that could be used to generate the BLS-12-381 group elements. And the total size would be roughly 128 kilobytes. And for this plain text size of the data size of 128 kilobytes, we observed that in the exponential Al-Gamal encryption case with a blow-up factor of 8, the range proof and ciphertext generation takes 89 seconds, but the overhead for proving the consistency of this ciphertext with respect to the commitment and the verification key is only 40 milliseconds. So what does this mean? This means that the pre-processing step in the previous multi-client web case will be the 89 seconds, but per client, the extra work I will need to do will be on the order of milliseconds. And for the Palier encryption, this proof generation, the runtime of this encrypt algorithm will be roughly 5 seconds. And here you can see how it changes as we vary the data size. Okay. Now let me briefly talk about the proof size. So the proof size for the exponential Al-Gamal case will exhibit a blow-up factor of 12x. So here this blow-up is compared to the plain text size. Now most of this blow-up is coming from the ciphertext because the proof is constant in the size of the plain text. It's just 6 group elements, assuming we can batch the range proofs. In the Palier encryption case, interestingly, the blow-up factor is 50, which is worse than the exponential Al-Gamal, even though our original motivation was to avoid this K factor, right? The K blow-up factor in the Al-Gamal case. Well, the reason is because the Palier group, in the Palier case, the group elements are much larger, and also the proof has linear size in the data, unlike in the exponential Al-Gamal case. And it's this should not discourage people. It might be possible to pack multiple plain text elements into a single Palier ciphertext. So we haven't done this packing, but this might be a future direction to reduce this 50 times blow-up. And for the verification and decryption times, we observed that for the exponential Al-Gamal case, the decryption time would be very quick with lookup tables. And for the Palier case, it's on the order of seconds. Yeah, and now we are getting close to the end, but let's have a more positive note, the on-chain costs. So the whole motivation was to reduce the on-chain cost here. Have we actually achieved our goal? Well, we did because the on-chain cost is constant in the size of the exchange data. It's simply 3 signatures, one verification key and 1 decryption key posted on-chain. And how many dollars is that? So what is our metric here? Well, on the Ethereum L1, there is the amount that the server and the client would need to pay for these posting operations will be very little, like on the order of a few dollars at most. And here are some of the functions, here are some of the transactions run by the clients and the server. So this one registers the server's verification key on chain. This one logs the client's payment. This one verifies if the decryption key and the verification key matches. And this one enables the server to withdraw the payment. And as you can see, they are quite small. But if you're not satisfied with these numbers, you can go even smaller on L2. Of course, this is not too surprising, but could be made even 200 times less. Yeah, so we have presented a scheme, a fair data exchange scheme based on verifiable encryption for committed keys, and with a focus on KZG commitments, and with an application in mind for proto-dank sharding. And if you can consult our paper for more details on how you can use Bitcoin instead of Ethereum as this trusted third-party blockchain with the help of adapter signatures, they could be used to replace emulate this contract's role. And how to support verifiable encryption for committed keys for subsets of the data. Maybe you're not asking for the full data under a certain commitment, but on a subset of it, so we can support that. And you can check out our definitions for those as well if you want to design them for different commitment schemes. And there are some future directions I would encourage people to look into. The first one is I mentioned the Palier encryption has a large blow-up factor, perhaps because the proof size is linear in the size of the data. So can we have a constant size proof for that? Can we design these VEC schemes for other commitment and encryption schemes? Can we avoid the grieving vector for the server, which means that a client asks for this encryption and the proof, then disappears, right? Then now our server did some work, and then it can't get paid for it. So we have some ideas for it in the paper, but it will be good to think about that. And of course, there's this general question of how do we price the data. So far, we only let the server decide the price, and the client pays for it. But perhaps maybe there might be some dynamic pricing depending on how much client demand there is. And you can consult these links for a blog post with a summary of our work, our paper, and the open source implementation. Thank you.
Okay, we have time for a couple of questions. Perhaps I'll ask a question. So it seems that your solution doesn't yet scale to large quantities of data. Have you looked at perhaps using proofs of retrievability or proofs of data possession as a way to accomplish that kind of scaling?
Yeah, that's a great question. We thought about it. Proofs of retrievability is not enough for our goals. So proof of retrievability, or okay, more like proof of replication, for instance, like those things, they prove to me that the data is being stored by the server. But in a proof of replication, there is no guarantee that the server will actually give me the data if I ask for the data. For instance, they can keep posting these proofs on chain to get a reward, right? But now if I want to buy it, they can just disappear.
Oh, I meant as a way to show that the ciphertext was correctly constructed.
Oh, yeah, that could be a potential direction.
Okay. I think we have another question here.
Thanks a lot for the great talk and the great work. That's an amazing contribution. I wanted to ask about how do you make it work for Bitcoin? Can you give a few more details, please?
Yeah, so in the Bitcoin case, how it would work is as follows. So if you recall in the, let's look at the Algamal-based WEG, right? There is this decryption key, and the commitment to the decryption key, the verification key, is basically a group element multiplied by this the decryption key. So this is actually a relation, right? With a witness and a problem instance, and you can design an adapter signature for this relation. And then how it would work is essentially, in order to, so the client is gonna lock some money, and this money will be, the client will be able to take this money after some time lock if the server doesn't exist or if it disappears. But if the server is actually there, the server will need to post two things to retrieve this payment from the client, the locked payment. First, it needs to post a signature under its own say secret key, like secret public key. Second, it needs to post an adapter signature. And how it's gonna get the adapter signature, and basically it's gonna get a pre-signature from the client, and the server will need to adapt this pre-signature. And while it's adapting this pre-signature, the pre-signature will be revealing this decryption key. And then the client now can read the decryption key from Bitcoin, perhaps the mempool, and then decrypt the ciphertext. So that's how the adapter signature solution would work. Is that clear?
Yeah. Thank you.
Okay, if there are no other questions, let's thank the speaker again. Our final talk of the session is entitled Cadabra, Adapting Kademlia to the Decentralized Web.
Hi, everyone. My name is Ringqi. I'm a fourth-year PhD student at The Ohio State University. And this summer, I'm working as a research intern at Stellar Development Foundation. Today, I would like to introduce you to Cadabra, an algorithm that adapts Kademlia for the decentralized web. This paper was originally published in Financial Cryptography and Data Security 2023. And the work was done by me and my PhD advisor, Professor Shailesh Bojavankarakrishnan at The Ohio State University. At the beginning of the new century, we saw a lot of attention on decentralized web and peer-to-peer networks. However, back then we did not have enough computing resources, and we did not have enough network bandwidth. And then the hype went away for quite a while until recently, as we gained more computing resource and network bandwidth, and also the idea of blockchain has emerged. We saw a bunch of decentralized web applications. And decentralized web has once again grabbed our attention. We have all kinds of applications, including social networks, healthcare, payment system, financial applications, and most importantly for today's topic, we have data storage and retrieval. So in a traditional web, a centralized web, data storage and retrieval is handled by CDN and cloud. CDN stands for Content Delivery Network. And they work similarly. The key difference is that CDN servers are very close to you, while cloud services, their servers are further away from you. Cloud services provide computing resources and also storage. Content Delivery Network, as you have probably guessed from its name, provide content delivery. For example, Disney Plus uses a third-party content delivery network. And suppose Fox upload the latest episode of Family Guy today, then it should be equally efficient for you and someone in Japan to retrieve the latest episode thanks to Content Delivery Network. And today we focus on decentralized data storage and retrieval. In decentralized data storage retrieval, they usually rely on a peer-to-peer structure. And anyone in this network can serve as a node, can serve as a server, and data can be stored almost anywhere. Statistics show that we have a bunch of peer-to-peer storage systems, and they are getting more popular these days. We will discuss more about P2P data storage and retrieval, its problems, and how we handle them later in this presentation. So no matter we're talking about decentralized data storage and retrieval or centralized data storage retrieval, the key challenge here is to locate and retrieve the data. Statistics show that 25% of users, they will abandon a website if the loading time is greater than 4 seconds. And personally, for me, if a website is loading forever, I'm just going to close it, unless it's my university login page, in which case I have no other choice. And 46% of users, they will not visit poorly performing website ever again. 1 second in delay would reduce your customer satisfaction by 16%. A term used to describe this is called bounce rate. The bounce rate tells you that the longer time your website is taking, the more customer you're going to lose. As for P2P storage, the same works the same way. If your P2P storage takes a long time to execute a request, then people is not going to use your P2P storage service. Most P2P storage systems today, they are based on a distributed hash table protocol called Kademlia. And interplanetary file system, IPFS, is an example of such systems. Suppose we have user Alice and Bob, and we have a bunch of P2P nodes. Here in this figure, these nodes are actually interconnected. We ignore the connection for illustration purposes and for clarity. And for every node in this system, you're supposed to connect to some other nodes, and you store them in your routing table for future use. Suppose Alice connects to 3 nodes here, and similarly, Bob connects to 3 nodes. And now Alice says, I would like to share this file with content identifier XYZ. The way it works is that Alice will talk to one of her neighbors, and this neighbor is supposed to have a node ID that is close to this XYZ. And if this is not the closest node to XYZ in this network, then that node will try to talk to someone in their bucket, in their table, and we repeat this process until we find the node that is closest to the content identifier XYZ. Their node ID should be closest to XYZ. And later Bob said, I would like to get the file with content identifier XYZ. So Bob would repeat this process. He would talk to someone, and that someone will talk to someone until we find this particular node. And this node will tell Bob, hey, I see you want to get this file with content identifier XYZ. You should talk to Alice. So Bob will send a request to Alice, and Alice will share a copy of this file with content identifier XYZ with Bob. So that's a oversimplified version of how IPFS works. And so far, everything seemed to work great. However, in a P2P network in general, many factors can affect the routing efficiency of a node. This includes, but not limited to, location of that node and its computing resources and also network bandwidth. The big issue here is that the MLS routing table, they are randomly chosen. And suppose here we have Bob again. We mentioned that Bob will need to include some nodes in his routing table. And as we have here in the thought bubble, nodes populate their routing tables randomly. In other words, nodes, they are completely agnostic of the environment they belong to. So just to illustrate why this random node population is such a problem, we have some example as to-them queries. And suppose we have a source node in California and a destination node in Texas. Since we populate our routing table randomly, you'll probably need to talk to someone in Tokyo, Japan, and they also populate their routing table randomly, so they'll probably need to talk to someone in London. And that London node will probably need to talk to someone in Sydney, because they also populate their routing table randomly. And finally, the query reaches back to the States and gets to its destination. As we can see here, this zigzag path is very unnecessary, and it creates a lot of overhead for this query. So we just had an example of a zigzag message routing path, and that's not the only issue. In Tadamia, we could also see a path that worked like this. Suppose, again, we have the source node in California. And this time, the destination node is actually in Asia, in Singapore. So now you route the message to some node in London, and that node route the message to Singapore. So it's just 2 hops. It looks fine. It looks straight and simple. However, in a P2P permissionless system, anyone can join the network. And you could have a very slow London node. It could be for any reason. Maybe they have a crappy machine, or maybe they don't have good network bandwidth. And for any reason, this London node could be very slow, and this slow London node can slow down your entire query process. So the goal of Cadabra is, our algorithm is to configure routing tables such that the lookup latencies are minimized, and also nodes are secure against all kinds of attacks. So here we have a node, and we know that our routing table is limited. We only have this much memory. So how would I pick nodes? How would I make smart decisions on the node I choose to include in my routing table? Before we delve into the details of Cadabra, let's summarize it. Cadabra is the first effort to accelerate distributed hash table protocols via a data-driven approach. And Cadabra automatically adapts to heterogeneity and dynamism in P2P networks. Our algorithm is motivated by the multi-arm bandit problem. We will explain this later in this presentation. And we use novel exploration strategy. Cadabra is completely decentralized, and it's secure against Sybil attacks. From the evaluation perspective, Cadabra achieves between 15 to 50% lower lookup latencies compared to state-of-the-art baseline algorithms. And just to put it in a nutshell, Cadabra algorithm nodes, they measure the lookup latency, and we will utilize the lookup latency to find the most suitable peer configuration for themselves. This is just an oversimplified description. There have been many prior works that focused on speeding up distributed hash table protocol. This includes both Cadamlia and other DHT protocols. Some of them focus on location awareness. The most famous papers from this one is probably proximity routing and proximity neighbor selection. In proximity routing, you would populate your routing table like you would normally do in Cadamlia protocol. However, when you route messages, you find peers that are closest to you. In proximity neighbor selection, you would populate your routing table by finding the closest peer in the network, and when you route messages just like you would normally do with Cadamlia. Then we have parallel lookups. In parallel lookups, you send out multiple copies of your request, and since you send out multiple copies of your request, normally one of them will get back sooner than others. And we also have recursive routing. When the Cadamlia paper first came out in 2002, the authors focused on iterative routing, in which for every hop, the message initiator has to talk to the nodes on the path. However, with recursive routing, as an initiator node, you don't need to talk to the nodes on your path by yourself. And last but not least, we have caching. In caching, the nodes cache the popular items in the network, and they store them. Since the items are popular, people will look up these items in the future, and you cache them, so it should be more efficient. So the issue with these prior attempts is that they did not completely solve the problem. Some of them are inefficient. Some of them are vulnerable against attacks. And here we have some details about the DMLA DHT as a background, so we can introduce the details of our algorithm. So each node in a DMLA network is assigned a 128-bit pseudo-random identifier called node ID. This length can be some other number, but most often people use 128-bit. And routing tables in a DMLA network, they consist of sub-tables called K-buckets. The data stored in K-buckets include node IDs, node IP addresses, and port information. So here we have a toy example of a DMLA node. We use a 4-bit pseudo-random identifier as a toy example. And the number of K-buckets you have is determined by your node ID length. Here we have a length of 4-bit. So we have 4 K-buckets. And the most important thing here is that you can only store nodes that share the I-1 prefix. However, the ith bit must be different with you in the ith K-bucket. And let me repeat that with an example. Since your ID is, since the toy example ID is 1101, and for your first K-bucket, you can only store nodes that start with a 0. And for your second K-bucket, that corresponds to the second bit. Since this is a 1, you can only store nodes that node ID start with 10. And another thing to notice that for your last few K-buckets, you won't be able to have key items. As we mentioned earlier, we need to look up content. We need to look up items in a DMLA, a distributed hash table. And suppose, again, we start from node 1101. This toy example explains how lookup works. We want to look up item 0101. And we go into the routing table of node 1101. And since the target starts with 0, we go to the first K-bucket, and we find the node whose node ID's XOR distance to the target is smallest. That will be node 0110. So we talk to node 0110, and from their K-buckets, since the target node has node ID 0101, we go to the third K-bucket of node 0110. And fortunately, the target node is actually in the K-bucket of node 0110. So we find the target within 2 hops. And we get a response from that target node. As we mentioned earlier, Tadabra is inspired by the multi-arm bandit problem. In Tadabra, we treat the routing table configuration problem as a multi-arm bandit problem. And if you're familiar with reinforcement learning, you should know this figure very well. So in a classic reinforcement learning model, you have the agent, and then you have the environment. The agent does something that affects the environment, and the environment will give you some feedback. And you can repeat this process and repeat the learning process, basically. In Tadamlia, it turned out that we can map everything to this classic reinforcement learning model. We have the nodes, which are the agent, and we have the rest of the network, which can be considered the environment. And when you configure your routing table, you're actually doing these actions. You're actually taking these actions. And the actions you take, they will affect the rest of the network, which we consider to be the environment. And the environment will give you the feedback, the reward, which we consider to be the lookup latencies. And in the naive approach, in the classic reinforcement learning example we have here, the issue is that if you map everything in Tadabra to this classic reinforcement learning model, you could have a huge number of P2P nodes, and the action space could be huge. How do you deal with this huge action space? So the answer to that is actually quite straightforward. In Tadabra, each K-bucket is treated as a subspace, and we consider subspace as independent problems. And going back to our toy example earlier, we have node ID of 4 bits. That means we have 4 chip buckets, and each of them is a subspace, and we treat subspace as independent problem. We focus on them one at a time. So now we have the background. Let's delve into the algorithm of Cadabra. In Cadabra, the chip buckets store a list of candidate peers. And note that for this algorithm thing, we are focusing on one particular chip bucket. So at the end of an epoch, if the next epoch is an exploitation, then the chip bucket runs the epoch with current peer configuration or previous peer configuration, depends on which one has better bucket score. And if the next epoch is exploration, the chip bucket replaces the worst scored peer with a random peer from the candidate list we just mentioned. And the chip bucket keeps track of the bucket score of the current and the previous epoch. And where do we get the peers in the candidate list? When there are queries that either initiated by you or routed through your chip bucket is going to store this data pertaining to unseen peers, and you will add them to the candidate list. So at this point, you will probably have 3 questions. Let me answer them before you get a chance to ask me. So what is an epoch? An epoch, in Cadabra, we make decisions. We make decisions after a certain number of queries, and we consider the time between queries, between decisions as an epoch. And also, what is the score? The score basically captures the promptness of receiving a response for a query. If it's a score for a particular peer in your bucket, then it's the promptness of getting a response from that particular peer. If it's a score for a bucket, we call bucket score, then it's basically the sum of the individual score from that entire bucket. And finally, how do you know if next epoch is going to be exploitation or exploration? Here we have a user-defined epsilon parameter. You can set the parameter to determine how frequent you want to explore or you want to exploit an existing peer configuration. And here we use an example to explain how the learning process works in Cadabra. And now remember that we are focusing on one particular node and one particular chip bucket of that node. Here we are focusing on the ith chip bucket of that node. And remember that an epoch represents a certain number of queries. So suppose we have an initial peer configuration with 4 nodes, A, B, C, and D, and we have a bucket score of 65. It's basically the sum of all the individual peer score. And we know that the next epoch is going to be an exploitation epoch. So after n queries, we have a new bucket score of 68, and we use an existing peer configuration. And then we know that the next epoch is going to be an exploration. So we basically replace one of the worst scored peer within that chip bucket. And in this particular case, we are replacing node A with node E from the candidate list. And now it's giving us a bucket score of 72. And our next epoch is going to be an exploitation epoch. So we use one of the existing peer configuration. And for illustration purposes, I'm using the configuration from the previous epoch. So now we have a bucket score of 71. And here our next epoch is, again, an exploration epoch. So we replace one of the worst scored peer, which is node D, and we replace it with someone from the candidate list. So now we get a new bucket score of 78. And again, we have an exploitation epoch. We use one existing peer configuration, and we get a new bucket score. So basically, we repeat this process to learn to find a better peer configuration for your routing table. And we repeat this process to improve the routing efficiency of a node. As for the security, a naive way of sampling peers from the candidate list would be picking peers with smaller round-trip time, just like proximity neighbor selection would do. However, we don't like the naive method because proximity neighbor selection does not work well under certain scenarios. They do not adapt to the heterogeneity in the networks. And proximity neighbor selection is very vulnerable to Sybil attacks. In Cadabra, we have a user-defined security parameter rho. And when you sample peers, the round-trip time between you and that peer must have a round-trip time greater than rho. So the intuition here is that we want to sacrifice a tiny bit of efficiency for a lot more security. if I'm sampling you from my candidate list, if you're fast, then I like you. However, if you are too freaking fast, then I don't like you. As for the evaluation, we have two simulators. On the left, we have a square simulator in which we put 2048 nodes randomly in a square. And for the right, we have a real-world simulator in which we grab the data from Ethereum node tracker, and we map all the nodes to their real-world locations. As you can see here, most nodes are in North America or they are located in Europe. Some of them are located in Asia Pacific. So the model we used in the evaluation, we focus on recursive routing because it's more popular nowadays. And for a routing path with node V, U, and W, with node V being the initiator, and node U being the intermediary node, W being the destination node, we calculate the round-trip time with this following formula. L of xy is just the latency of forwarding a query from node X to Y. And delta X stands for the latency of uploading value over the internet at node X. And here we have the evaluation result for the square simulator. As you can see on the left figure, Cadabra significantly outperformed proximity routing and Valena Tademlia. In this case, proximity neighbor selection actually outperformed Cadabra. This will no longer be the case in the real-world simulator. And on the right, we have Cadabra running for 10 million lookups. For the first 1,000 lookups, we have them in blue, and for the last 1,000 lookups, we have them in red. So this bar chart shows you Cadabra improved the routing efficiency of all the nodes in the network. And here we have the same result for the different evaluation in the real-world simulator. For the real world, we have Cadabra outperforms all the baseline algorithms, including proximity neighbor selection, because proximity neighbor selection does not consider the dynamism in the network. And you can totally have a node that is performing very well at this time, at time t, and at time t plus delta, this node is not performing well for certain reasons. And again, on the right, we have this bar figure that shows Cadabra improve the routing efficiency of all the nodes as time goes by. So those are the actual lookup paths of the same query for different algorithms. We show them here as an example that explains why Cadabra works well in the routing process. First, we have Valena Tademlia. It's the first baseline algorithm. And in Valena Tademlia, we only have 2 hops. However, the intermediary node can be very inefficient, and it gives you a latency of 24,000. And then we have proximity routing. In proximity routing, you populate your routing table as you would do in Valena Tademlia. When you route messages, you find the node that is closest to you for the current hop. The thing is that you populate your routing table the same way as Valena Tademlia do, and it could be very likely that you include a bad performing node in your routing table. And then we have proximity neighbor selection. In proximity neighbor selection, you populate your routing table first by selecting the peers that are close to you. And when you route messages like you would do in Valena Tademlia. The thing with proximity neighbor selection is that you only focus on your current hop. If your current hop is performing very well, then you choose it. However, you don't care for the future hops of this message. And here comes Cadabra. Cadabra chooses neighbors based on their overall performance, not only for the current hop, but also for future hops. And we also evaluate Cadabra in many other situations. In the presentation, we focus on distributed hash table, but in the experiment, we also did T-based routing. And we also did iterative routing, although we focused on recursive routing. We tried hotspot, in which some resources are more popular than others. And we also have skewed network bandwidth, in which some nodes are slower than others. This is actually very common in the real world we live in. And then we experienced with unstable networks. We introduced a noise parameter to the node latency and see how Cadabra performs in an unstable network. So in a nutshell, our results suggest that Cadabra outperforms all the baseline algorithms in most situations, and it provides better security. And if after this presentation you don't remember anything about Tadabra, I hope you at least get this takeaways. So first, Tadabra is a simple data-driven algorithm for peer-to-peer configuration. And Tadabra adapts to heterogeneity and dynamism in P2P networks. Finally, Tadabra is secure against common attacks. As for future work, we want to test the performance of Tadabra in real-world networks. And we would be happy to see some thorough analysis of Tadabra's robustness against attacks. And last but not least, it'll be interesting to do a better theoretical understanding of Tadabra. We believe this can be done using series from network potential games. And it'll be interesting, specifically, it'll be interesting to analyze the social cost of Tadabra in a local connection game. So this basically means, suppose you have a central controller of the Kademlia network, then you can basically give a optimal peer configuration for every node, and every node has to listen to this central controller. What if you don't have the central controller? You basically have a price of energy in which you want to compare the optimal result you can get from the central controller versus everyone do this in a decentralized way. And that's it. Thank you for your attention. Please check out our papers. For the QR code on the left, we have Tadabra. And for the QR code on the right, we have our recent paper about blockchain data sharding using P2P random walks. And now I would like to take any questions you have.
Okay, thank you. This is a really cool idea, and I'm just being devil's advocate here, but in the real world, does this end up where only, say, like AWS nodes end up being, the data only gets routed through them because they're always going to have the better latency than everybody else, and then like edge nodes operated by people never get routed through?
It depends on many things. So like, it also depends on what things you're looking for. Like people have different interests. Some like there are many popular videos on YouTube, right? But you can have different categories, and it's not like some companies they are gonna take charge of this entire thing. But it depends on what your subfield is. Yeah. So like, we hope there will be big companies, but big companies won't be able to take the entire thing off this Tadabra network.
Yeah. Thank you.
Hi, Pradyum Shom, Flashbots and Georgia Tech. I had a question about censorship resistance. Could you say anything about how this could, prevent some parties from making some content inaccessible?
So like for censorship, are you saying that you can eclipse a node, like block all the information that's coming through that particular node?
Right. If you don't want some pieces of content to be accessible in certain regions or by certain requesters.
Yeah, that's actually the Sybil attack we tested in our simulation. So we have this security parameter that prevent you from being taken by a Sybil group. And I mean, if you're a Sybil group, you want to get into the key buckets of your victim node. However, since we have this security parameter, even if you're performing good, you won't be able to completely take over the routing table of your victim node.
Thank you.
Yeah.
I have a question about, so one of the big problems we found with Kademlia was that it has very poor resistance to Byzantine nodes, so nodes that actively attack the network. Because, for example, it's very hard to detect them because an honest answer can always be, here are more nodes that you can query, and a Byzantine node can simply just always send more Byzantine nodes. Does Kadabra have any resistance to this, and what percentage could it tolerate?
Yeah, that's a very good question. We actually considered this during our experiments. So if you think about malicious nodes, if you think about Byzantine node, what are Byzantine node? If you can help me achieve my goal, are you still a Byzantine node? So if you have a bunch of Byzantine node in this Kadabra network, and you can efficiently help me find my resource, my target, then I don't care if you're a Byzantine node, as long as you can get a good response for me. However, if you cannot get a good response for me within a reasonable amount of time, then you're not a good node. I won't include you in my routing table. So in this paper, like, how do you define Byzantine node is a question. Like, if you can do good things for me, then I don't care if you're a Byzantine or not.
Okay, let's thank the speaker again. We're now on break, and we'll resume at 4 p.m.
Welcome back, everyone. I'm looking for the speaker of the first speaker of the session. Oh, yeah. Oh, sorry. All right, welcome back after the break. I found the speaker. Good news. So even better news, this is a session about MEV, minor extractable value. Yeah, the very first talk will be by Fan. He is assistant professor at in the computer science department of Yale University and is doing really groundbreaking work in the space of MEV, oracles, and decentralization in general. And he'll be speaking today about decentralization of the Ethereum builder market. Welcome, Fan.
Oh, thanks for the kind introduction. Right, this talk is about the decentralization or the lack thereof in Ethereum's builder market. Why do we care about decentralization? Well, if there's, we were to summarize what makes blockchain special, in one word, that's going to be decentralization, right? The system should not be controlled by a handful of entities. But the natural question is, how are we doing on decentralization in practice, right? In practical systems, are practical systems like Ethereum decentralized in all important aspects? So this session is about MEV, and the MEV is considered to be an important threat to decentralization. Just quickly talk about what MEV is. MEV refers to the profit from manipulating transaction ordering by injecting, deleting, or reordering transactions, etc. So this is a pretty significant amount of profit. To give you a concrete sense, you can think about something like $1 million per day at the high point. This value varies, of course, but it's a pretty significant amount. The concern that MEV brings up in terms of being a centralizing force is the following. So this significant profit is not equally distributed across validators or participants in the consensus protocol, all right? Because big validators can perhaps extract MEV better than small validators. So the concern is that most of the MEV will be extracted, earned by big validators, and the smaller ones will be driven out of the market. So this threat is recognized by the blockchain community, and the Ethereum community in particular is actively engaged in mitigating it through a mechanism called PBS, or proposer-builder separation. That's where this builder market is introduced. So the idea in PBS is, well, the challenge with MEV is that not all validators are equally well at extracting it, are equally good at extracting it. So why don't we introduce a specialized service that extracts the value for validators? So what they introduced is a market of builders. So when a validator is up for proposing a block, instead of building the block by him or herself, the validator goes to the market and asks for these builders to propose, to build a block and to compete for including that block in the blockchain. Essentially, this is an auction where the builders will bid for including the block in the blockchain. And the proposer naturally chooses the most profitable block, paying the highest. This system has been in operation since 2022. And ideally, if the builders market is competitive and the builders compete with each other, what they will do is they will essentially give most of the MEV away in the form of profit, auction revenue. Right? Ideally, proposers do not need to do much. They can then collect most of the MEV in the auction revenue, and therefore this system is meant to level the playground of validators. All right? But how is the builder market functioning? How is it fighting decentralization, fighting centralization? So the answer is rather unclear, because the builder market itself now is hyper-centralized. So this graph plots the market share of different builders over time. You can see a kind of a clear trend towards less variety of colors, which indicates a concentration of market share towards just a few entities. As of March 2024, which is when we plot this graph, 3 builders are responsible for building 90% of the blocks in this builder market. It's a hyper-centralized builder market. So the natural question is this centralization okay? It's thought to be okay by the community. I'm quoting this blog post from Ethereum.org. Basically, the argument for it being okay is that we don't really care about the block builder centralization. What we want is proposer decentralization. As long as that is the case, it's okay to have a builder market that is centralized. We are not convinced by this argument. That's why we did this study. Our concern is that builders and builder market and the proposer they're not exactly independent. The proposer will incur a loss in their revenue when this builder market is not competitive enough, not efficient enough. And the concern is that this profit loss incurred by the proposer is going to have some undesired consequences. The first consequence is what we call instability of PBS. Right? When proposers do not get enough from this market, what they will do is they will go ahead and start building blocks by themselves. And this takes us right back to square one, because now the proposers and the builders, proposer will start to function as a builder. They are incentivized to build blocks by themselves, thus reintroducing the centralizing force that PBS wants to avoid. The implication number 2 is there are various proposals building on top of such MEV auctions, proposing to maybe burn some of the MEV or redistribute the MEV, and they are effectively using the auction revenue as an indicator or an oracle for how much MEV there is in the system. So proposer's loss translates to inaccuracy in this oracle. Right? For example, in MEV burn, for example, if this oracle is not accurate, that means you may be burning less than what you should have, what you should be burning. So in this talk, I will present the results we find in this empirical paper. We want to quantify the loss incurred by the proposers. We want to understand the causes, and we want to explore ways to mitigate the loss. So let me just quickly introduce some notation so we can talk more precisely. In each instance of MEV auction, builders will submit a bid in the form of a block B and the bid value BV. We denote the true value of each bid, the TV of B. True value of the bid means the balance increase after executing transactions in B. So TV of B is what the builder will actually get in the pocket if B is included in the blockchain. So when the auction concludes, the block with the highest bid value wins the auction. The block is added to the blockchain. Builder of B gets the true value, and builder pays the proposer the bid value. So the difference between the true value and the bid value is what the profit pocketed by the proposer. So usually the bid value is lower than the true value because the builder wants a non-zero profit. Okay, so now after understanding this mechanism, we can talk about the potential concerns. Why are there, what are the potential reasons for proposer losses? The first one is about the first question is whether the mechanism itself actually incentivizes competition. Does this round-based auction incentivize competition? So there is reason to say yes, because it is akin to English auction, which has nice properties in terms of encouraging competition. But there's also reason to say no, because MEV auction is not exactly English auction, which doesn't have a deadline. And for MEV auction, you do have a deadline. And also, when there are only 3 major players, there's a concern that they may collude or they may coordinate in other fashions to reduce the competition. So that's the potential reason number 1. Another reason is a little bit more subtle. So that's another reason that the proposer may incur a loss is because builders, the bidders in the system, may have very different block building capacity, or BBC. This is better explained in an example. So suppose Alice can extract 100 ETH in a given slot, Bob can extract 10, Charlie can extract 9.5. Okay? Assuming the auction is completely competitive, then Alice will win the auction bidding slightly over 10, right? 10 plus epsilon. So, but what the proposer gets in this process is still far from 100. Proposer will get 10 plus epsilon, but the proposer could get up to 90 ETH more if they were building the blocks by themselves. So in that sense, proposers incur a loss because of the inequality of block building capacity. So there are 2 types of losses, one from uncompetitiveness and one from inequality. So these are the 2 types of losses we want to kind of look closer at. Put it pictorially, if in a given auction, if you know all the true values behind all the bids, and you can put the true values on this axis from low to high. So here TV1 is the highest true value, and the TV2 is the second highest true value, and so on. Then if the winning bid of this auction is below the second highest true value, we call this auction uncompetitive, right? Because in a competitive scenario, the winner should pay at least higher than the second highest true value. So the amount, the difference between the second highest true value and the winning bid, if the amount is positive, that's a loss from uncompetitiveness. And the loss from inequality is the difference between TV1, the highest true value, and TV2. Because even in a completely competitive auction, the proposer is gonna get a little bit more than TV2, but not TV1. Auction is not going to generate TV1. But if the proposer build blocks by themselves, they could potentially get TV1. So the difference between the 2 is the loss from bidders' inequality in block building capacity. Okay, so then we went ahead and quantify these 2 types of losses. So as you can see, if you know the true values of all the auctions, then computing these losses is a matter of simple arithmetics. But a practical challenge is that the auction data itself is not recorded on chain. Blockchain only records the winning bid. But to do that arithmetic, you need losing bids as well. So to enable this study, we archived the auction data since 2022, and we obtained an auction data set from ultrasound relay with not only winning bids but also losing bids. These 2 data sets enables our study, and we tried our best to cross-validate the data set with other papers and the other available data set to make sure it's representative. Let me jump right to the results. Okay, first the question is, in the past MEV auctions, are the auctions actually competitive? By competitive, I mean the winning bid is greater than the second highest true value. It turns out that 90% of the auctions were competitive. All right? We also looked at a definition of allocation efficiency. Auction is efficient in this definition if the winner of the auction has actually the highest true value. Interestingly, only 80% of these auctions are efficient. That means there's 20% of the auctions won by parties who do not have the highest true value. All right, and there are 70% of the auctions that are both efficient and competitive. So that's first set of results. Were the auctions competitive and efficient? Second set of results is we looked at the inequality of block building capacity. Right? Are builders equipped with similar capacity to build blocks? So to do that, we looked at the true values of the bids. And we used various statistical metrics to plot the disparity of the true values. And this graph in particular shows a metric called the QCD. The larger the QCD, the worse the inequality is. You can see that the x-axis is for different builder groups, top and the middle and the tail builders. And different color represent the different MEV size of MEV in a given slot. So you can see that within each builder group, inequality gets worse when the MEV gets, when there's more MEV. So top builders tend to have similar block building capacity when MEV is low. But when MEV is, high, then the inequality worsens. And across the board, there's an inequality worsen trend as we go down the list of the block, the builder. So tail builder, for example, has much worse inequality than top builders. Okay? So the takeaway is, builders do have drastically different block building capacity, even among the top builders when the MEV is high. Okay, the third set of results is, ultimately we care about the loss. That's what I motivated the talk with. So we compute the loss, two types of the losses. Here's the result. Okay, so the loss from uncompetitiveness turns out to be quite small, despite that, about 10% of the auctions weren't competitive. But the loss is moderated, it's about 1%. But on the other hand, the loss from inequality in block building capacity is a lot more significant. The percentage is around 6 to 12% in the range of our study. For example, give you a concrete sense, in April, in this week of the April in 2023, the profit in MEV is 2,700. Losses from uncompetitiveness is about 47 ETH, but the losses because of inequality is 312 ETH. So if there were not, if there were no inequality, then the proposer could have earned 300 ETH more. Okay. Right, so the takeaway is that the two types of inequalities kind of manifest itself in the loss quite differently, with this inequality causing a more significant loss. So then we want to understand, right, what caused the inequality. So this has to do with how builders build their blocks. Builders' job today is they accept the transactions from various channels. These channels, some of them are public, some of them are private, and then they come up with a block by kind of identifying the best combination of these transactions from these channels. The important distinction between these channels is that some of the channels are public and some of them are private. The public channel is available to all builders. Private channels are sort of the secret information available only to a specific set of builders. So the answer to this question is the reason that caused the inequality is largely due to access barriers to profitable order flows. So profitable order flows can only be accessed by a small set of builders. And the more interesting takeaway is the reasons behind the access barrier. We observed two reasons. First, there's a kind of a trust issue between searcher and builders. And second, a more concerning reason is that there's an incentive for them to form exclusive relationship. I will now talk about each briefly. Right, so order flow providers do not share with their private orders about any builder because they don't trust the builder, because this mechanism doesn't protect the order flow providers from malicious builders. Usually, order flow providers resort to either the reputation of the builder, or they have to just hide their identity from the public to achieve this obscurity for security. So because there isn't really a fair exchange mechanism between the order flow provider and the builder, the order flow in some sense cannot flow freely. And platforms like MEV Share aim to address this problem by providing this fair exchange mechanism, but the systems that we have today are still centralized. So that's the first reason for integration, for inequality. The second and the more concerning reason is this phenomenon called integration. We observed that order flow providers sometimes form an exclusive deal with a builder, right? They only send their order flow to a specific builder, not others. To identify such integration, we proposed a metric called the pivotal level, and we identify these integrations through the auction data. We find that the top three builders, all of the top three builders who collectively win more than 90% of the market, have integrated order flow providers. Interestingly, we kind of reveal a previously unknown integration between a Telegram bot and the builder Titan. The reason that integration is more concerning is because there's a strong incentive to form integration. For one, integration gives the builder a unique advantage in the auction. Because if you think about it, if an order flow is available to everyone, then in the auction, this is not really an advantage because everyone will raise their bid. But if you have some private information, that's truly your advantage. The second reason is that by forming the integration, this pair of parties can avoid the competition. Let me illustrate that with a real-world example. So in this particular slot, the Flashbot's banana gun, there's a profitable order flow of 340 ETH coming from this order flow provider, and this order flow was given to multiple builders. So this graph shows the auction bids of different builders. It's a little bit, it's not legible, I know, but because everyone bids, all these builders bid close to 340, then most of the value is captured by the proposer, the auctioneer. Well, then you would think, a rational, participant would think, why do I send it to everyone and it sort of cause this contribution? I could have avoided it by sending it only to one builder. That's indeed what happened in a later slot. Another very profitable order flow from Banana Gun arises again. It was sent to only one builder, Titan. And this time, Titan doesn't need to bid crazy high to win the auction. Titan paid only 80 Ether to the proposer. The remaining 128 is sort of the surplus of this integration. you can imagine the kind of two ends of the integration can share this surplus. So the result is integration leaks this MEV out of the system. They are not captured by the proposer. They are not captured by the protocol. They went to the builder's pocket. Right, if you think, look at the game, you would think that the builders should earn epsilon in a perfectly competitive market, but actually top builders earn a lot. In the first week of June, it's a particularly good week for the builders, but these top 3 builders made $5.5 million. That's more than epsilon. Okay. Right. Let me summarize the 3 results I presented pictorially. So we started with this phenomenon of builder centralization. We observed the 2 reasons that could contribute to builder centralization. That's the trust barrier and the integration. Then what's the consequence of builder centralization? Well, that's the loss of a proposer's revenue. This could lead to instability of PBS. And in the long run, if we don't have PBS, or if the PBS is not stable anymore, then the problem that PBS wants to prevent will become problematic again. Proposer loss also lead to inaccurate MEV oracles, which affect the subsequent protocols that rely on the auctions as an oracle. Builder centralization also has other more immediate problems like censorship, which is an important problem, but out of scope for now. I think the very hard problem and a concerning problem is this self-loop. Integration has a strong incentive to stay. And if the root cause of centralization has a self-loop, then this it's a hard problem how to stop the worst thing from happening. Do I have a couple minutes? Yeah, I can. I don't have a I don't have a solution to the problem, but I have solutions to the pieces of the puzzle. Let me quickly talk about them, and I invite everyone to kind of think about this problem. So one problem is the oracle is not accurate if you take the auction revenue as the oracle. But there's might be a potential solution. There's alternative mechanism that might be truthful. All right, this AFT paper in particular proposed a mechanism that can be shown to be truthful under certain scenarios. Another problem, the trust barrier, can be potentially solved by running some software in trusted execution environments. Right, this is something Flashbots is doing already. And you can imagine combining the 2 ideas, right? You can run this truthful mechanism in the TEE, and then you get the best of both worlds. But it's not so simple because this mechanism is only truthful assuming a monopolistic builder. That's one way to put it. So simply running it in TEE doesn't guarantee this property. So to conclude, I would just conclude with a list of open questions. This paper really is more about asking these questions and explore the kind of first steps of mitigation. But we don't have a solution, and I think it's an important problem to think about and to work on. We have a blog post and we have an e-print, and I'm also active on Twitter. So if you have any ideas, I'm happy to chat about it. Okay, thanks. That's the talk.
Thank you, Fan. Any questions for Fan? Yeah, go ahead.
Hi, thanks for talk, very comprehensive. So I have a question here is, the analysis really based on like how do you evaluate the true value here, which I personally think it's usually like a hidden value that is not public to all. How do you determine what is the true value for each block, and how do you analyze that? Thanks.
Yeah, that's a great question. So by true value, what we can feasibly get is the lower bound on the actual profit. So the off-chain profit, for example, cannot be learned from on-chain bids. So in the paper, we discussed the implication of having an overestimate or an underestimate of the true value. But we felt this is a kind of approximation, but it's also a standard approximation adopted by virtually most of the analysis like this. So long story short, I think the insight, most of the qualitative insight should still hold because it's consistent with others' findings as well. But it is correct that it is a lower bound, and we don't claim this is the accurate true value.
So basically, you're saying like the actual situation may be even worse than the current results you have shown.
Sometimes some results could be worse, some could be better. It depends on which result you're referring to.
Yeah, because the main situation I'm really concerned about is the example actually you listed that Alice can extract 100 ETH and Bob can only extract 10. Like if you cannot capture that like 90 difference, it may seems to be a large problem in the analysis.
Yes. So if that the inequality we measure is due to it's due to some option profit, that could be problematic. But we also think that in examples like these, the type of profit we're talking about is from priority fees. So so it doesn't really involve option values.
Thank you.
Very good. One more small question. So you mentioned there's a need for subsidy, no, for newly entrant block builders. Can you give us a rough estimate of how much that would be?
Good question. So I think in our estimate, the rough number is around a few ETH, I think, to sustain a market share of 1% for a week. And that's, I think, some builders' requirement for you to receive order flow. This 1.4 ETH is not a big number in the absolute sense, but if you compare it with the revenue of kind of long-tail builder, then that seems to be a relatively big number. I think that's in the range of our study.
Yeah, cool. Thanks a lot for quantifying this for us, no? For the community. This is fantastic. Thank you, Fan.
Okay, thanks.
All right, so the next talk will be again about order flow, in particular protected order flow. Today's speaker is Kushal Babel. He's a very talented PhD student at Cornell Tech, supervised by the very unique Ari Jules, who's also here today. So yeah, thank you, Kushal. No, the floor is yours.
Thank you, Arthur, for that kind introduction. So let me tell you the story about how has the community dealt with the problem of MEV. Fan has done an excellent job in telling you the lay of the land. So there have been two radically different approaches that the community has taken. The first approach is what I call the systematization of value extraction. This approach assumes that the extraction is inevitable as validators are rational agents. And some validators have less capabilities than the other validators. So the approach just focuses on every validator having access to the most profitable block. And this is largely called as proposer-builder separation. And Fan talked about MEV Boost, which is the current instantiation of PBS. Now, the thing to note here is that often the profits that are coming to the validators are at the expense of ordinary users. And this leaves ordinary users vulnerable to systematic value extraction. So in effect, the balance of power is heavily tilted towards validators, and users are vulnerable, as shown here. And validators have enjoyed this power, right? You can see that the proportion of blocks that are built through PBS has rapidly increased to more than 90%. And this validates the assumption that validators are in fact rational players, and we should think about them in the same model. The second class of radically different approach is what I call fair ordering, which has a couple of other sub-approaches in it. The first one is temporal fair ordering, which basically decentralizes the ordering task among a set of validators based on their local timestamps at which they receive the transactions. The second one, which is complementary to this sub-approach, is called blind ordering, which orders these transactions based on just the fees that they pay, doesn't look at the contents of these transactions, and it can be enforced through either TE or threshold encryption through a committee. Now, this class of work has seen a very rapid development in the academic community, and largely this work has remained in academia with very little adoption in practice. And the reason for that is while this work protects users, well, why would a rational validator adopt fair ordering if they're getting all these juicy profits from PBS, right? So in effect, ordinary users would be happy, but validators are unclear why they should even opt into it because they are rational agents. There's also some externality here where there's latency racing for the top of the block in some of the cases. Okay. So the question that we ask in this work is it possible to build a system where you can protect users in light of the fact that validators are rational agents? And while this work is academic, I want to highlight that from the day one, we have approached this work from a very practical point of view, as you will see in the rest of the talk. So let me introduce you to the work called PROF, Protected Order Flow in a Profit-Seeking World. The mechanism for PROF is simple. It's backward compatible, means it's compatible with the current way blocks are being produced. It protects users without service degradation. I'll talk about what we mean by that in detail. And it accounts for rational validators. All right, so the summary of the design for PROF is you have the system called PROF. It ingests private transactions. These transactions, in a sense, should be sent exclusively to PROF, but if those transactions are coming from mempool, that's also fine. PROF orders these transactions in a bundle, and I'll talk about how these transactions can be ordered in a fair way, but essentially PROF constructs a fairly ordered transaction bundle. It then takes in a block, which is produced outside PROF, and then it enriches that block with the bundle, which is fairly ordered. Now, you would notice that this bundle is appended to the end of the PROF, at the end of the original block. And so if the original block gave you a reward R, the PROF-enriched block will give you a reward R plus epsilon, where epsilon is just the fee coming from PROF transactions. All right, so from a validator's perspective, which block should the validator choose? Well, there's a block B that gives you a reward R, and there's an enriched block that gives you slightly higher reward that is coming from the fees that's charged to PROF transactions. It's clear that if validators are rational agents, even if epsilon is small, they should prefer the PROF-enriched block. From a user's perspective, should the user send their transactions to the mempool, or should users send their transactions to PROF, where if they send their transactions to mempool, they are vulnerable to risk of extraction, versus if they send their transaction to PROF, they can pay an epsilon fees for incentivizing inclusion of those transactions. Now note that PROF should protect these transactions in the sense that these transactions should not be vulnerable to extraction, and I'll talk about how we enforce that. Now let me talk about the details of the design. So as I said, it's backward compatible, so let's look at how blocks are being produced currently. This is the PBS architecture. You don't have to look at the details, but the main thing here to note is that validators are receiving most profitable block from the supply chain. This is mediated through this trusted auctioneer, which is auctioning off the blocks and choosing the best block for the validator. For the purposes of this talk, you can just assume this abstract view of PBS, where there's a supply chain represented by builders here. Builders are sending their blocks to the relay, and the relay is choosing the best block for the validator. Now, the key insight in PROF is you have an alternate where a PROF-enhanced relay would just append PROF transactions to the best block coming from the PBS auction. So the best blocks are being selected by PROF, and then at the end of it, you have appended transactions. And the validator is given a choice. It can either choose the original block that is coming from the auction, or it can choose an enrichment of that block that is coming from prof, which will give its higher reward, as I mentioned. So the validator is given a choice of take it or leave it. Prof enforces the choice that if the validator leaves these transactions out, the validator learns nothing about the transactions. This is the key insight. The validator is either taking the prof transactions, or it has to leave those transactions and it learns nothing about those transactions. All right. So the question is, why should relays support prof? Well, relays are also competing in this ecosystem. They're competing to have market share of how many blocks are included through that relay. So all else equal, a relay that supports prof-enhanced relays would be more competitive. That is, they would be producing more profitable blocks for the validator, and so their market share would increase. And the workflow for builders remains unchanged. So now let me talk about the details of how we enforce the take it or leave it guarantee from prof. So this is the current PBS workflow, where there's a supply chain, some blocks are being built by builders, and they're being sent to the relay. What the relay does here is it sends a header of those blocks to the validator, which is essentially a bid that if you choose this header, it has an associated value associated with it, and if the validator commits to including that bid, including that block, which is basically a signed header from the validator, then the relay can release the full block to the validator. This is how currently the blocks are being built in PBS. So note that the validator is first committing to the block without even seeing the contents of the block. So in some sense, it's a blind commitment from the validator, and it trusts that the relay is kind of validating the block and so on. OK. So now we are ready to dive into the details of the design of prof. This is the design illustrated in a logical sense. So the prof sequencer, for now, assume is a black box entity. It sends a prof bundle to a prof bundle merger, which is running at the relay. This prof bundle merger essentially takes the best block coming from the auction, ingests it in the bundle merger, appends the prof transactions to it, and then sends that block to the validator. And while it's kind of simulating these transactions and appending the transaction bundle, maybe the auction has proceeded, maybe you have a better bid from the auction. So the relay will make sure that it sends the best out of the two, the best block from the auction and the prof-enriched block to the relay. Now, while the relay is trusted, we still want to run the prof bundle merger inside a TE because it's just good to have defense in depth. If the relay, for example, is honest but curious, we want nobody to see the prof transactions. That's why we, even if the relay is trusted, we want to run the prof bundle merger inside a TE. All right. So here's the diagram for how the timeline would proceed during the block production. You have two concurrent paths. The orange path, which is the PBS path, that's the current path, and you would have a prof path which runs concurrently to it. In the orange path, of course, you conduct the MEV auction. And in the blue path, which is the prof path, you conduct the MEV auction, but at the end, you merge prof bundle to the best block from the auction. At the end of it, you choose the best block coming out of these two paths and send the best block to the validator. Now, some of you might notice that if we run this auction a little bit, if we run this auction for a little bit shorter duration in the blue path, then that might lead to a suboptimal, a lesser block from the auction compared to the orange path. So yes, if you do end the auction a little bit earlier, there is some penalty in that sense. So for example, if you are ending your auction delta seconds earlier, and in Ethereum you have 12 seconds, for example, then you're ending the auction, you're running the auction in a sense for delta duration shorter, and we call it the latency penalty that you would incur in the auction path. Well, to compensate it, you have the fees from prof transactions. So in a sense, the block that is enriched from prof, it has a little bit of latency penalty from this bundle merging, but it also has the extra fee coming from prof transactions. So the likelihood of inclusion of these prof transactions would depend on whether the prof-enriched block is better than the PBS block, if the validators are rational. So let's see what the break-even equation looks like. You have these two competing equations for whether the prof-enriched block would be selected by the validator. So this is the latency penalty from real-world data. Here you can see that there are different percentiles for how much penalty you incur if you shorten your auction by a little bit. So for example, if you shorten your auction by, say, 85 milliseconds, then in 90% of the slots, you would produce a block which is 0.003 ETH, roughly about maybe $10, less than if you had run the auction for the full length. So this is the latency penalty which Prof needs to compensate from the fees charged to the Prof transactions. All right, so let's model this inclusion likelihood a little bit more formally. So the break-even equation for Prof, as I said, is the fees that is coming from Prof transactions, whether that's greater than the latency penalty. This fees in itself depends on the gas in the Prof bundle, and the fee charged to the Prof bundle, which is basically gamma F, where gamma is the overhead on top of the base fee F. So there's a relationship between the inclusion likelihood alpha, the gas used in the Prof bundle, which is essentially the size of the Prof bundle, and the overhead that you need to charge Prof transactions. This is inclusion likelihood that we calculate from real-world data. Here you can see that as Prof transactions, the Prof bundle gets bigger and bigger, you use more and more gas in Prof transactions, the inclusion likelihood increases for the same overhead that is charged to the Prof transactions. So the colors represent the overhead that you're charging, so 0% on top of base fee, 2%, 4%, and so on. And for that overhead, if you increase the Prof bundle size, what's the likelihood of inclusion? So the takeaway from this slide is there is high inclusion likelihood, more than 95%, for charging very minimal fee. And that likelihood even increases as more and more users adopt Prof. OK. So we go a step further. Let's look at some of the redistribution mechanisms of MEV. So many approaches in the industry have come up where they are protecting users, but they are also redistributing some MEV that was created from their transactions. So let's look at an example of how this redistribution is happening. Suppose Alice buys some ETH from an exchange, and it causes the price to go up on that exchange. An arbitrager could backrun Alice's transaction, profit off from that arbitrage opportunity, and redistribute some money back to Alice. So essentially, if the profit here was, say, $20 from the arbitrage could share some portion with the user, keep some portion for itself and the validator. So there have been these approaches that have been proposed. You could have similar approaches integrated with Prof. So the thing to focus here is you run in step 1, 2, 3 the same workflow for Prof. But then once the validator commits to the Prof block, you can actually release these transactions for backrunning to the public. And then the backrunners would compete to basically give value back to the users in the Prof bundle. So 1, 2, 3 is the normal workflow for Prof, and then you can enhance it with Prof share, where now you are conducting a backrunning auction. This is inspired from the approaches in industry, a la MEV share and MEV blocker. OK, so as I said, there are these approaches in industry that attempt to also prevent front running and redistribute MEV back to the users as well. Now, these approaches, while they are kind of attracting backrunning for these users, they still have to leak something about the user transactions in order to make it attractive for backrunners to backrun them. If the backrunners don't know anything about these transactions, how are they going to backrun them? So these approaches kind of have a trade-off between the privacy for the transactions and their attractiveness for the backrunners. And as Fan mentioned in his previous talk, these approaches are already pivotal in deciding who wins in these auctions. All right. So the other benefits of Prof share on top of redistribution to users, if you compare them specifically to the current approaches of redistribution, are as follows. The key insight here is that in Prof share, you can actually release these transactions once the validator commits to them. So the transactions are completely private. You don't have to leak anything about them until the validator commits, and then you release these transactions for backrunning. As a result, you have some nicer properties than other redistribution mechanisms. The first property, you might have guessed, is that you can now do more efficient backrunning because you know the full contents of the transactions. You can even do it off-chain. You don't have to do it through smart contracts, and it saves some gas as a result. Second, you might have noticed that when you do backrunning in the current mechanisms, you still have to incentivize by paying some cut from the profit to the validator. Whereas here, if the validator has already committed to the transactions, you can actually run this backrunning purely for the benefit of the users. So all the backrunning profits would go to the users, and you may be kind of giving, say, some epsilon value to the validator. You don't have to cut in the validator during the backrunning auction. And finally, ProfShare also has this property where the users are being backrun together. What that means is you don't have to backrun them one by one. And so as a result, users benefit from kind of organically backrunning each other. So consider the example where one user is trading, say, in the positive direction. For example, they're buying some dollars for ETH. If the other user trades right after them in the opposite direction, they would get a better price as a result. So what you want to do is backrun these transactions as a bundle, and Prof ensures that all its users are backrun together, and they get the benefit of organically backrunning each other. All right, so we conduct some utility analysis for these mechanisms, Prof, ProfShare, and some redistribution mechanisms like MEVShare, MEVBlocker, and so on. The model is you have a DEX, which is a constant product AMM. You have an external market against which arbitrageurs can arbitrage and get some profits. You start out with these markets being balanced, and then each user is trading some unit quantity in randomly either direction. Let's define a concrete parameter called demand ratio. Demand ratio informally means how much demand is there in the transactions. So for example, if all the users are trading in the same direction, you have a very high demand. If users are trading in opposite directions such that they kind of cancel each other out, you have, in some sense, a zero net demand. And as you might have guessed, if they're trading in opposite directions, which is if the demand ratio is small, you have these benefits of organically backrunning each other. So this is the utility analysis for ProfShare, Prof, and other redistribution mechanisms. You can see that ProfShare always gives you better utility than other mechanisms. There are two reasons for this. One, well, you are protecting users, so they are not vulnerable to extraction. Second, you're also redistributing any profits that are created by backrunning those transactions. So ProfShare always gives you the best utility. In some sense, it's a strictly better mechanism. Prof also does better without even redistributing things, because as you might have guessed, if you're organically backrunning each other in the Prof bundle, then you can compensate for some redistribution that way. So in low demand ratio regimes, Prof has these benefits of backrunning, organic backrunning, and you can get good utility in Prof even without redistribution. And on the right, you see that a lot of blocks fall into this regime where they have low demand ratio, in the sense that the market is not always moving in one direction or the other direction. It mostly moves sideways. So you have low demands in most of the blocks, which means it's a good regime for doing organic backrunning for the users. All right, I want to highlight some flexibility parameters in Prof. As I said, we have designed the system to be practical from day one. The first one is you can have multiple sequencers. There need not be just one Prof sequencer. You can have multiple sequencers, and in fact, these sequencers can have different ordering policies. We are not tied down to one ordering policy like, say, first come, first serve. You can even run auctions inside Prof sequencers. These sequencers can either operate concurrently, where their bundles are being merged concurrently in parallel, and you choose the best enriched block as a result. Or you could also merge different bundles from different sequencers, and you create like, a mega enriched block from different sequencers. Second, Prof sequencer here is really a black box, as you might have already seen. It need not be a centralized entity. In our prototype, we implement it as a centralized entity inside TE, but it could be a decentralized protocol like that has been proposed in the community, such as Equitas, Themis, and all those other fair ordering protocols and blind ordering protocols. So it can be a decentralized protocol that's ordering transactions fairly. So in conclusion, Prof is a simple, backward-compatible system that's designed for protecting users while accounting for the rational model of the validators. And in our opinion, because Prof leads to these win-win dynamics where users benefit as well, validators are always given the best block, relays are more competitive as a result, and builders' blocks are also more competitive because they are getting enriched. If they don't support Prof, they don't need to, but if they are working with, say, optimistic relays, they might have to merge the bundles there. it leads to win-win dynamics for all and shifts the power balance towards users. And so the endgame thesis that we have here is that transactions that want top of the block can go through the gauntlet of the auction. They can compete in these auctions. And it also has some positive effects where you kind of take out the negative externality of latency racing. So the top of the block can be auctioned off. But all the other transactions that don't want the top of the block should go through Prof because it provides them higher economic utility while also guaranteeing good inclusion for their transactions. To learn more, I would encourage you to go to the website. It has several FAQs. You can watch a demo of Prof that is landing Prof-enriched blocks on the relay by forking of the relay code that is put out by Flashbot's open source. I would also highlight that Uniswap Foundation is kindly sponsoring $50,000 for anyone who wants to help us build the Prof implementation into a more mature implementation, thanks to them. You can also track the announcements and contact if you have more questions. And the Prof paper just released a couple of days ago. I would really encourage you to check the paper. Because it's designed in a practical way, it has a lot more details. I would like to thank my collaborators, Nerla, Yan, Ujjwal, Mahimna, Khosla, Andrew Miller, and Ari Jewels. With that, I can take questions.
Oh, hello, cool. Hey, Kushal, great talk. I might have missed it, but in Prof Share, you said that the validator has to first commit to, signing the header blind before the background auction takes place. How are they able to sign over a second header that's SIG H2 without equivocating in the protocol view?
Yeah, that's a great question. So Prof mechanism requires only modifications at the relay, as you might have guessed. But in Prof Share, you have to modify the MEV boost adapter as well to be able to sign two headers, one for the committing the Prof block, and second after the backrunning auction. And crucially, if you notice here, the headers, that is step 2 and step 7, are going into the TE. And the TE enforces that it will never release two headers. It will only release one header so that the validator is never at the risk of equivocation. So yeah, that's a great question.
Okay, thanks.
Thanks. Thanks for the talk, Kushal. A couple of questions. One is on the latency analysis you did. So it seemed like the primary analysis was looking at the value of blocks through time in the slot, but that sort of is like a measure of the absolute MEV available. But one other way that latency also plays a role is in the sort of adverse selection sense. So if you look at different relays, I suspect this is the case. I don't have the data on me, but if you look at different relays, I think you'd see block builders basically shading their bids on slower relays because there you have more adverse selection where competitors going through faster relays might be able to maneuver faster than you. And so I think maybe, unless you guys already did this, one interesting analysis here would be to look at relays which are slower than others and see if people shade their bids through those as well, because I think that might be a more relevant latency analysis.
Yeah, that's a great point. So if you look at the paper, we did analysis for all the major relays. So this graph is for Flashbots, I should have mentioned. But the paper has similar analysis for ultrasound and agnostic. We see similar patterns. So you would see the same inclusion likelihoods for other relays as well.
Sure, but I'm saying across the relays, at the same point in time, are they seeing bids of equal value? I suspect not, because if you're a market maker and you have a slow avenue to getting on chain and a fast one, the fast one just presents you much less adverse selection.
That's right. So the claim that I make here is that all else being equal, a Prof enhanced relay should be more competitive. So what that means is if you are anyways a fast relay, you are going to be more competitive if you also enrich your blocks in some sense. So this analysis is for a relay and making it more competitive with enrichment.
But isn't there then a latency penalty that the fast
That's what we calculated for all the relays. So even if you have that latency penalty, your inclusion likelihood for Prof doesn't reduce, and the original workflow of relays is not disturbed. You still have the concurrent path of prof auctions, of the MEV auctions, so that path is not disturbed. So the latency is coming in the concurrent path, and the original workflow is not disturbed. So if you are worried about the relay becoming less competitive suddenly because of latency, that's not the case, because it's all concurrent.
Okay.
Yeah, we can take it offline.
I'll speak to you offline.
Definitely.
Thank you.
Thanks for the talk. Just a quick question on the latency side of things. With like timing games becoming more and more prevalent, are there, just out of curiosity, solutions to run traditional block building with PBS and then the prof bundles in parallel in any way? Or will there always be that latency penalty? Because I'm thinking that if the latency penalty is too high, the only way to address that is by increasing the transaction fees to get included in the prof bundle, which then disincentivizes users to use it in the first place.
Right. So here's the answer. If you look at the paper, we analyze it in very carefully in detail. The idea there is you have these latency games because they're kind of targeting a deadline. Now in prof, what you would say is at this time, say 11.9 seconds, I'm going to enrich the block that I have with prof bundles. So all the validators or all the builders who are playing these timing games, instead of targeting a deadline of 12 seconds, they'll target a deadline of 11.9 seconds. So it's just a matter of shifting that deadline a little bit, making it known to the players, and in game theory-wise, they would kind of get their blocks in just in time for enrichment.
Under the assumption that everyone uses prof, though.
All else being equal. So
Right.
whoever is using it, to that extent, it applies.
Got it. And it stays competitive with PBS-only builders.
Yes, that's right.
Thank you.
Yeah, quick question. So if there's a clear, transparent ordering policy used with prof, and there's a party at the user level which has a lot of order flow, wouldn't it make more sense for that party to withhold order flow and extract the MEV revenue at like the top layer of the stack instead of submitting it to prof? And maybe second part, have you compared it to like application layer auctions such as Sorella Labs, where you have competition between solvers building bundles? And have you looked at that comparison to prof?
So I'm not sure if that actually applies. So the idea is simple. Users who want protection just go through this protected route. You don't have any kind of leaking of what those, any arbitrage opportunities. So suppose that you start up a sequencer, okay? And you are just starting the sequencer in a way that's fair. For example, it could be fair ordering, blind ordering, any other ordering. If it's run in TE, it's not kind of exploiting users. You have that flow, and you just give it to a prof supporting relay, which would just enrich the block with those transactions. So in that sense, you don't have any competition going on inside prof bundle. So the kind of insight here is that you can have a block where there's a competitive path, an auction path, where there's lots of these competitions, arbitrages happening, but users who don't want anything to do with this, who want protection, just go through a different path, and everybody's incentivized to include them. So it's a merging of the two things.
So the user would have to choose at the application layer to send through a different RPC?
That's right. So if you are a user, you just select your favorite prof sequencer. If you trust the prof sequencer is good, for example, it's running on a TE, decentralized protocol, any of that, right? Then you send your transactions to that sequencer will forward it through a relay, get it included, and so on.
Okay, so you need adapted user behavior at the DEX level, for example. Like if I'm Uniswap, I need to choose a different RPC, but then it would work.
Yeah, I wouldn't comment on protocols, actual protocols, and Uniswap and so on. I'm just saying if you are a user and you are an educated user, you care about your transactions, send it through a protected route.
Thanks.
Thank you so much, Kushal. I guess the vibrant discussion is a testament to the interest for this. Thank you.
Okay. Thank you so much.
Okay, thank you for the speakers from the last session. And our last session of the day is a super exciting session. I'm really looking forward to the conversation. So Chris Dixon is joining us for the very last session. Let me introduce Chris just before we dive into our topics. So Chris was a serial entrepreneur, and then he became a VC, funded a bunch of companies, a bunch of the early companies in the blockchain space. Then in 2018, he actually created an entire fund just devoted to the blockchain space, the A16Z crypto fund. And I guess in his dealings with all the various companies and entrepreneurs that he was talking to, he became a very prolific writer. So I don't know if you guys follow Chris's writing, but he's a very clear and prolific writer and explains the space extremely well. Earlier this year, actually, Chris wrote this book. I'm sure many of you have heard of it. I hope many of you read it. The Read, Write, Own book. This was a New York Times bestseller. It's a super interesting book to read. I highly recommend it. And so because of this book and the fact that Chris wrote it, I thought it would be really interesting to have a conversation with Chris to share, that he could share his experiences with us. So Chris, thank you so much for coming, and let's welcome Chris to our session.
I think my quick Dan Benet story is I think we met like in the mid-2000s. I had a security startup, and I think I cold emailed you basically. And if you know Dan, you'll know that he's the kind of person that responds to cold emails from random people. And I got a chance to meet with him, and you were really helpful, and we've been friends ever since. So thank you for having me.
Yeah, awesome. Thanks, and thanks for coming, Chris. So let's see. I wanted to start the conversation actually by literally asking you, why did you write this book?
Yeah.
What is it for?
Yeah, I mean, you can kind of think of it like sort of trying to answer the question of like, what is this all for? Like, why are we building blockchains? Like, what's the purpose of all the, the kind of technical talks you've done today? Like, what's the societal goal? And specifically, I wanted to answer that question for kind of, am I getting echo? Am I okay? Is this okay? Sorry.
Yeah, it's good.
Okay, it sounds weird to me. I wanted to answer that question sort of for the general audience, but also specifically for policymakers, because I've spent a lot of time in the last couple of years in DC and other places trying to kind of explain the purpose of these things, why we care about it, and why we think there should be kind of smart regulation that provides clarity. And literally in those meetings, hundreds of meetings with policymakers, they would always ask what book to read. And there are a lot of great books about sort of Bitcoin and like the history of stuff, but I felt like there wasn't like a book that kind of summarized it all, and sort of from a societal point of view, like why does it matter? And specifically what I try and do in the book is break it down conceptually, like what is it, what are blockchains, why would you want them? And I think to understand that, it's important to understand the history of the internet. I've been working on the internet my whole career. And if you've been an internet entrepreneur or an investor, you know that the thing that matters on the internet from the point of view of economics or control are networks. So a network can be built with a protocol like the World Wide Web, HTTP, or email, SMTP, right? That's sort of an open, decentralized way to build a network. And that was the sort of dominant way to build networks in the 90s. And then in the 2000s, you had the rise of what I call corporate networks, which are networks that are centralized. So Facebook, Uber, eBay, et cetera, they're one company that controls that network. And networks matter because networks have network effects. So the more people that use a network, the more valuable it gets. And it's what creates essentially power and defensibility in these businesses, right? I mean, it's why you have, companies that control networks like Facebook or something, or Instagram or TikTok end up being very high margin, very powerful, very influential networks. And so my argument is that, what blockchains let you do is create networks. Like when people say Bitcoin is a ledger, sure, it's a ledger, but that's not why it's interesting. It's interesting because it's a network, right? It's a network that's a financial network that has certain properties that are different than other networks like PayPal. And so then I try to go very specifically and analyze what are those different properties? Like what is it about blockchain networks to make them special? And in summary, I kind of think of them as it's sort of a little bit thesis, antithesis, synthesis, protocol networks, corporate networks, blockchain networks. They combine the best features of the prior two kinds of networks. I like to say they combine the societal benefits of protocol networks, openness, decentralized software production, i.e. composability, low take rates, meaning that money flows to the edges of the network and not to the center of the network, community governance instead of sort of centralized governance, but also, so they sort of have the benefits of old-style networks like the World Wide Web and protocol networks, but they have a lot of modern other features like the ability to manage a treasury and to allocate capital and do all these other things that blockchains can do. So they're kind of in my mind, kind of the best of both worlds. And if you believe kind of my way of framing this, the conclusion is that blockchains aren't just good for financial services, right? They're good for anything where you might want to build a network. And so that could be financial services. It can be, a AMM or sort of a DeFi thing or Bitcoin, a store of value, whatever it might be, but it could also be a social network or games or systems, identity systems or whatever you might, anything that you've seen in the last 30 years where somebody has tried to build a network, that you can build a network using a blockchain, the same idea, and it'll have different properties. And I have specific, so sort of the book is, first third is history of the internet. I think that kind of stands on its own as a history of the internet, independent of blockchains. The next third is kind of a deep dive into what blockchains are and these specific properties of what make them different. And in the third section, I kind of speculate as to 7 application areas that I find interesting, not exhaustive, but just, you know, to give people a sense of it, because you often hear like, what problem did the blockchain solve, and these kinds of questions, and I want to take that head on. So anyways, that's the book. You know, I'm hoping it's a book, probably folks here, you know, I imagine it's a very sophisticated audience, like probably some of it is redundant for you, hopefully maybe some of the history and other parts are new, but specifically I hope it's a book that you would give to like your friends and colleagues as a book to kind of as a one-stop shop intro to the topic.
So
that was the goal.
yeah, I'm sure you gave this book to a lot of the policymakers.
Yeah.
you
It's like blanketed DC with it. I go with stacks of books.
So do you have any? So you know, a lot of the folks here are kind of asked to you know, opine about blockchains and such. Do you have any advice on how to speak to policymakers about the space?
Yeah, it's a good question. Well, I think that a couple of things. One is that because of the origins of this kind of movement being in kind of Bitcoin and maybe sort of more in like the libertarian side of politics, that branding is very strong in DC. And so honestly, you walk in there and you start talking about, you know, sort of quote unquote normal use cases like DeFi and stable coins. And that alone, I've heard many times, wow, you know, I hadn't heard that. We all sit around and talk about it, but it really just hasn't kind of propagated outside of.
You're saying folks in DC don't know about stablecoins?
I think most people in the world, and particularly in DC, think of blockchain mainly as Bitcoin and as sort of this alternative, hard money alternative to the government, right? And that's immediately threatening to policymakers. And that's just not going to work in DC to say like we're going to replace the US dollar or something like, it's just simply not. Like whether you know, some people would disagree with me, I don't think that will be a winning argument. And so I think a much more powerful argument is to talk about all these other kinds of interesting use cases. And specifically, like, so for example, I like to talk about the take rates. So take rate, just for definitions, is a term that goes back 25 years, it means the percentage of money flowing through a network that the network operator takes, right? And so, for example, you know, social networks, it's close to 100%, meaning they, you know, of the 150 billion in social networking revenue last year, YouTube is the only one that really shares revenue in any kind of de minimis way. The rest take all that revenue. You know, you build a decentralized social network, like something like a Farcaster or Lens, and, you know, by default, all of the money that goes in from one side flows out to the other side. So for example, creators who create all the content on these networks, right? The network operators don't create the content, the creators do. They actually make all the money in a decentralized design as one example. Like the economics one's a good one. You know, finance is another good example where there's very high take rates. Just, you know, you take a ride sharing, you know, Uber, I just the other day was in an Uber and you asked the driver how much he made and it was like $17 and I paid $60 and like, you know, there are taxes and everything else, but like there's a very high take rate in almost all of these internet networks. And so that, for example, is just eye-opening, I think, to a lot of people like policymakers, and the prospect of building a new set of internet services where the money flows out to the software developers, to the creators, et cetera, is an interesting argument to them. Another thing I think for those who were in the entrepreneurial world in the kind of last 15, who've been sort of in it longer, there was basically like 2005 through 10, like the hot thing in Silicon Valley, like I was an entrepreneur then, was building on top of social networks. People saw social networks as like the new platform. So there were companies like Zynga, and there's a whole series of, I list them in my book, a whole series of sort of venture-backed companies building on Twitter and Facebook, in the same way people are building on ChatGPT today or something. And there was a whole generation of them, and they all basically got killed when all of those centralized social networks decided to deprecate their APIs. So it was like 2011, 12, they all started shutting down RSS and APIs and everything else. And that's something that if you build a blockchain network, you know, you build a social network on a blockchain or some other kind of system, you can make strong commitments to developers, right? Like, you know, if you know that if you build on top of Ethereum or you build on top of Uniswap or whatever it might be, that you know what the rules are as a developer, right? Maybe they have a take rate, maybe the governance can change a few things here and there, but they're not going to go and say tomorrow that you can't build software or you can't build an Ethereum client, you can't. So there's a much greater degree of freedom and persistence and sort of long-term viability for developers building on these platforms, which is very, very important. You know, I think an interesting, an interesting kind of historical thing is open source software. So open source software now is probably 90+% of software running in the world. Linux is the dominant operating system in the world. For most of my career, open source, like in the 90s and 2000s, open source was considered this kind of weird fringe thing. Probably started really getting big in the probably mid-2000s and going mainstream. I think an interesting question is how did open source software like Linux go from being kind of this fringe political movement to being the dominant operating system in the world? And I think the answer, in my mind, is composability, meaning that it's the fact that all these different developers from all over the world can get together and contribute to things like Linux and other open source projects, and in a way that you sort of, that Warren Buffett, I think, says that compounding interest is the eighth wonder of the world, and the same, because you get this sort of compounding effect. I think in the same way composability, you get this kind of knowledge compounding effect of software getting better and better, right? And so all the work you're doing here, right, everything is talked about on stage, it's open source. You can see this work and build on top of it, and that ends up having these compounding effects. But a prerequisite of composability is you need to know as a developer that you can build this and you're not going to have the rules changed on you, right? Because if you go and you trust these platforms, there's sort of a whole generation of entrepreneurs who trusted the last wave of platforms and got burned. That was, for me, personally, a very, very influential time, was seeing all of those.
So I have to ask, this idea of composability, this is something you're actually able to explain to folks in DC, policymakers?
That's a harder one. I think in DC, I try to focus on the economics maybe, and some of the other kind of. Another one I like to talk about is AI. Obviously the stuff happening in AI is very exciting. Our firm is investing a lot in AI. I think, though, that there's a lot of interesting challenges that AI raises that I think blockchains can sort of provide the antidote to. So one example are deep fakes and sort of bots and all these other kinds of things. Like, to me, the obvious answer to these problems is you need a real identity system for the internet. The internet never really had one. You have DNS and things, but DNS, people forget, it's a business product mainly. Like, most consumers don't have websites today. It just didn't, it's $8 and there's a whole bunch of, a year and all these other kinds of points of friction. And so, what if everybody on the internet had a low-cost, accessible, easy-to-use identity where they could prove they're human, like, prove they're not a bot, and then, if they create a piece of media, they could attest to that media being theirs, as an example. And so you have sort of a system of trust instead of kind of default distrust. That's one example. I mean, there's a bunch of interesting stuff going on around people trying to put kind of like copyright information for training data and for the ability to remix media and things on blockchains.
But actually, along those lines,
decentralized compute networks.
Oh yeah,
a whole bunch. Like, you can sort of take every stack of AI training and inference, and you can, for each layer, I think people probably here are aware, maybe some of them working on it. People are building interesting decentralized versions of those, which makes, which I think helps. It's important societally because it helps counter AI. I think AI right now, with the the high capital requirements and data requirements, is naturally centralizing. Like, it's headed now, like, where you need, I don't know what, 100,000 H100s or something to train a frontier model. And so there's going to be 5 to 10 companies probably who can do that. And hopefully a lot of this software is open source. Like, I think Meta's doing some great work there, and Mistral and others. But wouldn't it be nice if any startup could get access to that same training cluster, for example, or fine-tuning data or whatever it might be? So sort of all the different things that a big company might have access to that gives them advantage in AI. What if you could decentralize those various layers and make them therefore more accessible, and therefore counter what's happening now, which is there's sort of 5 big tech companies that control most of the internet, and the concern would be that innovations like AI left unchecked would further that consolidation. So, like, how do we, I think that's sort of, to me, that's actually, when I talk to policymakers, the thing I talk a lot about is just, and that's actually in the intro of the book, is just sort of the centralization of the internet. The internet was meant to be decentralized, and we're really losing that. And I worry that right now, like, you just look at the data, like, look at what the networks are doing now. Like, Twitter is now banning links. Like, they're all trying to keep you more engaged. They're trying to, like, they're basically kind of really, like, the traffic going to the open web is declining. You're going to end up in a situation where there's sort of 5 social networks and 5 kind of AI search engine type things, and that's what people use. And linking out is deprecated, and what's the business model in that world for content providers. Like today, you know, a content provider, like most content providers, they get indexed by Google, and then you click through, and then they run ads or have subscriptions. Like in an AI world, you're just going to get an answer. You're not going to need to click through. So like, are we going to just end up with an internet with like 5 companies? Like, what is that? What is the incentive structure for that internet, for the future internet, where you have AI systems and social networks and things? Like, I think that's an important question. I mean, you know, people sort of think like it's, I don't know, like, is it over? Like, the internet's 30, modern internet, commercial internet's 30 years old. Like, you know, one argument would be this is sort of like the automobile industry. There's like, you know, it started off with 1,000 companies in Detroit in 1900-ish, and then it eventually consolidated into 5 companies, and maybe that's what the internet will be like, or maybe it won't be, and we can sort of fight back against that, and we can kind of return the internet to its original ideals as a decentralized and open system. I hope so. I think that's why I got involved with the internet. I thought that was an exciting architecture. It incentivized innovation and creativity. You know, how like, if you don't have a business model for paying creators and everything is AI generated, so what does that mean? Like, you're gonna just sort of remove these tens of millions of people that make their living on the internet, or are they gonna end up working in sort of data center style, like, which is what's happening now? The AI companies are going out and farming out, fine-tuning data to offshore data centers, and like, that's, to me, it's kind of this dystopian outcome that we might be headed for, where there's like five AI, the internet becomes 5 AI, you know, kind of search engines and 5 social networks, and all the data is farmed in from offshore, and then all the, you know, we think about it from a venture capital perspective of like, that's going to be bad from a startup perspective, right? Like, our business depends on the internet being dynamic, and you know, that's another argument that we make a lot with policymakers too. Is just like, it's good. You know, I think historically people in DC have recognized that having a dynamic startup economy, you know, in software and the internet is good for innovation. Yeah, you know, Google invented the transformers, but OpenAI commercialized them. Like, there's a long history. You know, Xerox PARC and Apple. Like, you need a vibrant startup ecosystem, I think, to really kind of take these innovations further.
Yeah, these are all pretty consequential questions. So it's good to hear that policymakers are receptive to that. So actually, along those lines, let's continue kind of to the next topic I wanted to discuss a little bit. So I'm sure everybody in this room is getting asked by people, like, the number one question that like folks outside of the space always ask is, what are blockchains good for? Yeah, what are blockchains good for? I get asked that a lot. And so obviously people have heard of the financial application. Yeah. But the question is, like, what are the other areas that have a good product market fit for blockchains? In the book, you kind of cover a bunch of other areas. So maybe you can talk a little bit about what, other than finance, what are they good for?
Yeah, I mean, look, the finance ones are important. So there's obviously Bitcoin, which, you know, depending on your kind of monetary views, I think it clearly has some product market fit with a certain, you know, kind of hard money crowd. I think DeFi clearly does too. I mean, you know, just look at the volumes of AMM, like Uniswap, and the stuff that like MakerDAO and Aave and all these folks are doing are really interesting. And I think people underappreciate, I mean, the fact that you can basically perform a lot of modern banking functions in a better way without, you know, using sort of having all this kind of institutions and people is a pretty impressive feat. I think the limiting factor, and I'll probably come back to policy a lot here because I'm kind of obsessed with it, because I think that's the limiting factor for the most part with DeFi, is just that it's sort of stuck in a playpen right now because you can only really use crypto assets, because creating a bridge to sort of real world assets or, you know, sort of traditional assets is just a giant kind of regulatory headache. I deal with it all the time. I think once we figure that out and you can just sort of take, you know, the rest of the economy and use these tools, I think it'll become much more powerful and less like kind of this kind of circular playpen sort of feeling, sandbox. Stable coins are, you know, trillions of dollars in transactions of stable coins. Again, not to be broken record, but like there's a lot of regulatory uncertainty, and that one I think we're very close to getting a lot more clarity on, and I think that will be important. I mean, look, dollar is the most popular U.S. export, period. I mean, it's like Coca-Cola and, I don't know, Marvel movies and iPhones and the dollar are like our most popular products. So, and it's just, and you see a lot of adoption around the world, and blockchains make it very easy. And there's a lot of, like you have companies like Stripe, they just gave a really interesting demo at their last developer day. showing off stablecoins. I think it's really compelling for a lot of payment companies and a lot of businesses who typically pay around 2.5% of all of revenues to payment processing, which is kind of ridiculous. You know, if you think about, you know, payments are just moving bits around. The fact that 2.5% of all internet revenue goes to that. So, I mean, I don't think, like you said, besides finance, I don't think we should dismiss that. Okay. You know, I think stuff around, there's a lot of interesting stuff happening with NFTs. I wouldn't say it's like full product market fit, but there's like games and people, you know, artists and creators doing, even now NFTs are down and everyone's negative on it, still billions in volume of people buying NFTs. And NFTs to me are interesting because they are a digital asset where someone creative can create something like in a game or some other kind of thing. And to me, the most interesting thing about it is you're removing all the middle layers so that all the money, except for whatever, like OpenSea and these marketplaces charge like 2.5%, you have 97% or something going to the creators. And so it's just the economic fact that you've got new business model, like I would say early stage, but really interesting new business models that where all of the money goes to the kind of edges of the network, to the creators and the game makers. And so, like, for example, there's a popular game called Eve that folks might know. It's been around like 20 years. It's like a spaceship kind of MMO game, and they're making a blockchain version where instead of it being kind of a pseudo-economy, it's a real economy, and you can design spaceships and have this all these sort of economic relationships. And then, but it's interesting is you can take the objects in and out of the economy and have real value behind them. And I think in the future you could imagine, you know, these kind of decentralized universes that are kind of games and workplaces where they have, you know, where the users truly own the assets and you have real kind of economies that aren't, you have sort of pseudo economies now. Like for those who play games, you'll know that the dominant business model for modern video games like League of Legends and Fortnite is virtual goods. So most of these games are free and you buy virtual goods, but it's a very centralized planned economy where the vast majority of the revenues go to the game maker. And so instead, what these games are playing around with are this idea of sort of much more of a peer-to-peer economy. So like one user might create some virtual good and then some other user buys that good and maybe the game maker takes a tax on it, but it's like 5%, not 95%. And so you have sort of a true peer-to-peer economy, which I think is really interesting going forward.
Then you can use the gaming assets for like real-world activities.
Yeah, or you can trade them across games, or you can have, you know, you sort of users have persistent inventories that can kind of go across different things. So you kind of flip the model. Right now, you know, every time you go to a new website or a new game or a new application, like you start over from scratch and it's fully controlled. It's like a fully controlled, siloed, kind of corporate-owned experience. And instead, you flip the model where, you know, sort of users have persistent identities and, you know, you have, like, I think the interesting thing with these new social networks is that you can take your identity and your follower list from social network to social network in the same way that you can take your email list. You know, the reason that newsletters are having a renaissance for those who don't follow it from the media world, journalists and things leaving, going to places like Substack. Why are they going back to email, you know, a 40-year-old protocol? Is it because it's a better protocol than messaging or something? No, it's because of the low take rates, because it's like a 10% you pay to Substack and not, you know, very high take rates of social networks. Why is that? Is that because the email news providers are nicer and like to take less money? No, it's because it's a decentralized network where the user, the creator, the switching costs are much lower. If they raise the take rates above 10%, the creator would switch to a different newsletter provider, right? So all these things are, like, all the economics of the internet, and this is sort of the point of the book, are downstream consequences of these architectural decisions. And so, you know, sort of creating new services that work more like email and the web where you can switch providers. Same thing with the websites. Like, why do you only pay whatever you pay, 10, you know, 50 bucks or whatever to Squarespace or Wix to have your website? Again, is it because they're nicer and they don't, like, why don't they take part of your revenue? Why don't they take more of the way that TikTok does? Because they can, because you can switch, because that's the way the web's architected, right? So all of these kind of things are consequences of the architecture. So it'll take a while to build. Like, a lot of these use cases are more ambitious, and I think will take longer to build out. And I think you've got to kind of get to a point where people get so dissatisfied with a lot of the status quo, and they keep their, you know, continuing to squeeze people more and more, like the creators. And I think that dissatisfaction is growing, and at some point, this is why you have these pendulum swings, I think, and like in the history of computing, you have pendulum swings back and forth between kind of decentralized systems like Linux and, you know, centralized systems like Windows, and I think you'll have a similar dynamic here on the internet.
Yeah.
So the short answer is, like, I think stablecoins, DeFi, Bitcoin, somewhat NFTs have product market fit, and I think there's a bunch of TBD categories that are kind of nascent.
Makes sense. Actually, I want to open it up to questions from the audience too. So you guys think of questions that you're interested in having Chris answer. But before I do that, there's two more questions I wanted to ask. We'll see how we do on time. So one question I wanted to ask is, there are obviously a lot of folks here who are from blockchain companies. Maybe you could talk a little bit about like what does the space look like now for blockchain entrepreneurs, and do you have any advice for new founders?
Yeah, I think it's a pretty good. I mean, for those who haven't been in the tech business for as long as I have, the pendulum swings always. This is not the sort of crypto summer winter cycles. Might be more exaggerated in crypto, but it's not unique to it. And there will be, trust me, on the financial side, there'll be cycles in every category, and there have been throughout my career. I started my career really in earnest in the 2000s when the internet was, itself was going through a winter. And so we're a little bit in winter, although there's still a lot of people funding blockchain startups, and it just doesn't seem to be, for the most part. I mean, it's always hard to raise money. I wouldn't ever belittle that. It's a challenge, and it's very hard to start a company and a project. But I think it's, one of the areas where VCs are funding stuff today. I think AI is obviously the other big one. I think, the people that are having a bigger challenge with fundraising are people that are maybe doing things that aren't part of those two categories.
Which two categories?
I still think blockchain, and besides AI, is probably the one, kind of where more money is. Yeah, and then in terms of advice, you say advice for entrepreneurs?
Yeah, let's say.
That could be a whole book. Well, I think I'll just be specific to this period because I think it's kind of we're in kind of I don't know what, it's sort of a volatile, I don't know if it's a bear market, bull market, I don't know, it's some kind of weird period, and I think we're just, and look, there's a lot of trouble with the regulation and the lack of clarity there.
In some countries.
In some countries, yeah. I think, I don't know, look, I would say overall, what I've found is that any new interesting area of technology takes time. I think there's a lot of revisionism around this, like AI as an example. You know this, Dan, has been 1943 was the first paper on neural networks. I started an AI company. My second company, 2008, was an AI company. It was a machine learning company. And there was a long history of this, very long. There was an AI bubble, financial bubble in the 1980s. If you think it was just academic, it wasn't. There was a whole thing around expert systems and companies going public. And I think arguably now, I think it's pretty clearly now working as a technology for the first time. So it can take a very long time. And it's very hard you can sort of predict it based on like the number of transistors and GPUs and all this other kind of stuff. But it's also very hard to predict exactly when these things will tip. Mobile phones, there was if you want to watch this documentary on a company called General Magic, which was a lot of the original people that created the iPhone, but they were trying to do it, I don't know what it was, like 13 years before the iPhone, yeah. And so these things can just take time, and I think we're in one of those periods now, and so I would say, I guess my advice would be if you believe in this movement, that you just, that persistence pays off, and it's worth it to kind of stay focused. There's a tactical advice attached to that, like, you want to preserve capital as an example as an entrepreneur. Like when we work with blockchain startups, like a tip, if you're working on like a SaaS accounting system or something, you might raise 18 months of capital. Like I was involved with Coinbase for a long time, and they would always try to raise like 4 or 5 years of capital. Like there's just a lot more uncertainty in these kind of emerging categories than in, let's say, more mature categories. And so, you're sort of choosing to live life at the bottom of the early part of the S-curve and not the top of the S-curve. And there's pros and cons to that. And I think, but being smart about it and like preserving capital, like building a great core team, staying focused on a mission, that you really believe in and kind of a powerful use case you believe in, whether it's infrastructure applications. And I do think that people that do that are rewarded. And I think that my experience has been that there's sort of this phenomenon in Silicon Valley, I like to call it kids soccer. If you watch professional soccer, they all stay in their position and pass the ball. In kids soccer, there's like 22 kids running on the ball. In Silicon Valley, it's like kids soccer, where like every year or two, there's a new trend, and like everybody's doing the same thing. And like that works if you're OpenAI. They've obviously done a fantastic job. It generally doesn't work for like companies, 10 through 10,000 who do that or whatever. Maybe some of them will make it through, but like there's a lot of that happens. And so I would say, don't get seduced by that. Like I mean, like, not to dismiss any other category, but just do whatever you're doing because you believe in it and you know, and not because of the trends around you or what, you know, the cocktail party chatter or whatever, and just stay, you know, kind of focused on it.
That's actually good advice. Just do focus on the things
yeah,
you
maybe,
believe in.
By the way, maybe you believe, and again, I'm not trying to dismiss any other, I just want to be clear, like I'm very bullish on AI as an example, but you should be doing it because you believe in AI, not because it's like a trendy thing to do, right? And it's just like supply and demand, like right now, I mean, again, like there's like, I was in San Francisco recently and like, it's just like 1,000 people doing like customer service chatbots or whatever. And so there's just going to be so much oversupply in certain categories. And meanwhile, like to me, there's this obvious big ideas around blockchain startups, like some of the stuff I was mentioning with AI, where there's actually very few kind of credible companies doing. And so there's just like a lot more kind of, you know, white space in this category, in this area.
Not to mention, you just have to spend a couple of days in this conference and you see all the technology that's being developed in the space, which is
yeah, and like a lot of
cool.
good things like the infrastructure. I think we're probably at a point now, like there's clearly a lot of improvements to do, and that's what you've been talking about at this conference. But we're at a point now, probably for the first time recently, I would say, with like 4844 and like the L2s on Ethereum and maybe Solana and some other things, where like it's probably just recently gotten good enough. So that you can do, you know, so that you're not as infrastructure constrained. I wouldn't say fully, like, there's people talk about a lot, like the UX and just getting the whole wallet experience, and maybe that requires account abstraction and intents and whatever. And you can always have lower gas fees and more security and everything else. But we're probably at a point now where, for probably the first time ever, I think, where, you know, like the getting down, the way I think about it is, we're basically at the point now where an application can subsidize gas costs, right? So like that's why 4844 is important, because like, you know, you get it from, I don't know what, like $1 to 5 cents for like a typical transaction, and then that means that, you know, just in the same way that application providers, you know, subsidize their AWS fees, you could imagine a venture-backed application sub. So you're basically getting because you want to kind of get to the point where where the transaction fees are effectively zero. You know, there's no friction. I always think of it as like we've got to at least get to kind of Web 2 parity. We've got to at least get to sort of user experience parity with like traditional web experiences, and then have additional valuable things on top of it. Is kind of where I think we really need to get to application product market fit, right? And so, you know, asking the user to pay $1 with a big scary pop-up, and they may get, you know, if it's the wrong hexadecimal code, they send their money to the wrong place. Like that's not acceptable. And we're now at the point where you're really kind of getting to that, which means that a lot of the activity should move to the application layer. And for that, though, I think, not to again harp on policy, but like that, the thing we're finding in our investment portfolio with our companies is that the regulatory stuff is a really huge issue, because they can't build the products they want to build because of their lawyers are telling them not to do this, and don't do this with a token or this or that, and, you know, with a wallet, and there's no, and the, you know, the SEC and other regulators won't put out guidance, and so it's all getting decided by court cases, which are now contradictory court cases. So which court case do you rely on? And so it's just very confusing, and, you know, it's hard enough to build a startup, and now you can't build the product you want to build, and you've got to like, you've got like a team of lawyers in every product meeting. And so, but I do think on the optimistic side, I think we're, you know, for those who follow this, like there's just a bill passed in the House called FIT21. I think that hopefully I believe in the next year we'll get that bill, go through the Senate, and I think will become law. I think is a good likelihood. I'm spending a lot of time on it, and a lot of other people are. And that will be a huge unlock, provide a lot of clarity on the token side of things. And so I think there's a lot of good momentum. There's a lot of it's a bipartisan effort, and there's a lot of support there. So I think that, the infrastructure, like there's a bunch of reasons to be very bullish in the next year or two. And so, you know, but it takes time, and so you got to stick it out.
So let me open it up for questions. If anybody has any questions, please come up to the mics, and it'd be nice to have some conversation. Great. Yes. Yeah, Aline, why don't you go first?
Thanks for your thoughts, Chris. Really interesting. I have a question about privacy. So, can you speak a little bit to the privacy for on-chain transactions, and kind of this tension between normal folks like me wanting to have privacy for our transactions and the unreasonable regulations that cannot be reconciled with this basic need for hiding who I'm paying and how many coffees I'm getting per day?
Yeah, so it's a good question. and we've made a bunch of investments, like Aztec and some others in that area. I think so. I mean, like I think you can't have things like medical applications and financial applications. Like people are not going to put their credit card transactions on chain publicly, right? They're not going to put their medical records on chain publicly. Like you need some level of privacy. I think that the challenge, again, I'm going back to policy here, but that's kind of on my mind. It's really the kind of issue, is that you've got these things like mixers and Tornado Cash, and that in policymakers' mind, privacy means, illicit finance. And so I think what we need, and look, the reality is, forget about your political views. I know some people in crypto think that it should be legal to do mixers, and it's never going to fly. It's not going to be legal. Like it's like there's no way that's ever going to be a thing. So I think the right kind of product question is how do we build systems that provide privacy, that balance these two things, right? That provide privacy for users, and I think you definitely need privacy for a lot of application use cases, but also make it impossible to do or make it difficult and aid law enforcement to do these, and I think. So I think there's a lot. I mean, you guys are the experts here. I think like the zero knowledge proof stuff is really interesting. I think, it doesn't make sense that you have to provide. Like, think about how many times you provide like your social security number and all this information you provide, and you provide all this stuff to a random local insurance company who then gets hacked. I think everyone's been hacked now. They don't even report headlines anymore when they've been hacked, right? How many times does your private information get hacked? I get these letters. It's like, you get free credit reporting, or it's ridiculous, right? It's like that's going to do.
I have more free credit reporting than I know what to do with.
And that's of course absurd. Like you get these, it doesn't work. And so it's just a bad system, right? And like the right system is you should reveal only what you need to reveal, right? To any provider, like if it's a financial provider, like you should reveal enough to prove your credit score, and no more, right? And so that's one layer of privacy, right? And then
so Chris, actually, let's try to get through a few more.
Yeah, and then and then the other thing is just like how do you then also allow like law enforcement to get involved in certain cases and things too, which is just going to be a legal requirement.
I think we call this compliance privacy. So
yeah, I feel like there's a lot of you got Dan, you're the expert and folks here, but I feel like this is one of these problems that a lot of it can be solved through cryptography and technology.
Yeah.
Or
I love it.
Yeah.
Great answer. Yeah, please.
Yeah, so thank you. It was a very nice conversation. And Chris, you had very good content in your book. So I have some questions. So like we've seen the disruptive technologies like blockchain networks like Bitcoin, Ethereum, and now a lot of startups focusing on infrastructure, right? Can we move up? And when you said that anything that can be represented in a code can be put in a token, sold, brought, embedded, stored, transported, or whatever a person might want to be. Like just like the unpretentious internet, early internet. What do you think, do we have that moment, or, because I see most of the startups are still focusing on the infrastructure side, right? For example, I see professor working at Chainlink focusing on asset tokenization. Do you think we are at a stage where we can focus on the application side more than the infrastructure for this blockchain networks?
Yes, I do. As I was saying before, like I think for example, the infrastructure is for the first time probably at a point where it's good enough for a lot of applications. So like think about what became popular like 3 years ago. It was mostly like DeFi kind of applications where you were moving $1,000, let's say, or $10,000, or transacting or trading, and so you didn't mind a $10 gas fee, right? But if you had like a social network or a game and you had a $10 gas fee, that would just be absurd, right? So I think many application categories just require zero or almost zero gas fees, and so we're, I think, probably, hopefully, at that stage or close to that stage. I think that's one. I think, look, the second thing is just, again, like, again, I'll repeat it again, but the policy stuff, like, right now you make a game and, like, is an NFT a security? Is a token a security? Like, it's just all of these questions, and, like, we were just talking backstage about how, like, he was just met with an interesting company that had a multi-sig design, and they had to kill it because the lawyer said the multi-sig thing might trip up an accounting rule. Like, it's just kind of like, I don't know how you build software with that kind of, those kind of constraints. So, but like, yeah, but I think we're finally at a point where, I'm hoping we'll see a bunch more. Like, what we need though is, I see it on Twitter, people are like, the VCs aren't funding enough of this stuff. Like, I think it's half our portfolio's application layer, so at least we are funding these things, but I think that one is the infrastructure, the policy stuff, but then two is the talent. We need to attract more. I think a lot of kind of good product builders right now perceive crypto as either too kind of infrastructure heavy or too kind of gambling, meme coins, casino.
The speculation.
Yeah,
Right?
yes,
Yeah.
exactly. And I think that's a real branding kind of problem with the space. And I think it's a sort of a hangover from FTX and a bunch of other kind of bad incidents. But, you know, and I think the way to fix it is applications. So it's kind of a chicken and egg thing, right? Like we kind of need, like I think having one or two big breakout applications that really clarify to people and make it crystallize to people why this is important and different. You know, think about how ChatGPT galvanized the AI movement and brought tens of thousands of good founders into that space building applications. I think similarly, we need sort of a break. Like I think one, like the bad news is kind of a chicken egg thing. The good news is it really just takes one application to really kind of galvanize and get a bunch of people in.
But then there's also folks in the DC that holds a constraint threshold.
I'm sorry, what was that?
But there's also folks in the DCs or the legal side or the government side that holds a certain threshold constraint to the, you know, that holds the barrier high for the applications to enter in this space. Do you think that, or is there's, because you manage the fund, right? You have the portfolio. Do you see that's happening, applications, or?
Sorry, I just didn't hit, you said because of DC?
Because there are also folks like the government or the folks or the legal stuff in the DC, right? They hold a high barrier threshold for certain things that cannot be done by the startups, right? Do you think that's going to change soon?
You mean just the regulation that like?
Yeah, the regulation for these networks.
I hope so. That's what I was saying before with like if we get some bills passed and things, I think it would be a huge improvement. It's just very hard. Like it's very hard. Like I think on an average company that like if we fund a $10 million Series A, they spend at least a couple of million on lawyers and legal fees. So that's expensive, but really the problem is not the money as much as the constraints it puts on what they can build and the time sink and everything else. So it's a huge issue. I mean, we're also, by the way, having this kind of, we're involved in the policy stuff around AI right now, because I think there's a risk that they're going to do the same thing to open source AI. If you follow like the debate going on in California right now with this really terrible, ridiculous bill that's going to basically kill the AI movement there. Europe already pre-killed AI in Europe with the AI Act.
Yeah.
And so yes, I think that people that are not, don't realize how delicate and fragile startups are, don't realize that when you sort of put 10 agencies on them and start subpoenaing them, like it's very hard for startups to survive in that environment. Like it's widely believed in the internet world that GDPR was a giant gift to Meta and Google.
Yep.
And really hurt the startup community because it's very hard if those GDPR is a European Privacy Act, it's very hard for startups to comply with it. By the way, you also have, everything's now littered with these pop-ups and all this other, it's just a whole bunch of secondary adverse consequences of regulation when it's not well thought out. But
Sure. So let's try to get through a few more questions. Quintus, why don't you go ahead?
I'll try to be quick. I think probably related to the previous question, you mentioned low barriers to entry, low switching costs, and some of the key benefits of some of the things we can build in the sort of broader crypto industry. And at the same time, you mentioned people raising big rounds because you need long runway to work on these difficult problems. But I'm curious, it sometimes feels like this heavily open sourced, heavily transparent, low barriers to entry kind of world we're trying to create also can be at odds or in tension with the ability to have sustainable business models. And I'm curious if you think there is that tension and if you have some sort of a taxonomy of the kind of business models that we have seen to be proven out or may still see to come maybe in different regulatory environments.
No, that's a great question. I mean, to me, this is sort of what's beautiful with the token model. So you think about it, like just take Ethereum as an example, right? Where what's beautiful about that is you've got the token is kind of the economic model and the business model and ideally the incentive model. And therefore there's no incentive to lock up your code. And ideally everyone's aligned around the kind of the network and they're trying to build it out. And now that's the idealization, right? The reality is like the tokens aren't necessarily distributed to the people that are building in the right way, because it's whoever happened to buy it early or whatever. The other kind of negative consequence of tokens is that it can create a kind of mercenary financialized culture where, like I think Bitcoin's the example of this, where just like everybody seems to be obsessed with the price and less with building. I think Ethereum is much better on building than that. And so that there's risks to the token model, but that's in theory sort of the beautiful, elegant thing that the token solves for is it kind of lets you do the open source model while also having a financial model that incentivizes innovation.
So I'm curious on how you view the relationship between token models and business models. Because I'm not really an expert in this field, but if I was asked about Ethereum's business model, I'd say it's like gas fees, and the token is just the ownership structure. So do you think like gas fees are the only way to like this like usage infrastructure fees are the only way to give tokens value?
I think it's interesting. So I think gas fees or like or sort of a usage fee, like a percentage, like I think people are talking about having a fee switch stuff on like DeFi networks. So they take like the idea they would take like 0.1% of every transaction. So if you have money, basically you have money flowing through the system, like if it's most of these blockchain systems do, you can have the network. How does Ethereum work, right? It takes, essentially it's charging you to use the network, and then it's using that money it makes to burn tokens, right? I think it does two things. It pays out validators for a security budget, and then it burns tokens, right? And so in effect, what that means is that the token holders benefit from the gas fees, and there's a nice relationship, right? The greater the demand for the network, in theory, then the greater that also creates upward pressure on the token. And so I think it's an elegantly designed system in that way. And it should align, in theory, it would align the price of the token to the usage of the network, which I think is a good alignment because you want everyone working together to, like in this case, right, with Ethereum, like how do you make the price go up? Well, you get gas fees to go up. How do you get gas fees to go up? You create useful applications. Like that's a good incentive loop, right? A bad incentive loop is one where people are incentivized to just go shill it or something, or not actually build things, right? Now, none of this is fully figured out. I have a couple of chapters in the book on the token model where I try to go through this in detail, and I don't think it's fully figured out, but I think to me the tokens are an incredibly interesting new way to think about internet business models and where you can sort of align incentives across all the different parties of a network that are participants in the network.
Thank you.
Yeah, cool. Let's take one more question and then.
Hi, thanks for your presentation. You mentioned what blockchains are good for. And I wanted to ask if there's a couple more things that I have in mind and how you think about them, whether they are relevant or not. One is kind of a consortium of like banks worldwide trying to replace clearinghouses as they stand right now.
Yeah.
And the other is a non-financial application where you have just data being stored in a way that you don't need a central party to manage this amount of data. Yeah. And that could be in a wide area of applications such as starting from the supply chain, where you have a bunch of people handling a lot of different products, and they want all these products to be stored in a way that it's an append-only structure, after all, blockchain. So it could be very useful there, and I have an application in mind for that. And the other is for a radical democracy, where you just trust less your representatives and you go directly on the blockchain and say what you want. And you don't do that just for the governance of the blockchain itself, but for the whole of society. And whether you think, like, are these reasonable or are they completely out of the picture for some reason?
Well, I think, so the first couple are easier to answer. So I think with like the bank consortium, I think the way to think about it is, so like, let's say and it's funny, I was just at Goldman Sachs having this conversation. But like, let's say you're Goldman Sachs and you deal with 10 other banks, and you want to create a trading system with those 10 banks, right? The right way to think about a blockchain is it's not solving a technical problem for them, it's solving a political problem, right? So the technical problem is if they look at it as a technical solution, it's like, well, it's a database, right? It's a database, it's a ledger, but that's not really what it's solving a political solution, which is these 10 banks don't like each other, and they don't trust each other. And so how are they going to work together on a common system in a way that they know that the other 9 are not going to rug them, right? Now, how do you do that? Like, historically, you can try to create a nonprofit. Like, forget about blockchains for a second. You create a nonprofit. Okay, well, how do you get great developers to work there? People have tried that. It hasn't worked. Mozilla and OpenAI started as nonprofits. They pivoted to for-profit. You can create a for-profit that are jointly owned. People have done that. It's very hard to pull off. It's very hard to hire the developers, right? A blockchain is a way for like 10 parties, let's say like a bank or someone else, who don't trust each other and maybe even don't like each other, to get together and build on a common system, and a system that has its own funding mechanism, can hire developers, can piggyback off all the work you guys have done in the open source and world and everything else. To say it's like an L2, like what I recommended to the banks is like, you guys should do like an L2 like base, like build off of the Ethereum world.
A foundation of sorts.
What's that?
A foundation.
Yeah, so just like, yeah, and so then you can build like a, whatever they want to do, like stuff that today, there's still a ton of financial stuff in the world that's still done on the phone, like bond trading and things, or on Bloomberg terminals, and they want to create an exchange, kind of an AMM type thing among a bunch of untrusted counterparties, and that's a really interesting way to do it. So that was the radical democracy thing is probably beyond my, I'll probably defer to the governance experts. I mean, that's a whole different like political science question that I don't know if I'm qualified to answer, but I think it's interesting to see people running these experiments, and I think that's one of the interesting things of the whole crypto world is that you're kind of, people say you're speed running, governance, all these governance experiments. Like we work with Andy Hall, your colleague at Stanford, who's a political science professor, and they're running all sorts, they're sort of looking and using blockchains as kind of a test bed to think about all sorts of different interesting governance structures. So I'll defer to the experts on the topic specifically, but I do think it's like we've got this really interesting environment to test these things that we didn't have before. And probably, yeah, something like you're describing should be tested obviously at a smaller scale in the internet community, and if it works, potentially could be broadened out.
What about the supply chain applications?
I think, again, like supply chain thing, again, it's probably interesting in that it allows a bunch of businesses who don't trust each other to work together and to have sort of a common substrate infrastructure that they can all build on that has its own funding mechanism and its own programming language. And, so similar like stable coins, like why, it's not like a bank could do what a stable, like it could have a ledger and keep track, they obviously do that today, they keep track of your balance. But what a stablecoin, say built on Ethereum does, is it now provides a shared infrastructure that all these different banks can use, right? Which is a network. Going back to my book, it's a network, right? It's like now you've got to, and it's not, so if you just look at it, that's one mistake a lot of people make is they look at blockchains as a database. If you look at it as a database, it's not that, it's sort of a slow, not that interesting data, but you have to look at it as a network. And networks, when you understand the history of the internet, you understand the networks are very, very important sources of power and influence and, economic power that now you've got a new way to build them and the way for like all these, so supply chain, I assume there's, many thousands of counterparties in those supply chains who, how do they want to interact with each other in a way that they aren't going to, that they're going to trust those intermediaries. So I do think it's interesting. But you got to think of it that way, as like a way to solve a political problem and not a technical problem.
Thank you.
Oh, wow. What a wonderful way to end the session. Thanks.
Great. Thank you all.
Thank you. Thanks for coming. Okay. We'll see you all tomorrow, bright and early at 9 a.m.